which, as you know, has a special focus on EIC, especially the morning session. So we'll start with a JLEIC update. First, we'll have Accelerator update, and then a Detector update.
Okay. Thank you for giving me the opportunity to present this talk. I will give an update on the Jefferson Lab Electron Ion Collider Accelerator concept on behalf of the JLEIC design team. Let me start with a little bit of history. In 2015 NSAC long range plan, EIC was first officially recommended as a facility, as the highest priority new facility after completion of the existing projects. And the requirements for an EIC were defined earlier in a white paper, and then they were propagated into the long-range plan. So the requirements were highly polarized electron and light nuclei beams, ion beams from deuterons to heaviest nuclei such as uranium or lead, variable center of mass energies from about 20 to 100 GeV, upgradable to 140, high collision luminosity of 10 to the 33, 10 to the 34, and possibilities of having more than one interaction point. Just recently, National Academy of Sciences evaluated the scientific merit of an EIC, and in its report it strongly supported construction of an EIC. So it found a compelling scientific case for such a facility, stating that it will answer central questions to completing and understanding of atoms, advanced accelerator science, as well as benefit other fields from medicine through material science to elementary particle physics. And it identified three main scientific topics of research at an EIC, which is origin of the mass of the nucleons, structure of the spin of the nucleons, and properties of dense systems of gluons. So this is our vision of luminosity requirements for an EIC. So here on the horizontal scale is the center of mass energy in EP equivalent, and the vertical scale is integrated luminosity in inverse femtobarns. So this plot was developed in collaboration, well, it was developed under the guidance of Rick Yoshida and his colleagues. And as you can see, the most luminosity hungry measurements are nuclear tomography and spin structure. At the low end of the energy spectrum, there is confinement and hadronization studies. And at the high energies, the primary interest is saturation. Even if you consider studies beyond what's been defined in the EIC white paper, still the studies tend to cluster in this region. The high luminosity studies with high luminosity requirements tend to cluster in this region from sort of 40 to 100 GeV center of mass energy. And also let me point out that the legend here is, this is electron polarization, this is ion polarization, U means unpolarized, L means longitudinal, and T means transverse. So as you can see, again, the majority of studies are done with polarized electrons and polarized light ions, such as protons, deuterons, helium-3. So what's the status of design of an EIC at Jefferson Lab? So we just completed a conceptual design of a 100 GeV center of mass complex. Its key features are modern technology, high luminosity, high polarization, and full acceptance detection as required by the white paper and subsequent documents. So the current work focuses on completion of a pre-conceptual design report of this. As I said, the design is complete. It's just a matter of writing it up. Where we are working on some key R&D, and at the same time looking at performance and cost optimization. This is a front page of our pre-conceptual design report. All right, so what does JLEIC look like? This is existing CBUF. electrons, highly polarized electrons, are injected at full energy into a new electron collider ring. The ion side of the complex is new. It starts with an ion source, 150 MeV ion linac with warm front end and the SRF part downstream. Then there is a 9 GeV figure 8 booster. As I will explain later, figure 8 shape is chosen for polarization control purposes and control and preservation purposes. So from the low energy booster, ions are injected into high energy booster, which has the same circumference as the ion and electron collider rings. And this is a new component of JLEIC if you compare it to the previous design. And what this does is this high energy booster serves as an accumulator. So it really relaxes the requirements on formation of the ion beam and really improves the duty factor of the whole complex. There are two detector, two interaction regions. One is designed, the other one is currently a space holder. And this whole design is also upgradable to 140 GeV center of mass. I won't say too much about it other than that to first order it will be done by doubling the ion energy by increasing the fields of the ion collider ring dipoles. So there were two summary design reports, two pre-conceptual design reports earlier in 2012 and 2015. And we are planning to complete a new one for this version of the design very soon in August of this year. All right, we really believe that EIC should go to JLab because first of all, this is really Jefferson lab physics that will be studied at NAIC. CBUF, we have CBUF, which is the highest energy CW SRF linac in the world, and that's important. So for NAIC, in order to have a highly polarized electron beam, we are finding that one really have to have a full energy injector into the electron collider ring. And this is what we have with CBUF. So it can maintain high polarization, high current electron beam by simply tapping off the beam stored in the electron collider ring. We have the freedom of designing a completely new collider complex using modern design and technologies. We have no constraints imposed by existing infrastructure, and we can develop a design that is driven by experimental requirements. We can implement a high luminosity concept. Luminosity is optimized around the energy of physics interest. With figure 8 design, we can provide high polarization for any particles, including deuterons. And we can design the interaction region to be full acceptance and deeply integrated with machine design as required for physics. And in general, our design provides a good balance of performance and low technical risk. I must mention that our design does not involve any superconducting elements other than niobium titanium technology, which is considered to be conventional technology. So what are the main design kind of concepts? So for one is high luminosity, which is based on a high collision rate of short, low emittance bunches. So this is really needed to achieve small beam size at the interaction point. So with low bunch charge and high repetition rate, the bunch lengths can be made short, which in turn allows one to provide a small beta star at the interaction point. And then cooling, synchrotron radiation cooling in the electron ring and electron cooling in the ion ring can provide small emittances of the electron and ion beams, so which in combination with small beta star provides very small beam size at the interaction point, which in turn leads to high luminosity. So this design is sort of similar to lepton colliders such as KKB, and this will be possibly the first time this concept is applied to an ion ring. High polarization is based on figure 8 design. I will say a few words about it later, but the bottom line is that spin precession in one arc is cancelled by the spin precession in the other arc, which lets you easily control the spin. And another feature is a full acceptance primary detector with a focus on far forward acceptance. So this is just a table of numbers in case you need it for your calculations. So you can find parameters such as collision frequency, beam current, beta star at the interaction point, emittances, and then at the bottom there are luminosity numbers for different configurations, for different center of mass energy points. So the difference between peak luminosity and average luminosity is that we assume that there is a 5-minute beam formation time and a 75 duty factor of machine operation. So if I represent this luminosity graphically, this is luminosity as a function of the center of mass energy, peak luminosity, average luminosity with some realistic assumptions. So you can see it maxes out in this energy range, which, as I showed earlier, is the most luminosity hungry, from about 40 to 80 or so GeV. And if you translate it into femtobarns per week as a function of center of mass energy, you can see it in this graph. So it's sort of a few inverse femtobarns per week. So you can scale roughly how long it takes for a certain measurement. The shape of this curve is determined by the beam dynamics. So at low energy is determined by collective effects in the ion collider ring. So where it's levels off, it's limited by the beam-beam tune shift. And then at high energies, we start getting limited by electron beam synchrotron radiation. So some of the key technologies required for high luminosity, as I mentioned, one is high energy electron cooling of the ion beam. So this is one of the R&D topics that we're working on. So we plan to use a magnetized electron beam to cool the ion beam with high efficiency. And then in order to have keep the energy consumption at a reasonable level, the electron beam, cooling electron beam, is energy recovered in an ARL. And then there is a circulator ring which circulates each cooling bunch 11 times in order to relax the requirements on the ion source and on the current in the ARL. Another key technology needed for achieving high luminosity is Crab crossing. For various very good reasons, NAIC has to have a crossing angle of the electron and the ion beams. So, well, in particular, it's needed to avoid parasitic collisions due to short bunch spacing. You need to make space for machine elements, which are separate for electron and ion. It's hard, or if not possible, or maybe even possible, to use the same magnet, for example, as an LHC to focus both electron and ion beams. And then it also has some implications for detection and detector background. So by using Crab cavities, we can restore an effective head-on collision, which results in a factor of 12 luminosity increase. Electron polarization, as I mentioned, is maintained by currently trickling a highly polarized electron beam from CBAF. To preserve the high polarization, the beam is vertically polarized in the arcs, and then is rotated to longitudinal rotators, and is rotated to longitudinal polarization at the interaction point by spin rotators consisting of solenoids and dipoles. Ion polarization, again, as I mentioned, is based on the figure 8 ring. So just to give you a feeling, what figure 8 gives you is if you try to do polarized deuterons at 100 GeV in a racetrack, you would need a Siberian snake of the order of 400 Tesla meters In the figure 8, you only need a solenoid with a field of about 3 Tesla meters. Of course, figure 8 always has some imperfections, so they govern the spin motion in the figure 8. But their effect is relatively small, so all you have to do is just to overcome these rotations due to imperfections. And by introducing a 3D spin rotator, which does small rotations about 3 orthogonal axes, one can provide any polarization orientation at the interaction point. So this way one can get polarized deuterons again and can do as many spin flips as needed without polarization loss by doing them adiabatically. And then at the end of my talk, just a couple of slides about the full acceptance interaction region design, detector design. So the challenge of a measurement in an AIC is that we need to really detect the whole event, consisting of a scattered electron, particles associated with the nuclear remnant, and particles associated with a struck parton. So these guys can be detected the first order in the central detector, but these particles are difficult to detect because machine elements get in the way. So the way we are approaching it is that we detect forward particles in 3 stages in an end cap. So ion beam goes from left, goes at the diagonal here. So large angle particles are detected in an end cap. Then particles with angles of sort of less than 3 degrees are detected inside this, are momentum analyzed by the spectrometer dipole and detected by trackers inside. And then finally particles that are not detected in this, inside of this dipole pass through the apertures of the final focusing quads, which are followed by 2 additional spectrometer dipoles that momentum analyze particles with very small offset and rigidity. On the electron side, there is a sort of similar setup, but it's done using a 4-dipole chicane. This is just a schematic of it. So low Q-squared electrons are momentum analyzed by the first dipole of the chicane and detected here. There is an extensive R&D program, multi-institutional, interinstitutional R&D program. These are just a few examples, so we're actively collaborating with our neighbor ODU, Brookhaven, SLAC, Argonne, and other institutions. So this is just a few examples. So in conclusion, I would like to show this table compiled by Rick Yoshida. So as you go from white paper to long-range plan to NAS report, the requirements don't change very much. So basically, as they were defined in the white paper, they were inherited by the later documents. And JLEIC design, in fact, addresses each of these requirements of the white paper. Thank you.
Thank you very much. Questions for Vasily?
You said the cooling of the ion beam is done by magnetized electron beam. What's a magnetized electron beam?
It means it's, well, my understanding is that it's a beam where one emittance is small and the other one is large. So inside the solenoid field, you can turn it into a round beam with a very small angular spread. So it's magnetized because it has to be born inside the solenoid. So that way you can have a large beam spot size, but one of the canonical emittances is small. So inside of a solenoid, the beam electrons are moving parallel, so they're moving along the beam lines. And the reason you want to use magnetized beam, because if you don't have this, then space charge makes both emittances large. This way, with a large spot size, you can still keep one of the emittances, one of the canonical emittances small.
Yeah, this figure 8 and the cancellation of the unwanted spin components that have been introduced. What will happen if there's a small deviation in the magnetic field? The spin starts rotating a little bit, but now also as an effect of that, the orbit is a little bit different.
That's exactly so. We've done a lot of studies. So that is what the main question about figure 8 is, right? So in figure 8, of course, is not perfect. So the spin motion is governed exactly by those, imperfections, by closed orbit excursion. So we've done a lot of work. We developed an analytic theory. We've done a lot of simulations analyzing effect of closed orbit excursion. So, and I think we understand all of that. Of course, so we have to introduce something to overcome the imperfection effect. And in fact, there is an R&D project basically to test this concept at Brookhaven. It's not a figure 8, but with 2 Siberian snakes, you can make it topologically like a figure 8 for the spin. So we'll test our theory and our predictions in an experiment. But you're right. So that is sort of the main question about figure 8.
Any other quick question? Last question.
Maybe not question, but brief comments to support Vasily's reply about figure 8. Actually, he showed explicitly that we introduce also so-called spin navigators, which actually stabilizing the spin in figure 8, but the strength of this navigator is pretty small for all energy range of interesting EIC energies. And then we can easily control this stability, but we don't meet any resonances, and we can choose working point about frequency, spin frequency, introduced by this stabilizing spin navigators, and also we can choose carefully orbital tunes in order to stay away of dangerous spin resonances. This situation in this context is similar to a brilliant performance of RIC PP collider with polarized 2 proton beams, and where polarization maintains during a day, even for intense beam, which introduces, due to the beam interaction, very significant high-order nonlinear resonances associated with beam emittance. Nevertheless, polarization stands long time. There is no reason to consider that there may be something unexpected in figure 8. We have best experts in the world in Novosibirsk who actually driving this research, been supported some contract work. So there is no doubt that figure 8 will perform brilliantly, as well as Siberian snakes in polarized RIC with 2 proton beams. And finally, it also provides, as Vasily working together, incorporating with this group of Russians in Novosibirsk and Moscow, for concept of so-called spin transparency, which actually based on figure 8 features. And the main interest to this, one of the main interests is possibility for stable spin flip, which is very advantageous for detection of working with polarized beams for at EIC and maybe in other colliders as well. Other opportunity for deuteron beam just do not exist anywhere so far.
We need to move on. Let's thank our speaker again.
Thank you.
Okay, so our second talk is on the detector design by Dmitry Romanov.
Now it's working? Or not? I mean, is it close enough? Okay, so I want to greet everybody, and this is actually continuation maybe of what Vasily talked. At least I want to thank him once again because he will shorten several slides of my talk. And here's a brief outline that I will first introduce the detector design. And one of the, yeah, that's the problem that I don't have. Yeah, probably I have to. Over here? Okay, over here? Okay, excellent. Now I think it's okay right now, right? So, and thanks for the clarity. Didn't notice. So in this talk I will introduce to the detector design, and actually what happens for the last year, one of the major changes is moving to 100 GV, so thanks once again Vasily for about this. And the spoiler is there is no actually major detector update for this, so conceptually it's still the same. There are certainly some changes in beam elements, but still the concept is the same. But there are significant updates on the detector and simulation software, which I will actually cover in second part of this talk. So, talking about EIC once again, so it's going to be the frontier accelerator with a versatile range of beam, actually with polarization and with a pretty large physics program. So what is the detector to cover these needs? So as Vasily said, here's the actually picture, schematic picture of typical interaction in EIC with electron. Actually on all pictures, electron will be coming from the right side and the ion on the left side. No. Okay, I'm wrong. Okay, so the idea is to capture all fractions of the interaction. So, and as it was said in the last slides of Vasily, so the electron and the struck partner part is more or less covered by the central detector, which is pretty typical for collider experiments. But this remnant part is going to be cut in this forward region, which is covered over here, because actually many physics or important physics in our field requires this. So in order to do this, the particles will transfer for beam elements, and we will have kind of 0-degree calorimeter over here and Raman pods and other detectors over here. So in general, here's the kind of schematic picture from the JANT of our full detector with central part, and the target is actually interacting point, or not target, interacting point is actually over here, and we have electron cup, we have hadron cup, and we have this far forward region. As in Vasily's slides, the beam elements are green over here, and here we have the electron part out of it. So for each part, as it was said several times, we need 4 pi coverage. So for tracking part, we have the vertex detector right insert. Around it, there is a central tracking detector, which on this picture is a planes, but we can see there are actually other options. And we will have actually coverage with gems on the caps. So the magnet, there was some updates in the magnet with this transition. So magnet was from 3 Tesla to 2 Tesla. And also we actually removed these coil walls. Still, we await that this design won't affect our tracking in central region. And actually, the magnetic field allows us to have, this is the field profile, to have kind of low influence on the rich detector. So calorimetry, once again, we kind of try to stick with 4 pi calorimetry in central region. So with barrel electromagnetic calorimeter, and we have precise calorimeters for kind of close to beam small degree angle particles, and we have hadron calorimeters around. So needless to say that we need a pretty good PID. So for PID, in the central part, we have a barrel Dirk detector. We have a dual reach over here. We have a modular reach on the electron side, and time of flight. So tracking, PID, and calorimetry is more or less covered in the central part. So here's the more schematic picture of this far forward region where we have, so once again, green is beam elements. One of the updates that we will use Roman pods, which are located over here. Actually, 0 degree calorimeter in the kind of more real scape is over here. And yeah, that is more or less what we have in this far forward region. And finally, there's a electron part where we will have luminosity monitor, polarimeter. It's not on the picture, but actually team is working on making it there, and low Q squared tagger. So actually, because this design requires this far forward region, and we have to work very closely with Accelerator team. So what we did was kind of quasi-automatic way of importing the information from the Accelerator team and the CAD design, then to simulate our detector and maybe make some corrections. So this diagram shows this optimization. And if we start talking about it, we are coming to this EIC software and simulation part, which is one of the major updates for the last year, I could say even last 9 months. So on this diagram is the this is the most simple and the most straightforward diagram of the software simulation, where we have generators on the top, we have analysis on the bottom, and this actually arrow denotes that sometimes you just want to analyze the input of the generators, but certainly sometimes you need some fast detector simulation, or as it's called, smearing, right? And sometimes you need full detector simulation. So for this diagram, that is the software that we now provides. We have a bunch of generators that we work with, and we're going to provide the generator database where we will have kind of pre-generated data samples which you can just take and analyze. So on fast simulation, we will have this combined effort with BNL and NAS called EIC smear, where you can define pretty simply the smearing parameters, and actually excellent tool for fast prototyping of a detector. So if you would like to kind of simulate quickly what's happening on the detector side, it's the tool. So we also provide a new JANT called G4E, JANT for EIC, which is a plain C++ JANT which performs the full simulation of JLAB detector. And finally, we are working on the JANT for fast mode, once again for full simulation, but with magnetic field and everything. So on this reconstruction and analysis side, we have this EIC, JANA, and JANA is JLab born framework, modern C++ framework. So, but one very important stuff here is actually this configuration. How, because each of these packets certainly have its own kind of parameters or configuration files, but the question is how it's easy for users to actually navigate between these boxes. For example, I want to take this generator and put it to EIC smear. Okay, I analyze it. Then I want to do the same, but with a full simulation. How long time would it take to actually reconfigure, and moreover, and more important, how to learn how to do it. So we actually provide some software and this entry point for EIC, which should allow to more easily and more convenient way how you actually configure all those pieces together. And there are other software which I will a little bit cover later. So from the target audience, so if you can view on the software from the people that are using the site, right? At one point we kind of identified 3 groups. And one of them are just collaboration users that use usually collaboration software. ePhoenix is a good example of it, so it's kind of out of here. I mean, then there are the detector groups who do detector R&D design, and what they need, as we think, is to, if they have their simulation, the detector simulation, they wanted to put this JLEIC design and see how it performs. And there are certainly general audience who just want to do a physics study. So in terms of these groups, that is how it plays with this diagram. So we see that for people who want to fast prototyping, there's the way. And for detector R&D, the main tool is going to be this full simulation jump. So it's probably important to mention that before we actually used GEMC as main simulation tool. Now we actually created this jump for EIC, and GEMC first then announced that GEMC is still there, so if you use it, you can continue use it. But the reason for appearing for this jump for EIC is actually driven by community, because they wanted to actually apply in C++ detectors first, and then the second, I kind of can announce that there is an effort right now ongoing between Jefferson lab and Brookhaven to have a single simulation tool, so single jump. So this jump for EIC is the first step, trying to put all the detector together. And finally, actually, in the beginning of July, we will meet with developers of BNL, and I hope that in the end we'll come up with just one tool, because right now there's outcry of the detector teams that they just have to implement their detectors for different jumps. So we want to fix this situation and have one. So on the ones set on the analysis part and actually reconstruction part, we use this Jana tool. And I think the most important here to say that we used again feed for track reconstruction, RAVE internally as the vertex finding, and this tool is pretty modular and easy to use. There's a new thing that we are actually going to provide called entry point for EIC. The idea behind that is that imagine that you are a new user for EIC. I think many of you can imagine it, and you want to start with EIC software. So right now there is no kind of entry point or something where you can start with. So we wanted to provide it, and it's not only kind of the link on the website saying that here is the software, you can start reading, installing it on your machine, whatever, but we actually want to provide some interactive shell baked with Jupyter Lab and Jupyter notebooks that can provide you very documented way to run the code. And we hope that this will help new users to start with our software quickly. So, as I mentioned about how you get the software, this is the ways we are going to release everything. So right now we take our accent on containers as the pretty convenient tool how you can run it on your machine with one line. But actually we provide full spectrum of ways how you run software. You can run it on cloud without installing everything. So you can install everything on your machine, and there are some middle variants which we will provide pretty soon. So here's the this slide is more or less what is ready and what is not. And as you can see, everything goes to the beta, and by beta I mean that probably there could be some bugs, but it's ready for use for users. And that is actually one of the main messages of this talk, that at this point we created some kind of basement or for our software, and is actually getting ready to get used by users. And what we really would like to have right now is user input, because users must steer the software and actually kind of guide us to the future development, because our vision of software that we, with our small group, cannot do everything, and we actually count on users to drive and guide us. So we will provide help for this. So if you want to start simulating, studying, doing physics for EIC, at this moment, come to us, and we will guide you how you start. So besides the software, we also actually participate in a number of activities. You probably know that machine learning is getting the more and more hype around the world, and we're actually participating in studies how we apply machine learning for our detector. And one of the work is Bayesian optimization, which allows you to kind of multi-dimensional optimization of the detector design. So right now we're working on the several detectors, but also on this far forward region. We also investigate kind of new approaches in the machine learning, how we can apply it in the algorithms. We actually investigate how we apply this, how we can put this machine learning, for example, to FPGA for streaming readout and other stuff. And we also try to adopt the new emerging data science tool in our field. So this is all done within this EIC center at Jefferson Lab, and you are more than welcome to come with ideas or whatever work which are there. So finally, I want to mention, as Vasily, that there's actually a large R&D program, and there are several user groups that are working with us. So thank you very much for the attention. Once again, if you want to start using our software, it's more or less ready for you. Just come and try doing physics analysis with our detector. Thank you.
Thank you very much. Questions? No questions?
You have any training sessions planned?
Yeah, thank you very much for this question. So the main release point will be in 1 month on the EIC users group. And we plan to have tutorials there. And we will provide actually this tutorial in Jefferson Lab. There's going to be a full tutorial with how you start, how you run things. And also there will be a written tutorial. And right now we are in a stage where we more or less have all the bricks running. And we are extensively working on the documentation and stuff. So at this moment I say come to us to start with software, but I hope that in 1 or in 2 I could just provide you a link.
Other questions?
I'll shout. Can some of these tutorials be attended remotely for people from Europe, other countries, South America and so on?
I believe so. I could say that we will first introduce these tutorials for this EIC user group meeting, but then we plan to have them regularly, right? We plan to, for example, actually make these YouTube videos with these tutorials. And certainly we can work on how other people like Europe and from Europe or whatever participate in them.
Can you comment a little bit on the status of the reconstruction part of the software?
What part?
The reconstruction. Can we already reconstruct tracks coming out of the JM4 simulation?
Yes, we have actually. So as I put it here, right now we are using the GenFit for reconstruction. Yes, so actually hits coming from from the gent, just go to the GAN fit and we have reconstructed information. We cheat a little bit on PID, but we are working with PID team, so right now we have kind of fast simulation and reconstruction on barrel rig or on a barrel dirk detector. So yes, actually the reconstruction is actually is getting there as much as we get R&D detectors, R&D and stuff.
Thank you. If there are no other questions, let's thank Dimitri again.
One thing at a time here.
So Barbara will cover the last talk of the session before coffee break on the physics of EIC, QCD, and electroweak.
Well, that's a huge range, and needless to say, I'm not going to cover all of it in 40 minutes. So my actual title is QCD with jets at the EIC. And first, I have to get this high enough so you guys can actually hear me. So I want to thank you for the invitation to come here, and I hope that by the end of 40 minutes, I'll convince you that we have some exciting new science that we can do with jets. Of course, my talk is going to be from the point of view of a heavy ion physicist, and that means that I'm very interested in looking at how do partons interact with matter, and I'm going to talk about how we can use jets to study that. So, of course, before talking about what to do with jets, I want to tell you, what are the processes that produce jets at an EIC, what's in the jet, how do we measure them, and then I have a few QCD topics that can be studied with jets. I'll talk a little bit about some mysteries of the interactions of partons with matter and how we can use the EIC to get a handle on those. And I have a few words to say about hadronization, which is one of the things we all are interested in using the EIC to better understand. And I have maybe a few insights on what we can do with that. So here's a nice list of the sub-processes that produce jets at the EIC, ranging from jets from resolved processes to deep inelastic scattering, QCD Compton, and photon-gluon fusion. I want to focus a lot on the deep inelastic scattering because it has the beauty of being able to very nicely fix the kinematics by measuring the scattered electron, as you all know much better than I do. The question really is how best to study what happens to the struck quark. And jets are a very nice way to do that, because if you can reconstruct the jet from this quark, you actually have good access to what has happened to that quark without having to know fragmentation functions that give you single hadrons. So that's the kind of 30,000 feet driver as to why you might be interested in looking at jets. So what is a jet? Well, it's a coherent object. We know that traveling through the vacuum, a quark undergoes a probabilistic cascade of gluon emissions, as you can see here in this little cartoon. In the course of these emissions, the total color is conserved, and the successive branchings are ordered in angle, where the initial branchings where you have hard gluon emission, those are in small angle. The color coherence suppresses large angle radiation until the very end. And so, in fact, a jet will have collinear hard particles inside, and at larger angles is where you see the soft radiation from the last steps. What you actually see in your detector, of course, is a sort of relatively collimated group of hadrons. And that's then what we need to detect. And to give you an idea of what jets look like at the LHC, here's an actual picture of a dijet. This was taken by CMS, actually in a heavy ion collision. This is a calorimetric measurement. You can see here a 200 GeV jet and a 70 GeV jet. You can see exactly this correlated bunch of particles. So that's what we then need to go ahead and measure. A few facts about the jets. So how you might ask how many particles are inside. This is an analysis by CMS of those kinds of jets that you saw in the last picture. This is a distribution of charged particle tracks inside the jet as a function of this interesting variable. Never mind the variable at the moment, because all I want to do is to integrate and see how many tracks are inside. If you add them all up, you find out there's something like 7 or 8 charged particles. If you add another 1/3 as many to account for the neutrals, which you can measure in the calorimeter, then you find out that in these sort of roughly 100 GeV jets at the LHC, you're looking at 10 to 11 particles that are, again, pretty closely correlated in angle. So to measure the jets, you obviously need a pretty large coverage in order to be able to look at jets across a large kinematic range. You need hermetic tracker, because if you have 10-ish particles, you don't really, you can't afford to lose very many of them. And if you do, then you have to correct for that when you reconstruct the jet energy. You certainly need an electromagnetic calorimeter, which is hermetic, in order to catch the neutral particles. These two things, I think, are features of all of the EIC detector conceptual designs that we've been discussing so far. You obviously need tracking and good electromagnetic calorimetry to measure the scattered electron precisely. I put a question mark by the hadron calorimeter. You do have a significant advantage in measuring jets if you use hadronic calorimetry. First of all, they give you an unbiased trigger to look for the jets, and they also are quite helpful in the resolution of the transverse momentum of the jet by catching all of the hadronic energy. So, of course, in order to have a precise measurement of the jet spectrum, you need to understand your tracking and calorimetry efficiency and the detector response very well. And that's in order to unfold the jet energy, take what you measure, correct for all of the errors in the measurement, and come back to the information about the struck quark. So how will we reconstruct jets? Well, the basic question is which hadrons belong to the jet. Now, in the hadron collisions, such as the one I showed you the dijet in, there's an underlying event of particles from other sources. In proton-proton collisions, that underlying event is relatively small, but not zero. Needless to say, in lead-lead collisions, that underlying event gets really quite huge. In EP and EA, that is not going to be a problem, and that's going to give us some nice advantages. Now, currently, the jet algorithm of choice is called anti-KT. Now, what do you do? So you have an event. You think there should be a jet. You start looking for the jet by picking out the hardest either hadron track or calorimeter tower. And that's your seed for the jet. You then calculate the distance to other particles around it with a weight of 1 over the square of the KT of that particle. And KT means that it's the transverse momentum with respect to the seed. So you look at the distance in both rapidity and azimuthal angle. And basically, you go along and you cluster the softer particles with the harder ones. The 1 over KT squared weight means that you give the largest weight to the how do I explain this? Basically what you do is you cluster the softer particles together with the hardest one. And you keep adding in the particles until no more remain within a distance of 2r. The effect looks something like this. Again, in a high energy proton-proton collision, you find that around your seed you have roughly circular clusters. Now, typically in hadronic colliders, both in PP and especially in heavy ions, you use a distance parameter of something like 0.4. That is to allow a statistical subtraction of the underlying event. I was going to say precise, but in fact, there's quite some fluctuations event to event, so the underlying event subtraction is not extremely precise. Of course, if you cut off this range in which you cluster all of the particles together, then you are going to miss some of the parent parton's energy in the energy of the jet. That's something you try to correct for, but you cannot correct for it exactly. It would be much better to be able to use a larger R, such as 1, and that is going to be feasible for sure in deep inelastic scattering, probably in all of the EP collisions that we'll see at the EIC. Okay, so having defined a jet, what can we actually do with it? Why do we want to bother with this? Well, if you make a list of the physics that you can do with jets, you can measure the parton distribution functions in nucleons and nuclei, and look at the evolution in X and Q squared. Now you might wonder, why bother doing that with jets if we can do it with DIS? Well, being able to reconstruct the struck quark allows you to actually separate the different processes, and compared to measuring to semi-inclusive DIS, where you measure 1 or maybe 2 of the hadrons, if you use a jet, you don't have to worry about how well you know the fragmentation function. In fact, by reconstructing the jet, you can measure the fragmentation function, allowing you to do a much more precise job with the single hadron measurements. And of course, in nuclei, it's very interesting both to see how does the distribution function get modified by the binding of the nucleons in a nucleus, particularly at low X, where you have a large overlap among the partons of different nuclei. And measure the photon PDFs. Gives you another tool to look at delta G, and it gives you a way to pick at the parton interactions with the cold dense matter in the nucleus. So here's a slide that I borrowed from Elke Aschenauer, how to access the C quarks using deep inelastic scattering. I think this is a process that everybody in this room knows better than I do, where by measuring 1 or maybe 2 of the final hadrons, you can actually get at the, together with the scattered lepton, then you can get at the distribution, the PDFs. Of course, there you need to know the fragmentation function. Can measure W exchange. Now, if you reconstruct the jet, then you actually can figure out the subprocess, and you can measure the fragmentation functions. Now, how well has this, what do we know about jets in DIS? Well, there's a legacy from Hera. This is a plot that, of course, we've all seen 1,000 times of the distributions of the valence C quarks and the gluons. And here's a plot of the inclusive jet production at a variety of facilities, starting with 200 Jev root S from STAR, going all the way to 7 TeV at the LHC with data from Atlas and CMS. I show you that to kind of set the stage how precisely measurements have already been done. I think with the EIC we'll be able to do much better in terms of precision. You can also study the PDFs of the photons by looking at dijets in the resolved process, for example. And by reconstructing the PT of both jets, you can actually then reconstruct this X-gamma observable, which allows you to separate the resolved and the direct contributions and actually use the resolved to have a look at the PDFs here. Now, to look at the spin structure of the photon with jets, there are two things you would like to have a look at. One is to look at scaling violations in the single jet cross sections. There's a simulation of how well that's going to look shown here. The little green corner shows what's currently known from jets. And of course, the EIC will fill this in depending on which square root of S you make the measurements in. Furthermore, you can look at ALL, the asymmetry versus the dijet mass, and by doing that and mapping as a function of X gamma and Q squared and XP, you can actually separate the different processes. You may be looking at this and thinking that's going to be a challenge, and it will. However, it's a way of making the delta G measurements with a completely different set of systematic uncertainties than the G1 measurement. So that's, I think, very promising. Now, of course, since I'm the one giving this talk, I have to tell you about why I'm up here interested in making measurements of jets at the EIC. We are stuck with some interesting mysteries from the studies of hot QCD. You might think that by now we would know where the energy lost by fast particles transiting hot, dense QCD matter, where does that go? In fact, we don't really know where it goes yet. We don't understand the energy loss process very well. And in order to make progress, the basic question we need to answer is how does the hot QCD plasma transport energy? Another mystery, which is actually closely related, is why does hydrodynamics work so well in heavy ion collisions? We know we can describe the evolution of the quark gluon plasma with hydrodynamics extremely well. We also know by comparing hydrodynamic simulations with data that hydrodynamic flow sets in extremely early, very quickly after the nuclei interpenetrate. And we also know that even very small systems like proton nucleus or even proton-proton collisions with a high final state particle multiplicity, they also exhibit hydrodynamic flow. How is that actually possible? In order to make progress on the understanding the process that makes that possible, the question that we need to address is how does cold QCD matter transport energy? So let me talk about that a little bit more to try and set the stage of what we can measure to understand better. Well, it's difficult to measure directly how the energy transport works, of course. So what do we know about transport in cold QCD matter? Well, we know that you can have incoherent interactions among the gluons that come after the first splitting when you have a parton going through vacuum or matter. You can also have, of course, you need some matter in order to have interactions with partons from the medium. That can be incoherent or that can be coherent. Perhaps the coherent scattering is very important to quick, rapid isotropization. Now, I write isotropization because that's what you need for hydrodynamics to be a valid picture for the hydrodynamics to actually work to describe the data. We know this experimentally. You don't actually need full thermalization. You just need the longitudinal momentum of your initial stream of partons to be sufficiently isotropic that hydrodynamics is the way to go. So perhaps we have a lot of coherent scattering. Or perhaps the system is already involved in many body interactions that change the distributions rather than just the sum of individual proton-proton collisions. A heavy ion collision is a collision with a different distribution. For example, if you have a saturated system of gluons, you have a large cross-section for gluons, two gluons to fuse into one, and that can also change the interaction of the partons with the medium. So how do we get at that experimentally? Well, if you ask the QCD theorists, they will tell you that you start with this nice angle ordering emission gluon splitting in the vacuum that I talked about earlier. If you then embed this in a medium, of course you have interactions with partons in the medium, and what those do then is that gives you changes from an angular ordering cascade to a time-ordered cascade. And this then, these additional scatterings are going to suck some energy out of your initial forward-going parton, and they're going to, each one of these will in itself make another cascade. So how do we find out if that's actually happening? We can study that by looking at the substructure of the jet to figure out how this 200 GeV jet loses energy, transports some energy into the medium, and it looks like this in your detector. Now, in heavy ion collisions, we know that these very high energy jets are primarily formed, so hadronized, outside the quark gluon plasma. We know that they start to radiate these radiate gluons as they transit the plasma, and then you have secondary showers. We expect that the softer jets, well below 100 GeV, should be forming inside the plasma and resolved by it. We can see if we turn down the energy of the jets that they get wider. So this is a distribution of particles inside the jet plotted as a function of the distance from the center of the jet. And in a central lead-lead collision, you can see that you get an excess of particles out at the outer edges of the jet. If you look at the PT distribution that's plotted here, what you actually can see is if you take the ratio of gold-gold over PP at RIC, and you plot as a function of a variable where actually this direction is increasing PT, that these extra guys are rather soft. They're low PT particles. And so that's what you would expect if you're looking for and seeing these additional medium-induced radiation. So that's in hot nuclear matter. The question is, what happens if you embed your jet in cold, dense matter by looking at small x at the EIC? Another way you can answer another way you can quantify the parton-medium interaction is by looking at the substructure within the jet. Again, going back to this nice cartoon, I talked about the red. What about these initial splittings? You would imagine that if you have a collision inside the medium, that the initial splitting should be also affected. And so the question is, experimentally, can we see that? The way you do this is you, after finding your jet, you then take it apart. You can groom away these softer particles at large angle and end up with two subjets that are the hardest subjets inside your jet. And then you can make this variable called ZG, which is the ratio of the PT of the second, the second hardest to the sum of the first and second hardest. The distributions in PP and lead-lead look like this here in black and red. And if you look at the ratio as a function of the centrality of the collision, where these are grazing lead-lead collisions and these are central lead-lead collisions, you can see that indeed there is a modification of that first splitting, and we can measure it by looking at the substructure inside the observed jets. And this is a quite sensitive way to look and see what is the effect of the medium on the jet and on the interaction, on the fragmentation of the parton into a jet. So of course, the first way you would look at cold matter before we have an EIC to be able to do that is in p-nucleus collisions. So this is the spectrum of jets that are associated with a photon. So you trigger on a direct photon, you look at the jet from the scattered quark in QCD Compton scattering. In red, you see what we see in proton-proton collisions. Blue shows in proton-lead collisions. And your eye says, yeah, there's not much difference. They are, in fact, the same to within 20%. You can then look at the ZG, the red histograms are what you expect in proton-proton collisions. The black points are what we measure in proton-lead collisions, and your eye says, yeah, no difference there. And here's the jet fragmentation function in red in proton-proton collisions, and in blue in proton-lead collisions. And again, we don't see a difference, but that's at the 20% level. And if you ask, how big should that difference in fact be? 20% is not a very sensitive measurement yet. We really need much more precision than this, both on the measurement of the fragmentation function, but also in the control of the kinematics. If you want to look at the fragmentation, you really need to know what the jet energy was, jet by jet. And with an R equals 0.4 jet, you only know that for the jet core. So this is, I think these are a pair of measurements that we can do much better with jets at the EIC. So where will jets go in the EIC? So this is a simulation for deep inelastic scattering. This is for EP collisions, 20 JeV electrons on 250 JeV protons. We picked the highest root S since the jet cross-section is largest there and it's easiest to simulate. Here you can see the distribution of the jet energy as a function of the jet rapidity, and X covered as a function of the jet rapidity. And you can see, first of all, that we have a nice large range in X, so we can study the evolution in X. And you can also see that we reach rather small X, 10 to the minus 2 and 10 to the minus 3 are here, so we can use these jets to study the propagation in cold matter in EA collisions. Now, what's the kinematic reach here? So what's shown here is the jet cross-section as a function of the jet energy and the jet PT. For different slices in rapidity, this is the yellow is rapidity 0 to 1. The blue is 1 to 2. The green here is just backwards of mid-rapidity, minus 1 to 0. You can see that it falls off pretty quickly. So the jet energies are really not going to be all that large. The low X reach is actually limited by kinematics rather than statistics with the beautiful luminosity that we expect for the EIC. But you get reasonable jet PTs at eta between minus 1 and 0. And that will be in the barrel, the back end of the electron going end of the barrel in most of the full acceptance detectors. And you can reach a few times X of a few times 10 to the minus third still in the barrel. Of course, to study the lowest X region with jets, we really want to focus here and go down as close to 10 to the minus 3 as we can. And those go backwards in the electron going direction. even perhaps towards the electron end cap. Now, we're used to thinking of electron-proton collisions looking like this. When you have a high-energy proton, you expect the quark to be going in the proton direction. That's what your intuition says. Now, of course, if your struck quark has x between 10 to the minus 3 and 10 to the minus 2, then the momentum of the quark for a 250 JeV proton beam is 250 MeV to 2.5 JeV. So the lowest x with 250 MeV is kind of like a fixed target experiment. And so the jet goes somewhat into the electron direction. And that means that we need to make sure that as we design the tracker in the electron going direction, that it can handle some handful of very tightly clustered tracks. How many tracks? Well, if you look here, this is a plot of the number of constituents as a function of the jet PT. And you can see that it goes from 6 or 7 constituents up to over 10 as you get to 20 JeV jet PT. Now, of course, back here at low X, the PT is not very large, but you do get some even as high as 20 JeV, energies as high as 20 JeV. You've heard a lot about gluon saturation. I haven't talked about it. I've been more focused on the interaction of partons with matter. Of course, you can probe the onset of saturation by looking at jet and dijet production as a function of the nucleon size and the X to see whether one can actually identify where the saturation scale is. And I also would point out that the energy loss of the jet will affect the lepton-jet opening angle, and that's something we can measure. Now, we know that there's a very large jet energy loss in hot dense QCD matter. If we get to dense enough QCD matter that's cold at low X, we also expect to see some energy loss. It will be smaller but non-zero, and that's something else that we can look at. Now, of course, if you start looking backwards of mid-rapidity, I've been talking about PT, and of course, once you're away from 90 degrees and a collider, PT is not equal to P. And so let's have a look at the jet momentum rather than the jet PT. This is eta of minus 0.5 to 1 in purple, 1 to 2, minus 1 to minus 2 in green, minus 2 to 3 in red. This is the P, and this is the PT distribution. Of course, you see the kinematic cutoff that you expect once you look in jet momentum. I mean, energy conservation does still work, as it's supposed to. Obviously, as you look further backwards, further towards the electron direction, the jet cross-section plummets. If you look inside these jets and ask what's the mean number of constituents, you can see that in green here for the range of minus 1 to minus 2, you still have a handful of constituents in the jet, so you can still do your jet physics and have a look at the substructure. Once you get backwards of eta of minus 2, you're really looking at single and dihadrons. Now, I mentioned that we could do the jet substructure in EP collisions. This is a plot of the ZG. Expected, this is again for 20 JeV electrons on a 250 JeV proton beam. And you see a very nice measurement. This corresponds to an integrated luminosity of 10 inverse femtobarns. And here's the jet mass distribution. So you can see that these, I'm almost done. You can see that these variables are very accessible. Now, looking at the substructure with this kind of precision will actually allow us to have a look at the, to look under the hood, if you will, of the interactions of the struck quark with the nuclear the nuclear matter, cold, dense nuclear matter right around it. If you look at small x, you can see that we'll have the precision to be able to do that. And by looking at how the splittings are affected by the matter by looking as a function of the nucleus size, we may also gain some new insights into hadronization. Now, what do we know about hadronization? It's something that we all are excited about measuring at the EIC. Of course, when we've measured in the quark-gluon plasma, we've done lots of measurements of the hadronization of the quark-gluon plasma. After all, it's all the hadrons we measure in the final state. Now, this is a plot of the magnitude of the flow, the elliptic flow that comes from the collective boost that the plasma gets. And this is a plot of the flow per quark of different hadrons as a function of the transverse kinetic energy, again, per quark for the different hadrons. And the main thing I want you to see is that they all fall on a universal curve. The implication here is that the stuff that's flowing are the valence quarks, not the hadrons that are already formed as particles. When we first saw this, the conclusion we drew was that the pressure in the quark-gluon plasma builds up very early, and that dressed quarks are actually born of a flowing field. Now, the question actually that I'd like to talk about right now is how does that set of flowing quarks turn into the hadrons that we actually see in our detector? Turns out you can model that extremely well with a simple coalescence of co-moving quarks. And you can think of that as the particles that are seen in a quark after a quark-gluon plasma is formed. All of those things flow as if they're frozen out from this soup of constituent quarks. The question really is a simple coalescence of co-moving quarks in momentum space the right picture for hadronization. We always show each other this nice set of plots from the white paper where, well, what we're going to do is we're going to look at varying the length, if you will, in the nuclear filter in order to see how the hadronization is modified. And you can look at the ratio of different particles, pions, d-mesons that have charm quarks in them, how those are produced in lead, E-lead compared to EP collisions. But I would point out that we also can look at the nucleus-filtered jet constituents, and by looking at the jet substructure, see how does the nuclear filter affect the parton cascade that's about to turn into the hadrons that we see in the final state. So with that, I want to end. My main conclusion is that jets at the EIC will open a new window into QCD. Here's a list of things we can measure, going from PDFs to delta G, saturation effects on jets, and possibly a new way of looking at the hadronization process. The jet PTs are going to be pretty small compared to the LHC. You're talking about maybe 5 to 25 GeV jets before you plummet down the cliff for jets at small x. Of course, these are jet PTs that are pretty similar to what we have been seeing at RIC, and that's not too surprising. It's kind of similar to root S. And I think an important conclusion is that we will need to measure both the neutral and the charged constituents of the jets, which means that if the jets put a requirement on the tracking, hermeticity, efficiency, and granularity, and also on the electromagnetic calorimetry. Thank you.
Thank you very much.
So I think I want to make a comment and see if you agree with it or not. So you showed a lot of things as a function of rapidity, which is essentially a logarithmic scale of the angle.
Right.
But rapidity also correlates very strongly with the x
Right.
of the reaction. So for saturation, we want to go to very low x because that's where it's supposed to happen. But at very low x, in what we normally think of the current fragmentation, there might be one particle, which is not a jet. So on the other hand, that's low x means a very high excitation of the target ion, which means that all the action, if we want to study saturation with jets, all the action is going to be in the forward direction. And that excited baryonic system is fragmenting and maybe with variable PT or so. So we need to understand jets of fragmenting baryons rather than a fragmenting single parton.
You're talking about these guys up here, or perhaps these ones, the higher energy jets that you see forward. I think that's certainly true. I have focused on low X because I want to actually look at the initial parton distributions.
Well, I mean, the low X events, all the particles are going to be going forward, not backward.
Well, not all of them. I mean, the remnant of this very soft strut quark here at small x is not going to all be going forward. The rest of the stuff, yes, the rest of the proton will be. But the remnants of that strut quark are going to be actually going at mid-rapidity and a little bit backwards.
So one comment is that I guess it's going to be very interesting, very important to look at the detector requirements of what you want to do. I think that's absolutely clear from your talk. So when we did these jet measurements at Hera, we extracted the gluon distribution from photon gluon fusion jets using, and actually those turned out to be quite sensitive and even better than the scaling violations in some cases, but really in the medium X region for Hera, which would sort of end up in the low X region here. I think the problem there are two things, right? So one of them is instrumentation, as I said. The second thing is that you're now going down to a very low PT, and there's a big hadronization correction that has to be made in order to try to go back to the parton level, and that is going to be a problem, I think. I think those are the problems that exist at low X. I think for hadronization stuff, I don't see why, particularly for nuclei, I don't see why you can't do that at high X, where you have a slightly higher PT and then better control of the kinematics. I think that may be a better way to look at the hadronization problems.
Well, I agree with that. That's not magic at low X, and you will have higher energy jets there, and that will be much easier to do when you look at more zippy quarks to begin with. I agree with that. We'll have to see how far back we can go. I think some of the hadronization corrections that you make, if you have a fairly large jet, with a R of 1, hopefully those corrections will not be so huge, and one will be able to make them with the higher energy jets and see how they evolve down. What range did you guys do those at Hera?
I think they're mostly in the barrel, but in the rear direction, I think just because of the kinematics, actually they're very spread out. I think. Did you look at the actual configuration of those 2 or 3 particles that go in backward direction?
We didn't yet, but
I think they're they're not really collimated. I think. We have to.
Well, let's see. So this is something that I was thinking about. Now, I think as you go down in PT of the jet, and you get to fewer and fewer. Oops. Whoa. Where am I going here? Then of course it gets more complicated. Here we just use a straight anti-KT algorithm, and we could reconstruct the jets. I think the cleanliness compared to what we're used to in even PP collisions helps a lot.
Okay, one last question.
Yeah, more basic questions. What is the dimension of R? It's some kind of distance?
Yeah, it's, let's see. It's basically an angular distance where you use
it's an angle.
Yeah, you use the rapidity. The R squared is this.
Okay, so it's an angle. Okay, I understand now.
R squared is the sum of the distance in rapidity and the distance in azimuthal angle.
Okay, and then on slide 14, I think it was 14. Yeah, the coherent process. What is that circular ellipse on the right?
Well,
what does that really mean?
what I'm trying to do is to point out that in an incoherent process, when you have when you have a dense medium and you have an interaction of your fragmenting struck quark with multiple gluons, either if it's incoherent, then the interactions are not. One doesn't affect the other one. However, we know that from your papers even, there's a formation time for partons, and if you have multiple collisions before the formation time is over, you actually probably should be adding the amplitudes rather than the squares. And that's something that there isn't a lot of study of for a jet that's evolving inside a dense medium. Not a lot of study yet. People are starting on that.
Okay, let's thank Barbara again. So we'll break for coffee now. We're running a little late, so I suggest to start back at 10:45.
scientific meeting. The first speaker of this session will be Raphael, who will be giving us a talk regarding EIC physics at JLab 6 and 12 GeV.
Well, thank you very much. So first, let me thank you, the organizers, for inviting me and providing me this very nice title. That's what I thought before I started to work on the talk, and then of course started to be more complicated. But to summarize here, what I'm going to try to talk about is what we're starting now at JLab, that is very much what we want to develop further at EIC. And so I have to start with a disclaimer, because the physics program at Jefferson Lab and at the EIC is extremely large, so there is no way I can go through all of it. So I have made some selection, and I skipped a few topics in there, but we heard about many of those topics these few days, so I think it's fine. Interestingly, I found that it's not a one-way road. It's not only the JLab physics program that has been adapted to EIC, but sometimes it also goes back the other way, with some things that were thought for EIC, and we're thinking, oh, maybe we can start to look at this even at Jefferson Lab. So I think it's a very interesting exercise. Anyway. So the first part, and it's the first part of the EIC white paper, is about nucleon structure. And so we've seen this diagram a couple of days ago that tries to summarize all the different functions that can be defined to encode the structure of the nucleon. And clearly for the EIC, now we're starting to we're talking about three-dimensional, so it's TMDs and GPDs. And there are some hope to extend to the Wigner distributions in EIC. But that happens to be also one of the key elements of the Jefferson Lab physics program, to study GPDs and TMDs. So really, this is one of the point where the two physics programs meet the most. So to try to measure those GPDs and TMDs. So let me start with GPDs. So the generalized Parton distributions, they are three-dimensional, X, Psi, and T, and usually we're thinking more because they give you information about the transverse distance and the longitudinal momentum, but and that's with the 3D we think, but at the start, those are the 3 dimensions. And those are accessible through a list of processes. DVCS, which is shown here, is the most common and the easiest, but there are a bunch of others, and I'll talk a little bit about deep virtual meson production, but and there are much more. So the DVCS is the simplest one. It's the electroproduction of a single real photon, while keeping the target intact. So that has been studied, and we had a couple of talks on that, so I'm not going to go too much in depth. One important point to keep in mind is that when you measure this, you're actually not measuring the GPD, but you're measuring Compton form factors. So which are, the GPDs are here, so you get integrals or specific values of the GPDs out only. And when you're trying to measuring that, you run into another problem that happened to be a blessing, is that there is another process that produces photons that is in principle much less interesting, is when the photon is produced just by your lepton beam. So this is, in principle, not interesting, except for the fact that the two processes interfere together, and that creates a bunch of asymmetries and spin asymmetries of the beam, spin asymmetries of the target, which you can do longitudinal, you can do transverse. If you have the chance to have access to different charge of beam, you can also do charge asymmetries if you have like electron and positron beam. And so all those asymmetries give an access that is rather unique and allow to extract the content form factors with a reasonable number of measurements. In principle, there are 4 GPDs that you can measure in the proton. That leads to 4 complex content form factors, so 8 unknowns for every point in the phase space. And so you need quite a bit of observables to figure out those 8 unknowns. This has only been achieved by Hermes fully, to give like a full set of observables where you can extract completely the information. But JLab has provided a lot of data on a very large phase space as well. While not completely over everything, I quote a selection of them because there are way too many to quote all of them. And here I show a sample because the number of points published in those papers is overwhelming, and I could not fit them in one slide. What's interesting with all those points, and you can see, is that you can see a bunch of fits, and that's how the GPD business works, is that you input a ton of data and you try to fit those data to extract your GPDs. And that, in principle, allows you to extract the GPD and make the tomography of the nucleon. One thing I'm not going to talk more about, much more about here, is also the meson production that already exists. There are already some data from JLab. Those are not included at that point in those fits, so I'm not going to talk too much about it, but it's also a number of papers on that, and they're linked to GPDs. So a little bit more on the fit. So here you see the fit of some of those data I quoted just before. It's actually, those fits are exclusively JLab data, from JLab data. And here you have the extraction of the imaginary part of H. And you can see, for example, that you get a stronger slope that flattens as you go to smaller values of Xi, or larger values of Xi. And what it means is that since this is, if you want to obtain this tomography, you need to do a Fourier transform. So if you have something flatter, it means that the object is getting smaller. And here is a fit. Of course, most of the data we have in JLab is in this yellow and green part, and all the rest is extrapolation. But at this point, we can already see this behavior. If you multiply the number of observables you make, you can, of course, continue looking at that, but also for like the axial charge. And that's if you get the H tilde GPD in particular. And if you can measure the E GPD, so that if you have even more observables, then you can link this also to the G-sum rule, which give you the orbital angular momentum. So just to give kind of a situation at that point, just with the 6GeV data, we have a reasonably good H. The actual charge, we have a few points, but it's not to the point where we can really extract something as meaningful. And the E is mostly unknown. So of course, all of this is about charge, actual charge, and I didn't talk much about gluons. And EIC is clearly the machine for gluons. So question is, can we do something about that in JLab? So the way to access the gluon GPDs is to use vector meson production. So here I give a SS bar example. And the idea is, if you do that, if you produce a vector meson that has quarks that are heavy enough, then quark exchange is suppressed, and the main diagrams are through gluon exchange. And in that situation, you are really probing the gluon structure. So EIC has plans to do that with JPSI, because this is extremely massive, and in that case, you have very nice in easy perturbation theory treatment of that. Of course, at JLab, this is going to be a little bit complicated, but there have been proposals that are approved and that run actually doing that with the phi meson. And so it's only strange quarks, so you don't have this cleanliness of the supermassive, but it's a very nice experiment to start looking at this and seeing if we can really do that. Another thing is the neutron GPDs, and we had a talk by my colleague Carlos yesterday about that in details. There are two goals to measure neutron GPDs. One is to do a flavor decomposition. We've seen just in the previous talk those nice PDF where we have the U and the D and so on. At this point for GPDs there is no such thing. We just have to sum all quarks together. But if you start measuring neutrons, then you can start to differentiate U versus D and things like that. There is another interesting thing is if you look at the equations, you see that there are some form factors that show up in there because of the beta-Hitler contributions. And obviously, the charge of the neutron being 0, you have some of those form factors are pretty small, and that suppresses the contribution of H and make the contribution of E relatively larger. So there is also some hope by making neutron DVCS measurements to get more information about that, which, as I mentioned a little bit before, is very important for the GSOM rule. So there has been all A measurements quite a bit, some old one published and a new one that was reported yesterday that is in the process of being published. And there is also 12 GeV perspective, I mean, class 12 perspectives here. So there is a neutron detector that was built in Orsay specifically for this kind of measurements in class 12. A few weeks ago we submitted with Mohammad a new experiment to also do that using the tagging method. I'll go more in detail about tagging later, but so there is a strong effort to push for this, and this is really interesting. Let me go now to TMDs. So TMDs, it's more or less the same kind of business. To summarize, you get a very complicated expression for your cross-section, and what you get in there is that you have a bunch of terms that are based on some angular dependence that are different for all of them. Some of them are just the angles of your hadrons. Some of them are combination of the angles of the hadrons and the spins. So if you take a lot of data, you should be on a lot of different situations. You should be able to figure out a number of elements in this equation. And in the 6GeV era, that has also been JLab has also been a provider of a lot of data. Same situations and for GPDs. Here I'm really just showing a small extract of those data because there is way too much. But what I can point out here is that these measurements have been done for many different hadrons. We have pions, we have kaons, we have neutral pion. We have also very different observables, rather simple sin phi just with beam polarized, but you have also double spin asymmetries, and some of the more complex things with the spin and the hadron, like the Collins asymmetry here. And to be noted that there is a large part of this program that is being provided by a polarized helium-3 target, which we had also a presentation about that a couple of days ago. Basically, the polarized helium-3 gives you a neutron target, and that's also a key element of the EIC physics, because I mean, everyone has seen this 8 form of the accelerator, and the reason for that is you want those light nuclei to be highly polarized to do those kind of experiments at EIC as well. In the feed business, so it's a little less advanced than what's going on with GPDs. However, it's now starting. I quoted a couple of papers from this year and last year. Those include quite a bit more data than in the GPD case. In the GPD case, we're really just fitting DVCS. But in that case, it includes some lepton-lepton interaction, lepton-hadron, proton-proton, because you want to fit at the same time fragmentation functions and a lot of different functions. And here you see an example of such a fit. And you can see that we start for some of the functions to see some behavior emerging. One thing to note is that these things do not include JLab data. They're mostly based on Hermes and Compass. One of the main reasons is because the Q-square is too low, and the theory people do not trust too much those kind of Q-square to put in their global fits. But this should evolve with the 12GV, both because there is progress on the theory side to include correction terms to use those data, and also because the 12GV will go up in Q-square and provide some data that is safer on the theory side. So let me summarize this first part. Even though, so the 3D nucleon structure, clearly there is a big separation in X, because JLab is really the high X machine, and the EIC will be the low X machine. However, there is still very, very similar problems. And for example, the question of which observables, how many observables do you need to actually be able to extract your GPDs and your TMDs? This doesn't really depend on X. And these kind of questions of phenomenologies that we're working on with the real data today at JLab are really questions that are completely relevant to EIC in the future. The question of vector meson production is also one that is very relevant, and we are struggling right now in JLab on trying to connect this with GPDs, but it is still of high importance. So EIC will really extend these things and in a safe environment in terms of theory, but also in a much lower X. So some of those high X questions that are addressed, and we heard also about that in the past 2 days, will not be addressed at EIC and need to be done really at JLab. So the second part of my talk, and is also the second part of the EIC program, is because it's an electron-ion collider, so there has to be some nuclei in there. And to me, from my point of view, really the question is how do we go from a nucleus that, I mean, everyone learns in school is made of protons and neutrons, and why do we study it in terms of quarks and gluons? And the reason is actually there are a lot of tricks when you go from one to the other, and you cannot just do a sum of nucleons. That doesn't work. And we heard a heated debate yesterday about how to do those treatments. I'm not going to go too much more into that, because in the similar manner we have this low X, high X separation between EIC and JLab. So while JLab is really the place to look at the EMC effect, EIC will probably not say much about that, even though there are few ideas, but it will mostly look at the shadowing. But there are still some common interest, and the first is actually linked to what we were discussing before. It's GPDs, and the fact that we can measure GPDs of nuclei, and that's a very interesting exercise for several reasons. The first reason is if you have a nuclei, now you're not stuck with only spin half. You can actually have different spins. And in particular, you can go to spin 0. That's what I'm going to talk mostly about. And in that case, you have less GPDs. And so it's 2 GPDs, but actually only half of those GPDs intervene in DVCS. So you're left with 1 GPD, and all this fitting business that I discussed before disappears, because now you just have 1 GPD to extract. However, so that's in the case where you really do a real DVCS where the nucleus remains intact. But there is a second situation, which is the incoherent, where you do a DVCS on only 1 nucleon inside the nucleus. And that gives you an access to how nucleons are modified in the nucleus. So these are really 2 different ideas. So let me start with the coherent DVCS. So this was measured first in Hermes, but in a way that was not very satisfactory because they could not ensure the real exclusivity of the process, and that led into the development of this detector for class to allow to detect the slow helium-4 at the end of the reaction to make sure that the process was fully exclusive. And this experiment worked very well. You can see the results here. And the asymmetries are between 30 and 40%, so they are very strong. They're even stronger than on the proton, which was expected by theory. But that shows that even if this experiment got only a few points, because by opposition to GPDs on the proton, here I'm showing you all the worldwide points we have, and that's not so much, as you can see. What we have is that there is a single GPD, as I mentioned, and you can see here the equation you have to use to extract this GPD, this compton form factor, the 2 compton form factor you get from the GPD, and the alpha terms are shown here in this figure. And what I want just to point out is that you can see that actually there are orders of magnitude difference between those terms. So the fit is not completely straightforward, but at the end you have only 2 unknowns. And if you are trying to fit a sinusoidal signal with 2 unknowns, you get a fit that works, and here are the results of the fit. So error bars at this point are pretty big, but this is really the demonstration that it works and that you get the results you're expecting without all those model uncertainties of doing complicated fits. So for the incoherent one, so again, we made the measurement with the same setup. So in that case, we're looking at protons bound in helium target. And what we found, I'm just jumping to, so here are the asymmetries, but what we really look at is here is the ratio of those asymmetries compared to the free proton one. And as you can see, some predictions had an increase. They were predicting something bigger than 1. Other predictions were saying below 1, but by a tiny amount. And what we measured actually was very surprising, because the points here are like 30 to 40% below. So we have a very strong suppression of the beam spin asymmetry when we measure it on a nuclear target. So this is very recent result. It's actually been approved in PRL very recently, so it will show up there pretty soon. So the question now is, what is this? Is this linked to the EMC effect? Is it a new facet of the EMC effect or something like that? Or is it due to other effects in the final state, because you can have reinteractions and things like that? And so the idea here to solve this question is to make tagged measurements. And so what are tagged reactions? So if you are doing an incoherent process on a nuclei, what you want to do, what we do if we call it tagged, is that we actually start to measure the remnants of the nuclei. So you're not only interested anymore in this part that took part directly in your interaction, but you want to know what's left of the nuclei as well. Preferably if it's an A-1 recoil, because in that case it's very simple, you have everything. And in that case, what it gives you is, because now you have your nuclei in some kind of two-body situation, you hit one nucleon and you have all the rest in the other direction, it means that you can reconstruct the kinematic of the nucleon you were hitting. And very interestingly, from the kinematic of your spectator, you can actually calculate the virtuality of the nucleon you hit. So that's a very interesting point. Only issue is that here you can see different contributions, and you see that they are not flat at all, and that's due to final state interactions that intervene quite a bit. And so to do those measurements in a relatively safe place, we want to do it rather backward, because here, while there is an effect, it's not one, at least it's flat, so it's relatively easy to correct. And so tagging is going to be very important at EIC, because obviously, well, not necessarily obviously, but in the EIC situation, because of the collider kinematic, it's much easier to make. But it's something that has been done already, actually by the bonus experiment in class at 6GV. They have a bunch of results, but I like to show this one because I think it's the most illustrative of the point. And what you can see here is that you have in white the deuterium spectrum in W, where you see the quasi-elastic peak, and then first resonance, and then some kind of continuum where other resonance should be. But if you use the tagging method, you have the black point, and now you see that your elastic peak, your quasi-elastic peak is very much sharper, as well as the first resonance is much sharper, and you start to see all the other resonances. And that's really the demonstration that this tagging method works very nicely, and really allows you to make an effective neutron target. And if you push that to nuclear targets, that's what we did here for this for proposal. So that's 12 GeV physics. Here the idea is that you can really look at an equivalent of the EMC effect and say if it depends or not on the recoil momentum, which is a way to just tag the virtuality of the nucleon. So this is a way to really test directly if the EMC effect can be linked or not to the virtuality of the nucleon. I'll go quick on that. Just to summarize all the different tagging measurements that are proposed right now at JLab 12 GeV to show that it's actually a very hot topic. There are three experiments that are on the line. Bonus 12, the first one, is really a prolongation of bonus I presented before. And this is on the schedule and supposed to start running January 2020, so pretty soon. And so that's looking at neutron structure and neutron GPDs I have mentioned before. Then there is the alert detector, which is here, which has a slightly different technologies in there using drift chambers. And the main idea is that if you want to move to heavier nuclei like helium, you need to be able to differentiate the different isotopes. So that's why we designed this detector. And there is also the TDIS experiment, which want to look at pion structure. And in that case, they want to be able to take very high luminosity. So they have highly segmented time projection chamber to do that. So this is a very active topic right now in JLab. I'll finish with hadronization, and I'm almost out of time, so I'll go quite quickly because the talk before talked about that quite in depth. Just to say that hadronization is also something that is going on both at JLab right now and will be going on at EIC. And yeah, maybe the one point that I want to make is that most of those studies in the past have been done relatively naively, but with the development of TMDs I mentioned before, I think it's a good time for JLab to modernize our tools in preparation of EIC. And there are some predictions already for those kind of measurements. And very interestingly, if you measure hadronization and nuclear TMDs, one of the things you obtain from that is the transport coefficient, Q hat. And this Q hat is actually linked to the gluon distribution at very small x. And that's more or less, you can link that directly to saturation. So saturation is the point where you get at x that is so small that the recombination diagrams, the density becomes very high, and the recombination diagram starts to compete with splitting diagrams, and so you're not in the normal evolution anymore. And so in this place, it's actually what you're really probing with this transport coefficient. So the possibility to access transport coefficient at the JLab is already a way to have a first look into what is the saturation scale. So after all of that, let me conclude. So first, let me apologize for the electroweak physics. I did not include that in the talk, but there are plenty going on at JLab. We heard about Muller experiment and so on at JLab, and there is also some plans at EIC. But so we have seen hopefully that the EIC physics program is in many ways a natural prolongation of the JLab program and the 6GeV and 12GeV. And even if the X range is going to go down, many of the tools that we're going to use are the same, and many of the topics we can start to explore already. And the three main topics of the EIC are really also three very important topics of the JLab physics. So I should also remind that the EIC physics program is still very much in its construction phase, and there are actually many topics we've seen and heard about during the past 3 days that I think should have their place also in EIC, even though they have not been developed yet. Thank you.
Thank you very much, Raphael. Any questions for Raphael? Rick?
Thank you. So this, shall we say, this idea that EIC is primarily an low X machine is kind of baked into the way we discuss EIC, and it has to do with the way it started, and also the fact that Hera never really measured well at high X. But there's no real reason why EIC cannot measure up to X of 0.7 or even 0.8. And we are thinking about programs that do that. So those of you who are primarily interested in high X shouldn't think that this is not something that I should be interested in. An EMC effect and things like that will certainly be measured here. And EIC will not only extend the kinematic region to low X, but also at high X into high Q squared. So I think you should. I think we really should think about not discussing it in this way anymore.
So I kind of agree with you partially. I agree in the fact that IX will be accessible, and not only because we can detect electrons and stuff like that in this in the right range, but also because if you start to go at the production of heavy quarks or heavy anything, any heavy particles, you're actually shifting quite a bit the X range you're probing. So that's completely right. Now, at the same time, I would not be too optimistic into resolving some question. I think if we cannot in JLab with the very high luminosities that we get in all C, for example, if we cannot resolve some of the questions with the EMC effect, I don't see how EIC would be the solution to that. So I agree there is quite a lot to do at IX, at EIC, but I still have the feeling that it's quite different than what we are doing at JLab at IX right now.
Ian?
Hey, Raphael, I just want to kind of make a comment about this virtuality. So we already know that that the electromagnetic coupling of the photon to a virtual pion is very, very different to an on-shell pion. That's been measured here at JLab. You have to extrapolate to the pole. So I think all you're going to show here is that the virtuality of an off-shell nucleon, or that an off-shell nucleon is very different from an on-shell nucleon. And that's not the same thing as an explanation for the EMC effect.
Yeah, I completely agree with you, and it's actually, I think it's actually the whole point of this figure, because there are some plans to measure, we heard about looking at short-range correlated pairs, for example, and my whole point here is that you actually, so short-range correlated pairs are going to be somewhere here or slightly farther. And my whole point is that if you just get one point, it's very difficult to say anything. What you really want to look at is the slope. Because if we get something flat in another place, and it's actually, then it means that it's not really depending on virtuality, but it's just because, oh, it's off-shell and you have some correction. So I think those measurements will be able to make the difference between the scenario you're giving and really a link with the EMC effect, because you're covering quite a bit of phase space, and now you can see if there is an evolution when you go from slightly off-shell to much more off-shell. And also here, I mean, it's shown linear, but it could also show up to be non-linear, to be flat at the start and drop at some point, or having any kind of shape. So
with the pion example, we already know there's an evolution with off-shell.
Yeah. Well, it depends what model you're looking at, but some model directly linked those two things. So this is a test of that.
Okay, any more questions for Raphael? Okay, if not, let's thank our speaker again.
Quickly, while our speaker's getting set up, thank you for coming to the colloquium part of today's user group meeting. So we invited Kazu Akiyama to come here to tell us about the image that he and his collaboration have made of this black hole, which is quite a dramatic event to see. Kazu is a Jansky Fellow from the National Radio Astronomy Observatory, and which is in Charlottesville, but he's at MIT working in the, I'm sorry, I've forgotten the name of the laboratory.
Haystack.
Yes, the Haystack Observatory. And so the talk is about, yes, the imaging of the black hole, but so both about the black hole and I think hopefully a bit about imaging, because we've been hearing a lot about how one is trying to take projections, slices through data, and expand upon a 3D image, which is very much the challenge that they faced in making the image of the black hole. So I think there's some connection here, although some big differences also. So please welcome the speaker.
All right, so can you hear me? Okay, great. So thank you very much for inviting me to JLab. It's quite exciting. This is the first time for myself to visit any accelerator facility in this planet, so I'm quite excited. So I think you guys know what I will present. I'm still feeling weird because every time I will give this talk, everyone knows the results. So of course I will talk about this one. So this one is the first ever picture of black hole taken by the Event Horizon Telescope. That is a planet-wide, planet-sized radio telescope, which have ultimately high angular resolution. So this image is actually one of the highest angular resolution images taken ever in the astronomy. And that is finally reaching at the ultra compact object, which is a black hole. So my talk is focusing on imaging process, actually how we made this image, I mean, before observation and after observations. And I also like to introduce what we have learned from this image. And I think the imaging techniques or imaging approach could be really different depending on the properties of data or underlying physics. But I think some parts should be very similar to the imaging of the actually accelerators data. So hopefully I can provide useful some information based on our experience. So because I think you guys know this image, so let me just start from the highlight of the results. So I hope that you can see this, but so our target is M87. So that has a different name of Debago A because it's the brightest source near the Debago in the radio wavelengths. So if you're zooming up this, this is nice. If you're zooming at this area, actually you can see a many number of galaxies that is so-called the Debago cluster. And at the center of the Debago cluster, there is a giant elliptical galaxy, so-called M87. So you can see that narrow straight line. This is a relativistic outflow coming from the central supermassive black hole. And this is very bright in radio wavelengths because of synchrotron emission. And the synchrotron emission becomes more transparent at going to the higher frequency. And finally, we're reaching at the origin of the jet, which is a supermassive black hole. This is actually our results. So we have published 6 papers simultaneously with 6 international press conference held on April 10th. Let me just summarize this because the paper is completely open access. So if you want, you can read it. The first paper is just summary of all 6 papers outlining what are the results coming from first EHT observation of M87. And then the second paper is describing what is the EHT. So if you have interest in technology or instrument of the EHT, this is the place. And then the paper 3 is actual starting point of our observations, describing how M87 data are obtained and how data are processed and how data are calibrated. And this already showing some interesting results, just purely from the data domain. I will briefly introduce later. And the paper 4 is actually one of the key components of these 6 papers. This is providing the first ever picture of a black hole. So my role in the Event Horizon Telescope collaboration is leading the entire imaging team, which is consisting of like 70 people. And also I'm the primary developer of one of 3 imaging software packages that actually created the first ever picture of black hole. So that's why I'm leading this paper as one of the corresponding author. We had a fantastic colleagues like Katie Bowman, she's now really famous, and then Andrew Shao, Jose Luis Gomez, and Michael Johnson, who is co-leading imaging working with me. The paper 5 is more like a theory paper. They did a fantastic job. They just run a supercomputer simulation of the general relativistic magnetic hydrodynamics of the gas near the black hole. And they created like a 6 petabyte of data and just directly fit to the observing data to learn what is the physical origin of that asymmetric ring emission. And then the paper 6 is extracting the modeling that ring emission and deriving some physical parameters. So one of our main product from these 6 papers is the mass of the black hole. It turns out that M87 a supermassive black hole has a 6.5 billion solar masses. It's really massive. And this is indeed actually massive as a black hole. And then also what I want to emphasize is this paper is also massive. So Astrophysical Journal letter is like a physical review letter. It usually have like 5 or 6 pages. But it's actually break the limit. Our paper break the limit. For instance, even for the summary paper, it's like a 20 pages. And most of paper actually have like more than 30 pages. Actually, our imaging paper is like 50 pages. So it's probably difficult to explain everything within 1 hour. But hopefully, I can present a rough overview of the EHT results. Because I'm heavily involved in this imaging process, so my talk will, modestly focusing on the imaging process. So what we reported on is a detection of the shadow of the black hole. And that is actually seen in our image. Let me explain actually what is the shadow of the black hole. I think here everyone has a physics background. So I think most of you actually know what is a black hole. The black hole is one of the densest objects in this universe. It's very, very compact. And that compactness creates a really strong gravitational field that creates a weird surface so-called event horizon. So that is the surface of no escape of photons, or that is the surface of no escape of any other information. So by definition, we cannot see the event horizon. That's the definition of the event horizon. However, if the Einstein's general relativity is correct, then the black hole will cast a shadow to the distant observers. That is an apparent horizon of the black hole. So, by the way, the size of the black hole is characterized by the Schwarzschild radii, which is a 2gm over c squared. So it's just roughly proportional. It's just solely proportional to the mass of the black hole. So here, what I'm showing is the light trajectory from the distant observer to the vicinity of the black hole. So what you can see is if the impact parameter of the photon trajectory is just large enough, then it's just slightly bended by the strong gravitational field of the black hole. But if you're getting closer, then the degree of the bending is getting more severe, and you can realize that there is some threshold where inside all of the photon trajectory will cross the event horizon. So that boundary is so-called the photon sphere, and it's characterized by a stable or unstable photon orbit near the black hole. So if you flip the photon propagation from the vicinity of the black hole to the distant observers, then you can understand that the dark nature of the event horizon actually will cast a shadow to the distant observer. So that is the shadow of the black hole. Its diameter is a 5.2 Schwarzschild radii for non-rotating black hole. It's strictly its square root of 27. This even actually doesn't change a lot, even for a spinning black hole. So black hole have 3 parameters: mass and spin and charge. But for cosmic black hole, we don't have to think about the charge because the universe is just neutral. So even this doesn't change even if the black hole is spinning. The minimum size of the shadow is given for maximally spinning black hole seen from the axis of the spin. So it's a polar view of a black hole spin. That gives a size of 4.84 Schwarzschild radii. So regardless of the spin or regardless of the viewing angle of the spin, the size of the black hole, apparent size of the shadow is 5 Schwarzschild radii plus minus 4%. So if we want to take a picture of a black hole, actually what we need is we need to resolve this 5 Schwarzschild radii. So the angular size of the black hole is really, really important. And fortunately, human beings have 2 excellent targets so far where probably we can reach. The first one is the Sagittarius A star in the direction of Sagittarius concentration. That is the galactic center of our galaxies. That have 4 million solar masses of black hole. And the distance is in astronomical unit 8 kiloparsec. It's a 24 kilolight years, I think. That give angular size of the 10 microarcsecond. I will explain what is the microarcsecond later, but the 10 microarcsecond for 1 Schwarzschild radii. And another excellent target is, M87. So it has 1,000 times heavier black hole, and that is also has a roughly 1,000 times farther distance. So just everything is just canceled out, and that also provides a very similar angular size of black hole, which is the 7.6 microarcsecond. So as I said, the shadow diameter is 5 Schwarzschild radii. So that is a 50 microarcsecond for Sagittarius star, and then 35 to 40 microarcsecond for M87. So if we have the angular resolution of just a few tens of microarcsecond, we can resolve the shadow of the black hole. This is actually what we did with the EHT. So let me explain the unit of angular size in astronomy. So I'm not sure this is popular in the US, but this is the typical protractor in Japan. And I think one ticks is corresponding to the 1 degree, which is the most popular angular size, angular unit. So if you divide 1 degree by 60, you will get arc minute. And let me show some example of the stellar object have arc minute scales. That is a moon. So the moon has an angular size of 0.5 degree, and that is corresponding to 30 arc minutes. So this is a typical scale of the moon. If you divide by 60, you will get arc second. This is a typical angular resolution of Hubble telescope, for instance. And if you divide it by 1,000 again, you will get a milli arc second. Then finally, you will reach at the micro arc second by farther divided by 1,000. So what is the like a shadow size? It's 40 to 50 microarcsecond for Sagittarius star and M87. That is corresponding to the orange on the moon. So if you take a picture of the orange from the ground, you can actually see a black hole. So this is, of course, not feasible so far before the Event Horizon Telescope. So the EHT is gathering the many radio telescope observing at 1.3 millimeter. Actually, almost all of the telescope that observing that wavelengths in this planet. And they actually observe the target so simultaneously, and that provide a virtual planet-sized telescope. So we have, so for this particular results, we have 8 telescopes at the 6 geographic site. And let me show this one. It's actually probably much easier to see it. So you can see that our actually 6 geographic site actually can create a literally planet-sized telescope. So that actually provides angular size of 20 microarcsecond for angular resolutions. That is corresponding to the size of, I think, a ping-pong ball or golf ball on the planet, or the angular resolution that can see your smartphone in Paris from the New York, something like that. And that is enough to resolve the shadow of the Sagittarius star, hopefully, and we already know that we resolved the shadow of the M87. So that was made by the Event Horizon Telescope collaboration. This is, again, the literally planet-wide collaboration. So we have more than 200 scientists coming from the 59 institutions from 18 countries, which is spread in many regions. 1/3 of scientists is coming from the United States, and we have collaborators in Canada and also South America like Chile. And we also have fantastic colleagues in Europe and East Asia, where I'm originally coming from. And also we have some colleagues in Africa. So it's a really literally planet-wide international collaborations. So, so this is actually the radio telescope that we use for the EHT. So for instance, in the United States, we have a sub-millimeter telescope in Arizona. It's on the Mount Granham. And also another telescope is a James Clerk Maxwell telescope that is operated by East Asian Observatory in Mauna Kea on the Big Island in Hawaii. And also this is a large millimeter telescope which has a 50-meter dish, which is, oh, by the way, so this is 10-meter dish and a 50-meter dish. So it's a large parabolic antenna, basically. In Mexico, this is a telescope in Spain, and 30-meter dish. This is a 12-meter telescope in Chile, which is a European pathfinder for the ALMA. And ALMA is one of the highest sensitivity telescope at 1.3 millimeters so far, consisting of like a 66 radio antennas, which is a very, very massive array. We also have a telescope on the South Pole in Antarctica, South Pole telescope, and also 7-millimeter array, which is located next to the JCMT. So basically, what do we? So the timing that we got data for this particular black hole image is 2017 April. So it actually took 2 years to publish data to confirm everything. And then deduce data carefully. But anyway, at the timing of observations, so the 200 members just split to the globe, and each group actually operate the telescope and gathering data. So let me just explain a rough process from the observation to the final image. So we received a signal at each telescopes. And then signal is transformed to digitalized signal and recorded at hard disk. And these hard disks are physically shipped to the MIT Haystack Observatory and Max Planck in Bonn, and we process the data and create a virtual telescope in a supercomputer. But that virtual telescope still have some issues of focus, so we actually calibrated data so that the virtual mirror's focus is in the correct position. Then we made image reconstructions. And then, we get this kind of black hole images. So this is the rough procedure of the our data flow from observers to the observation to the images. So let me show in a different aspect, in terms of data size. So our final image is like a kilobyte data size. But because the M87 signal is really big, it's like 10,000 times smaller than the typical noise level of the receiver system of the telescope. So that means, and then we actually need to detect this signal within like a 10 seconds to calibrate the data. So that requires a lot of photons to get a robust detection of signals within very short time scales. That needs basically a wideband recording in terms of the radio bandwidth. And that is corresponding to the wide data recording in terms of data rate. So to actually make this image, actually we collected in total like a 5 petabyte of data. So for instance, this is the photo just in front of the correlators actually make the supercomputer making a virtual telescope from the raw signal data. So what I have here is a disk module of the EHT. So one module, it has like a 8 hard disk with 8 terabytes. So it's like in total 64 terabyte. That is corresponding to the like 2.5 hour observing time at each station. But we have 8 telescopes, and also we usually have an observing session for a week. So in total, we have 92 modules. This is corresponding to like a 5 petabyte data. Then we correlate data and calibrate data and averaging data and then make images. So to get a kilobyte image, we actually reduce data by 12 order of magnitude, which is literally a theta reductions. So after the correlations, making the virtual telescope, we calibrated data. So the EHT's policy is in every process, we have a parallel processing. So even for correlations, we have a parallel correlations, independent correlation at MIT Haystack Observatory and Max Planck in Bonn. And then also the post-processing data calibration is also split to the 3 independent pipelines developed independently. And to make sure that every output of the data processing is consistent with each other with a different method, that is enhancing our quality. Actually, we usually have like an external panel review after each step of the data reduction. And if there are some issues, we usually actually doing again. So actually, from correlation to this process, we actually redo calibration for 7 times with a lot of issues. This is actually how EHT process the data. So after the processing, we got a kind of data ready for imaging. So let me explain actually what are the data. So here, this is actually what we want to get, the image of a black hole. But EHT is the instrument so-called the radio interferometer, which is a very weird instrument. We cannot take a picture directly like optical telescope or the smartphone's camera. So what we are doing is we're measuring data on a Fourier domain. So for instance, this is a Fourier transformation of this image, and it's just taking magnitude of the Fourier component. And here, this is the R seen from the M87. So what you can see is with Earth rotation, you can see many EHT stations here. And you can see the lines connecting 2 antennas. So that is so-called baseline. And what EHT observed is a Fourier component at the spatial frequency corresponding to the projected baseline length seen from your target source. So first of all, Earth rotation will help a lot. So with the Earth rotation, the projected baseline length, baseline is actually rotating with Earth rotations. And also if you have many stations, you can get many combination of baselines. So you can sample many spatial frequencies. So as a result, for instance, EHT can sample this kind of Fourier component. So this is still very, very sparse, but it's very good for this sort of images. For instance, you can see the EHT coverage is covering some null regions. So this is creating from the shadow-like features. If you're familiar with Fourier component of the ring-like emission, that is actually Bessel function, and this is corresponding to the first null and the second null of the Bessel function. And you can also see that if the ring have a asymmetry like this, you can see that null is not in every direction, but it's actually have asymmetry. There's no null in this direction. And in EHT coverage is enough to capture this kind of asymmetry of the ring-like emission. So that's why we expect that if M87 has a shadow, probably we should be able to make images or grab that signature. So let me show this with the image processing. So at the beginning of EHT observation, M87 can be only seen from the Europe and Chile. So we have only just one baseline and one spatial frequency measurement. So the data is of course very poor. There's no ring-like emission. But as observations start with Earth rotation, we have a lot of spatial coverage, frequency coverages. Then once we have like isotropic coverage, in spatial frequency domain, then we start to see a link-like emission. Then you can see that image is converging into the final image that press release on April 10th. So that is actually how the radio interferometer works. So in mathematically, that is ideally just a simple linear problem. So what we want to solve is the brightness at each pixel, and an interferometer works as like a Fourier matrix, and we got a fractional Fourier component, and plus thermal noise. This is a very ideal case. The number of pixels of images is usually much higher, much larger than the number of data sets. So this is a very simple equation, but it's idempotent and underdetermined. So there are a number of infinite number of possible images that can perfectly explain your observing data. So imaging in a single sentence is picking up a reasonable solution based on some prior assumption for the image. So this is actually what imaging is doing for radio interferometry. And I would like to mention that, so this case is really similar to the mathematical equation of MRI or CT for medical imaging. But for the radio interferometry, we also have some systematic error component even after the calibration on, for instance, the magnitude and also the both phase of the component. So we also need to handle this kind of systematic errors as well as just Fourier inverse problem. So let me show what are the M87 data. So this is the magnitude of Fourier component as a function of baseline length. I will not explain the details about this data, but what you can see is, so here the different colors showing different observing day. So we observe M87 for 4 days, April 5, 6, 10, 11, so 4 days within a week. And then what you can see here is, regardless of observing day, the data points is really similar, have a similar trend. So this means the basic structure of M87 actually doesn't change within 1 week. And then also what we can see here is, so this, as you can see on the previous slide, the spatial frequency coverage is a 2-dimensional. And this is just a linear plot. But still you can see just one single line of the tendencies. So this means that the structure of M87 is somewhat symmetric, radial symmetric. And let me pick up just the data from the final day. Now the different colors showing a different baseline, different combination of telescopes. So here I just put the dashed lines here. So this is the Fourier transform of the very thin link. And surprisingly, it's explained most of the signature seen in data. So actually my first impression of this data is, oh, this is a very beautiful link. Because radio astronomer actually can do a Fourier transformation in our head. So one other thing is actually we need to be careful that because this dashed line cannot perfectly explain everything, and there's some deviation here, and then also here you can see that in some baseline there is no null. So actually this is an east-west baseline, and this is north-west baseline. So this is also indicating that this structure cannot be explained by just simple asymmetric link. So this needs some asymmetry in the structure. So far we just focusing on magnitude of Fourier component, but we can also take the information of the phase of the Fourier component. So here I'm showing is a closure phase. It's a phase of the bispectrum. It's a triple product of the Fourier component and just taking phase. So this is a very robust component free from any calibration errors. So it's just purely reflecting the M87 structure. So for instance, alpha LMT SMT triangle is here, very narrow triangle. And then this closure phase means at the sum of the phase of the Fourier component between alpha alpha LMT, LMT SMT, SMT alpha. This is a tiny triangle, so it doesn't have a really good angular resolution. But still you can see some structure here. And if the closure phase is 0, that means that your image, your source has a symmetric structure. But you can see that the values are clearly non-zero. So that means actually the structure has some sort of asymmetry. And then also a fantastic thing result, which is not emphasized in the press conference, is that if you look at a larger triangle, something like this, you clearly start to see some tendency. I mean, there is no systematic offset in the first 2 days and the latter 2 days. So this means that there's a basic structure tracked by low spatial frequencies is almost same. But if you go to the finer scales, actually structure is changing day by day, which is quite exciting results we haven't seen before. So now then we move on the imaging process. So as I said, the imaging is a UTPOS problem for radio interferometry. Then for the EHT, there are actually 3 major challenges. The first one is our spatial frequency coverage is very poor, very sparse. So in general, radio interferometry has a UTPOSness generally, but the degree of UTPOSness is very severe for the EHT because it's a very sparse coverage array currently. And then also still we have some residual calibration errors. So the problem is more complicated than medical imaging like MRI or CT. And another thing is, basically we are picking up one reasonable solution from the infinite number of possible images. But still, actually, we don't have any information of any horizon scale picture of a black hole because this is the first time. And in the history of radio astronomy, we usually use just single technique validated in the community for a long time, just with a single parameter, optimal parameter set. And just make one single image and publish in a paper. So for instance, this is a protoplanetary disk image obtained with ALMA. Or I think if you go to the hospital for some sick, maybe sometimes you will take an MRI. But we usually see just one single image because medical imaging people usually apply one decent method and then reconstruct image and showing one image, one reconstruction to the patient. I don't think that actually this is a bad idea, but this is probably not a good way for our imaging, our actually scientific objective. We actually try to detect something new, and we actually need to be very careful about our output of image. So I think the major risk of the classical mindset of the imaging for the radio astronomy is if we take one single technique or one parameter set for a single technique, maybe we are just developing a false confidence in some structure just coming from the nature of imaging techniques, but not coming from strong support from the data. So this is actually a major risk of the EHT imaging. So we actually changed our mindset for this particular EHT imaging, which is actually completely new in the field of radio astronomy. Is that so we actually like a 3 mindset to create the images. So first one is imaging must be agnostic. Image should not assume any specific features for these black hole images. And then also imaging must be capable of revealing totally unexpected structure just without assuming any specific models. And then another thing is extrapolarity. I think that is the most important thing for our EHT imaging. So we are focusing on surveying various techniques, and even for each techniques, we actually need to survey a lot of parameter space to know what are possible images coming from data. So this is actually really different from the traditional imaging approach in the radio astronomy. So we actually tried to test a lot of techniques and a lot of parameter space, rather than having a single technique or single approach. Another relatively minor mindset is for these particular results, we try to stick to the simple algorithm. I mean, not assuming, not complicated or not super fine-tuned techniques, which would be a kind of complex black boxes. So we stick to use like a traditional simple technique, or even for new imaging techniques, we use a kind of agnostic prior assumption for making images. And also, what we also emphasize is the reproducibility. So if you go to the EHT website, actually you can download all of the calibrated data in various formats. And also our imaging code is completely in public. So you can actually reproduce our results by yourselves. Or even you can apply your imaging techniques to the EHT data to create your own black hole images. So let me just quickly explain how are the traditional imaging techniques and what are the new imaging techniques. So let me start from the traditional imaging techniques. So radio astronomer has used the technique so-called QUIN for like 45 years. It's like a half-century technique. So the basic idea of QUIN is like that. So we have image and have observation with the EHT and got a sparse measurement. The problem of the sparse measurement is because we don't have a lot of data on not sampled Fourier component. So what QUIN is assuming is you just simply assume 0 for data set are not sampled with our observations. Then just do an inverse Fourier transformation based on that assumption. And then that assumption is completely wrong. So what you will get is a completely messy image, something like this. This is just convolution of the true image and also the point spread function of the interferometer. And then what QUIN is doing is decomposing this dirty map with a point spread function of the image such that the image consisting of minimum number of point sources. So it's a kind of a sparse reconstruction technique. And what you will get is this kind of reconstruction, actually the minimum number of point sources. And this is actually consistent with data, but of course the assumption is completely wrong. So these images are quite different. So the radio astronomy people just blurring image to get higher fidelity, typically the size of the point spread function. Then you will get this kind of images. And actually QUIN needs a lot of user input. Even I myself actually was trained with a lot of data set to how to decompose image using the point spread function. So usually the radio astronomer are putting in this kind of box based on their experience to derive reasonable location of emission of the real emission of the source. So this actually really depending on the expertise of the professionals. And also you may also realize that because this is doing direct inverse transform, so it's really difficult to incorporate a lot of observing effect. So actually the QUIN is doing so-called self-calibration to solve the residual gains. So just start imaging and create some images with QUIN and assuming that this is real and solving the residual gains, then doing this kind of cycles. So this is the way the QUIN is working, but it's probably difficult to get some sort of trust or credit if we only publish QUIN images. So that's why we actually are motivated to develop a new imaging techniques. So new imaging techniques is like a forward modeling approach. So QUIN is doing inverse transform, but we do not do any inverse transform. What we are doing is, again, so we have measurement set, and what we are doing is at each iteration of imaging, we just do a forward transform from image to data. Then what we can do is just comparing the real data and the model data coming from the image, and it just compute the likelihood. And then the good thing of this is we can incorporate many errors and uncertainties based on your observational equations or the nature of the sources. For instance, it's high, but thermal noise or some systematic errors or digital noise and in amplitude of phase. And then also, so this still is not enough to derive a unique solution. So we can also incorporate our prior knowledge about images written in a mathematical form. This could be, for instance, the very simple the assumption is a non-negativity of image because we are looking at just this image is just represent the total radiation from each pixel. That should be positive, non-negative. Or we can assume some sparsity in the image or smoothness of image, or this is also another traditional technique, maximizing information entropy of the image or something like that. So the new imaging techniques can flexibly design likelihood term depending on observing effect. We can actually incorporate many effects directly in the imaging process with many variety, or even combination of variety of the prior assumptions. So this is a kind of Bayesian-inspired optimization. So we basically try to pick up an image, maximizing likelihood and your prior assumptions. So that is what we are doing for the new imaging techniques. So the development of the new imaging techniques is actually one of the prime innovation in EHT in the last several years. So I think we have more than 15 to 20 papers in the last 5 years, just coming from just two groups. So the powerhouse is the Boston area, Harvard and MIT. And also Japan, where I'm originally from. So we have developed a lot of techniques. So for instance, the techniques based on the compressed sensing, or techniques based on the maximum entropy method, or techniques based on some machine learning. I will not go to the details of each techniques, but this is basically describing what is the, your likely image. I mean, this is defining the prior, depending on different prior assumption for the imaging. And all of the imaging techniques, new imaging techniques, are implemented in 2 imaging software packages. First one is developed at a group in Harvard, and then another one is actually the software developed by myself. And this is also completely open source license, so you can actually download data and inspect what is the source code and algorithm by yourself. Anyway, so we have 3 types of techniques. The traditional imaging techniques, which have an advantage of long history, but there are a lot of technical disadvantage. The new imaging techniques are quite new, but it's not tested very well. So what we are doing before the observation is we are doing accumulating experience with the blind imaging challenges. So what we did here is someone actually prepared this kind of theory model. Then another person actually created synthetic data for the EHD, assuming the array performance or systematic errors should be on the observational data, and that synthetic data are distributed to each imaging team without telling what is your ground truth image. Then each team reconstructed images completely independently without any exchange of information, then submit images. Then what we did is we have an external panel which are not involved in imaging process or data generation, and ask panels, what source actually images might look like. And first of all, panel inspect that you can get they can get consistent impression about the type of sources, for instance. And after that, we open the ground truth data to the external panel, and now the panel actually can compare what is the fidelity of each imaging techniques. So sometimes we did this kind of joke challenge. Because most participants are biased and assuming that your input is astronomical images. So that's why sometimes we have this kind of joke challenge. Actually, the winner of this challenge is my algorithm here, which is great. But actually, when we had this challenge, I thought that this is astronomical images. So you can see the central depression here. I thought that this is a black hole, but it turns out that just photons of snowmen. Anyway, so we actually accumulated this kind of experience even before of the actual observations, to make sure that software works okay, or each techniques can reconstruct image very well. Then finally, we got the data in 2018 June. So actually, a year ago. EHD took a year to actually reduce data. I mean, they started from even for data set without M87 and make sure that software works okay, then move on to M87. So that actually takes a really careful analysis with a multiple data review. Then finally, data released to the imaging team. So when we got the data, so what we really wanted to avoid is if if the 70 people of the imaging team work together, then maybe we will bias by the very first image created by someone. So kind of shared bias or group bias. So we really want to avoid this kind of things. So we split our imaging group to the 4 independent imaging team consisting of like 10-ish people. And each team actually worked on imaging M87 completely independently. I mean, without any exchange of information with people outside of each team. So for instance, so each actually team have like a wide range of people, diversity, like from student to postdoc, or people familiar with new imaging techniques or traditional techniques. Actually, each team working as like an independent imaging group. And but still there are some characters in regional things. The team 1 is consisting of people from Harvard University or Smithsonian Astrophysical Observatory. Team 2, actually led by myself, is like a team from MIT, Japan, and also the University from Netherlands. Team 3 is Boston University and people from Europe. And T4 is another East Asian team. And they also have a mild technical preference because Team 1 is developing EHD imaging library and Team 2, I mean myself, developing a SMILey. So the Team 1 and 2 have a modest focus on new imaging techniques, and then Team 3 and 4 have a modest focus on traditional techniques. Anyway, each imaging team worked on imaging for 7 weeks without any communication. That was a really weird moment. I mean, you know, I have, for instance, the EHD colleagues in our observatory, but I could not share anything about imaging results during that 7 weeks to the, you know, my friend working in the next room, next desk or something like that. It was a really weird moment. Anyway, then seven weeks later, we gathered at the Harvard University in the week of July 24, 2018. And this is the exact moment we compared the images across the 4 teams for the first time. So you can see, you know, the submission from each team here, but you cannot see. But you can guess, you know, how are the results from the people's face. You know, everyone looks really, really happy, and Katie also looks really happy. So the results are really encouraging. So these are the first images of M87 compared across the 4 teams. So because of, you know, difference of techniques or the assumption to make images, you know, the images looks slightly different, but the basic structure is the same. For instance, here I overlaid the circle with the same diameter, and you can see that you know, all images have a ring-like emission with a really consistent diameter, and also you can also see that, you know, all images have, you know, the asymmetry where southern part is somewhat brighter. So this is actually consistent with what we presented in you know, our press conference, final images. And then also, so this is the memorial photo after the first comparison. So here, what I show in the screen is actually average of all 4 images, just average. And then you can see that this image is really, really close to what we presented on April 10th. And I also like to note that this is still engineering data. So data are almost good, but still data still have some issues at that moment. So with this engineering data and with independent imaging by 4 teams, we still got this kind of consistent basic structure that actually enhance our confidence about the results. By the way, so these are actually a fantastic international team spending last several years to develop imaging techniques or testing software or, you know, working on imaging in the last couple of years. But you can still see some difference in 4 images. That is primarily coming from, you know, each team's choice. So because interferometric imaging is assuming a lot of things. So for instance, what is the total flux of your, you know, ring like emission, or, you know, what is the weight on each prior assumptions or something like that. So it's a kind of recipe, and, you know, and depending on what you want to include or how much you want to include, the resultant you know, cooks actually have a different taste, right? What we want to avoid is you know, making you know, this kind of choice with a lot of user input. So what we did is like a sort of machine learning approach. So here we just prepare like a training images based on the feature of what we want to distinguish. For instance, we reported on detection of asymmetric ring. So what we need to make sure is if you observe symmetric ring, then you need to get a symmetric ring. Or if you observe asymmetric ring, you need to reconstruct asymmetric ring as it is. And most importantly, we detect the shadow of the black hole. So if we observe image without shadow, we need to reconstruct image without shadow. This is really important. And then also, if we observe, you know, non-circular emission, then actually we need to reconstruct it as it is. Yeah, so what we did is, you know, with this kind of training images, we created synthetic data based on actual coverages of the EHT observations and also exactly same thermal noise and realistic systematic noise consistent with observations. Then we actually ran through 3 imaging pipelines, but what we did is we surveyed a huge number of parameter sets, like 50K parameters. This is completely new in the field of radio astronomy, or maybe even for medical imaging, to just survey what are the possible images coming from the data. Then what we can get is a 50K set of images for each training images, and what we can do is like a tasting of the recipe. So we can just compare the image fidelity and pick up optimal parameter set that can distinguish these 4 images with high fidelity of the image reconstructions. Then with this good parameter set, we can apply these parameter set to the real M87 data. So then we can create like a top set images. So as a result, actually the number of the optimal parameters are like 2,000 images. 2,000 parameters. So we finally got like 2,000 images for each observing day. And actually we presented all of the results from the images based on these 2,000 images. This is actually quite new way to assess the uncertainty of images. So it's really difficult to show 2,000 images, so let me pick up just a representative image here. So this is the image showing the highest performance for the synthetic data. For each imaging software, this is traditional technique, this is new imaging techniques, and this is for each observing day. So still you can see some difference depending on the techniques, but what we confirmed is with the 2,000 images, all of 2,000 images have asymmetric ring which have the very consistent diameter and also the measured direction of the asymmetry. So all of actually 2,000 images have actually shadow-like feature. So for instance, this is a diameter for each software packages, different colors showing each software packages. And you can see that regardless of software packages, the diameter is all the same. And for each observing day, it's actually really consistent to the 40 microarcsecond. And also this is the first moment of the image asymmetry that is also consistent within, by the way, error bar is showing the dispersion of the 2,000 images. It's consistent, regardless of the imaging techniques. And then you can see that actually, the systematic change in the measured direction of image asymmetry within the first 2 days and the latter 2 days, which is seen in data. So we actually start to capture the time variation of M87, actually also for in the image reconstructions. So let me explain actually what we presented in the press conference. So what we did is just pick up the best image showing the best performance for the synthetic data. Then because the traditional technique have worse angular resolutions, so we just blurred by just taking a conservative approach positions, and just take an average. So this is actually what we presented on April 10th conference. So it's just as a representative image of the M87. So by the way, I heard that 4.5 billion people just saw this image throughout the press conference and also the media news after that, which is very impressive. So this is the all kind of average image for observing day. You can clearly see that actually the measured direction of asymmetry is actually changing the first 2 days and the latter 2 days. Let me so quickly introduce actually what we have learned from these images. So for the M87, because M87 is a kind of our neighborhood, although I think you think M87 is really far away from here. It's like a 55 million light years from here, but it's still a neighborhood for myself. So M87 is so close, so we can actually resolve the sphere of the gravitational influence around the black hole, and we can measure the dynamics of the gas or stars around the black hole. That actually provides an estimator of the mass of the black hole. So previously, there are 2 estimators. So if you use the star dynamics, it provides 6.6 billion solar masses. And another one is, it's hidden, but the 3 billion solar masses is roughly half. And if we think that if this is a black hole shadow, So let me set a difference for the stellar mass black hole. It's something like this. And as I said, this is, okay, so this is for non-spinning black hole, and it doesn't change even for spinning black hole a lot, just 4% change. And if the gas dynamical mass is correct, then we will have just a half size of the shadow, something like this. And another exciting thing is, there are many weird objects expected by Einstein's general relativity. One of the exciting objects is a wormhole. There is no event horizon, and it's connecting two different points of our space-time. So there are a bunch of wormholes, but actually some wormhole can create a shadow, like a black hole. But the size is very different. So for instance, this is a very famous type of wormhole proposed by Kip Thorne in, I think, 1970s or 1980s. It has actually smaller shadow like this. Or there is another exotic object, so-called naked singularity. If black hole have a really extremely high spin, then event horizon will disappear, and you can see there's no horizon beyond the, there's no horizon and just only one singularity, which is naked. And naked singularity also create a shadow. It's very compact, like a 1 Schwarz radii. So what we can do is that we can compare these angular size with actual images. And here's the results. So our images are perfectly matched with a black hole, a shadow, with a black hole mass expected from the gas dynamical mass. So the most probable scenario is actually this is a 4 billion solar mass black hole. And if we admit that this is a black hole, we can also test interesting things. So for instance, even if there's a black hole, it could be coming from different space-time metrics, not expected from the general relativity. So if there is a deviation in space-time metric from the general relativity, what we can expect is basically that your shadow shape is deviated from the circle, like this. And what we found is Einstein is still correct so far. So the deviation of the circle in image is like less than 10%, which is completely matching with the prediction of GL. And we don't find anything needs modification in the GL. So another thing is that this is, I think, one of the greatest honor for the EHT, XKCD. I'm making this fantastic plot. So as I said, the shadow diameter is a 5 Schwarz radii. So the actual size of the black hole, I mean, event horizon is like a 1/5. So it's actually really similar to the size of our solar system, and the photon ring radius is very close to the orbit of the Voyager, which is actually, I didn't know that before this image. Anyway, so one another popular question is, so this is, I think, the most popular black hole image before April 10th. This is the photo from Interstellar. And then, this is the most popular black hole image after April 10th, our image. So why actually this is so different? So this Interstellar picture is calculated by the group in Caltech, I mean Kip Thorne's group, for this particular movie. It's actually 17% correct, I think. So what you can see is, first of all, there is a emission, like a bridge-like emission, across the shadow. So this is coming from some geometrical difference between this image and this one. So this one is, first of all, optical image, and this is assuming a very, like a CD, compact disk-like geometrically thin disk, and we are observing that thin disk from the edge on. So that's why we see some foreground emission from the disk. But for the M87, we are looking at the accretion. First of all, accretion flow is geometrically thick, and then we are observing almost face on. So that's why there is no foreground emission from the disk. And another big difference is, the interstellar image is like symmetric, but our image is asymmetric. So this is because Interstellar intentionally ignored one important effect, which is Doppler weaving. I think you are really familiar with this kind of effect. So actual accretion flow or a jet ejected from the accretion flow is actually rotating. And also, actually theory simulation revealed that to explain EHT data and other wavelength data, we need a black hole spin. And actually spin of black hole is dragging our surrounding spacetime. It's also causing the rapid rotation of surrounding medium, apparently. What we can expect is, one side is approaching to our side, and another side is going away from us. So that's why this side becomes brighter and another side is fainter. So the asymmetry is actually naturally coming from the dynamics of the gas, which could be angular moment of the disk itself or dominantly coming from the black hole rotation. But anyway, we expect this kind of asymmetry, and the interstellar actually intentionally ignore it because they think that symmetric image is more beautiful. Anyway, so one thing we can do is we can also, because it's really perfectly matching with the prediction with a black hole, we can also measure the mass of black hole, assuming that this is a black hole. So what we can do is we can, for instance, for the image, we can measure this kind of rich line of the photon ring, and just checking just population of the peak radii from the center. That is giving the typical diameter and also associated uncertainties. And then also what we can also do is we can directly fit some geometric link model to the observing data, I mean, without imaging. I mean, what we can do is like this kind of Bayesian MCMC like approach to derive for instance, diameter or the asymmetry, like this. But yeah, it's actually showing from the Barring stage, but anyway. So what you can get is, the probability distribution for the parameter of this link model, like this. Or theory people did a massive supercomputer simulation. They surveyed like I think 60K parameter set, I believe. And then fitting the data directly again with these supercomputer movies. So they actually fitting directly to their simulation to data to extract the physical parameters from observing data. So actually we have 3 independent approaches to derive the mass of the black hole or other parameter set. So what we learn is, so here the vertical axis estimated black hole mass, and as I said, there are previous measurements for using gas dynamics and stellar dynamics, and this is coming from direct fit to the EHT product from using geometric models or GLMHD supercomputer simulations or image demo extraction. And the great thing is we have an excellent agreement for the black hole mass measurement. So that actually provided 6.5 billion solar masses, which is a massive, even actually massive as a supermassive black hole. So let me just conclude the summary for what we have learned. So I think with this observation, Einstein's GL have tested a new test, new strict test at strong gravitational field, which is the presence of the shadow or photon sphere of the black hole. And simultaneously, it provided one of the strongest evidence for presence of black hole, as well as the detection of the gravitational wave. And the third one, which actually I didn't present very well in this talk, is the theory simulation actually find that an M87 black hole must be spinning to explain observational properties. So this is really important because M87 is known as an active galaxy where the nucleus is very active. And an astronomer believes that nucleus is powered by the supermassive black hole. But finally, we confirm that there is a supermassive black hole, and then also the black hole spin is really good at extracting the rotational energy of black hole and powering many things. So we actually confirm that the AGN or associated, that bright jet is actually powered by a spinning black hole. And then also, what we also found is the stellar dynamical measurement is accurate than the gas dynamics, which is affecting the black hole's mass measurement for other galaxies, which is actually really important to learn the evolution of a supermassive black hole in this universe. And then also, another exciting thing is we actually started to timely resolve the horizon scale time variability in M87, which is also really exciting. Anyway, so what I presented is just the first observation of EHT. So this is just the dawn of the new era of the black hole astrophysics. We finally got a tool to monitor the black holes in the electromagnetic wavelengths with a high angular resolution. So I hope that in the next decade, EHT, actually will find many interesting in M87 and also another target such a star. So I want to stop here and thank you very much for listening.
Time for questions?
This is very nice, and it's very inspirational and challenging for our ambitions to do imaging on the femtoscale, which we were talking about a great deal in this meeting. And so I certainly hope you will leave behind a copy of your talk. I mean, I know they recorded it, but it's nice to have the slides as well, if possible.
Yes. I'm not sure actually how to share the presentation, but yeah, I'm happy to. Yeah, there is nothing must be hide, so yeah, it's okay. It's perfectly fine.
So you showed the different observatories on the Earth, but the Earth's also moving about the sun.
Yep.
Do you exploit that at all, or is the variation of the event horizon too short a time scale to do that?
Oh, that's an excellent question. Let me see. So the time scale variation is actually connected to the size of the black hole. So for the case of M87, we expect like a day-to-day change, and with a current angular resolution of the DHT, we expect that we can actually expect that the structure is almost stable within a day. So we can expect that with one track observation throughout the day, we can make one single image. But actually, the situation is changing for Sagittarius star. This is actually why I presented M87 results first. So Sagittarius star have 1,000 times smaller black hole mass. So it's like what I usually say in the public talk is M87 is like a neutral adult. It's very stable. But the Sagittarius star is like a toddler. So because the 1,000 times smaller black hole indicating 1,000 times, so everything is like happening 1,000 times faster than M87. So 1 month, the things happening on day is happening in minute. So for Sagittarius star, actually we need to make the image reconstruction is not two-dimensional but three-dimensional, involving time variations. So for instance, this is just toy model. But let me show something. Yeah, so the reason why actually, for instance, we didn't publish such result yet is actually we need to reconstruct this kind of movie. And I actually want to mention that M87 imaging was so easy. I actually got that image within just a few minutes after the data delivery, but it still takes a year to confirm this is real. And of course, the Sagittarius star imaging extend the dimension to third dimension. So it's simply actually taking a time if this is real or not. But so for smaller black hole, actually we need this kind of three-dimensional image reconstructions, and we actually have certain techniques to do that. But of course, it takes a lot of time to confirm, the reconstructed images are real or not. So that's why it's really taking time for the another source.
Thank you.
Any other questions? Oh, sorry.
Hi, love the talk. I don't believe M87 can be seen from the South Pole, so what was the South Pole's telescope contribution to the project?
That's again excellent point. Well, yes, M87 is a northern hemisphere source. It cannot see from the South Pole. But the tricky thing is, so we usually observe not only the M87 but also light sources very close to the M87 as a calibrator to make sure that every data processing works okay. And one of the primary M87 calibrator is a southern hemisphere, just like 6 degrees from the equatorial plane. But it actually can be seen from the South Pole data. So still we need the South Pole data to make sure that everything works okay for the M87. So that's why, that is actually causing another time delay because we need to ship the data because we have a petabyte of data set and we cannot send it online. And the South Pole, we'll have observation in April. which is a winter time in South Pole. So actually we need to wait for summer to ship the data. That's why we actually got the data from South Pole in I think in December. So like 6 months after the observation, that also delaying our the data reduction policies. Yeah, so actually South Pole is kind of bottleneck currently for the EHT.
Thank you.
Okay, any other questions? All right, if not, let's thank our speaker again. So we have 2 announcements before you leave. The first being the graduate student postdoc lunch is currently ongoing in F113. So we have free pizza today. So we hope to see you there. And Will Brooks has an announcement as well.
I want to remind you about the secret prize giveaway. The secret prize giveaway will occur in the last session of the meeting. And if you come to the last session and participate in it, you are eligible to receive a prize. We will have 12 prizes, so there will be a dozen lucky people, and they're secret, so come and see what they are.
Evans. I'm a scholar at the Baker Institute for Public Policy, which is a think tank affiliated with Rice University down in Houston, Texas. So scholars, what they call me now after 4 years of postdocing there. So I'm a physicist by training, so it's really nice to be in a national lab. And, but I'll admit I don't know the first thing about nuclear physics, so I'm here to talk about federal policy, federal budget, which I've been studying for the last 4 or 5 years as a postdoc working in a think tank. So what they asked me to do was to go through basically just the general process for budgets, and then I'll give kind of a brief overview of the last couple of years of trends for research and development funding, and then give kind of a brief introduction to how scientific leadership is structured in the White House, and then I'll end with like an outlook for the next couple of years moving forward with research and development budgets more broadly in the US. So I wanted to start by just giving this, so this is like the canonical R&D, oh, is it on? There we go. Okay, many of you have probably seen this graph. This is basically plotting federal research and development as a percentage of total discretionary budget over the last 50 or 60 years. And what's so striking about this graph is that it's been almost constant at navigating between 9 and 12% for the last 40 years. So as the discretionary budget shrinks and expands, so too does the federal R&D budget. So a lot of the discussion this year in terms of the fiscal year 2020 budget is as much about specific programs as it is the total discretionary pool of money that can go to research and development. So I want to point out a couple things. Okay, this is obviously the Apollo era, and after the mid-70s, it's kind of, no matter which president, who controlled Congress, different programs, new initiatives, the R&D budget has stayed constant throughout. I want to point out also this kind of last 2017, but there is a statistically significant dip from fiscal year 2017, which is not resulting from a change in funding, but actually in a change of definitions to the DoD, the way that they structure their budget, which I thought was very interesting. They call it 6.1 through 6.7, which basically goes from basic research through applied research all the way to downstream development. And they basically cut 6.7, which resulted in something like a $30 billion decrease in the total federal R&D budget, which is significant just by categorizing one type of R&D out of what is now considered D. And so I want to just emphasize that R&D budgets, what's most important is how Congress decides to set caps moving forward for discretionary funds overall. So that's the point of the slide. So I want to give like kind of just a bit, am I missing a slide? I guess that I am. Okay. Yeah, so because I'm missing a slide, maybe I should have turned it a PDF like they asked. But basically, in fiscal year 2011, Congress passed the Budget Control Act, which basically laid out caps for the discretionary budget and the non-discretionary budget as they proceed through the next 10 years up to 2022. Basically, every year Congress has just ignored these caps and passed new caps that said, oh, forget about the Budget Control Act. We're going to pass a new amendment to the existing Budget Control Act that basically says, let's just extend the cap so we can keep funding things at previous year's value and give increases. So each year there's this hullabaloo surrounding, are they going to actually raise the caps or not? What are we going to do about the caps moving forward? So that's really the largest question in the coming years is, and in this in fiscal year 2020 is, will they raise the caps again to basically extend and continue funding R&D programs as they have the previous couple of years. The one controversial item surrounding this year's caps is, of course, President Trump has basically proposed budget cuts across all federal agencies to say, okay, we're going to cut these programs in line with the existing Budget Control Act current law so that it meets existing law. And then what he's doing with the defense discretionary budget is he's skirting around that by trying to pull Pentagon warfighting funds. So its budget has kind of been met again this year with kind of confusion and, or not confusion, but kind of like it doesn't make much sense because it's trying to skirt around existing laws. Unlike other countries, the US, as I'm sure many of you are aware, has no set mechanism for setting an entire research and development portfolio. They do so in a patchwork manner across 12 appropriations subcommittees. Excuse me?
It's almost re-election after
Oh, sorry. I don't. No, I'm sorry. It's not. I'm not trying to get Trump elected. All I'm saying is, I just took his main photo. I had a goofier one up there because I give this lecture at class, but I was like, well, I'm at a government institution, so I should use his official photo. So there he is in all his glory. Okay, so there are 12 agencies with over $1 billion research budget. And that's more than you think of, and they're spanned across many different committees in Congress. Of course, the president proposes a budget, Congress disposes. Congress has the ultimate power of the purse. In the last few years, the president has he's proposed sweeping cuts, but then Congress had said, no, we're going to do whatever we want. In the last 20 years, or 40 years, there's been an increasing use of temporary budget measures to continue previous year's budgets, which of course in the scientific community is really difficult to handle because you don't know how much money you're going to get for specific programs year to year, and that can cause disruptions to research programs. I know that was a big deal while I was in graduate school. Now I work on an NSF grant as well, and each year we kind of wonder if
Nice to meet you.
Yeah, thank you. Great. So each year, if the budget isn't passed by October 1st, there's what's called a continuing resolution, which I'm sure you all are familiar with, which basically sends the previous year's budgets into the continuing new fiscal year. One thing in the past 3 years that's kind of been notable is that there really hasn't been a strong voice for science inside the White House. Typically, this role is reserved for who's known as the President's Science Advisor, who's kind of the chief United States federal scientist, who is there in budget discussions. Should I use this one instead?
Sorry about that.
Oh, no problem. Okay, so President Trump finally appointed a science advisor last August, and he was confirmed last January, but he's made it clear that he wasn't really involved in any of the early budget discussions surrounding fiscal year 2020, so we didn't really expect to see anything new from the Trump White House regarding science. But moving forward for fiscal year 2021, it looks like he'll be there and hopefully involved, so we'll be seeing hopefully some change, although you never really know with this administration. And I guess I'm going to get to a little bit about the White House leadership in the later slides. How am I doing on time? Does anyone know if I've gone 10 minutes or? I got 30 minutes. How long has passed? Oh, perfect. Oh, sweet. Okay, so at any given time, there's 3 budgets in play. So as fiscal year 2019 is happening, and there's agencies are already planning for fiscal year 2021. And usually there's kind of 2 important dates. April is usually when Congress decides on the new caps, which they haven't done yet. So everything's kind of in flux, and the House has already adopted and passed 4 spending bills, and earlier this week, including for the Department of Energy, which basically ignores Trump's proposed cuts to the agency. And then each summer in July, or usually in late June or early July, the Office of Science and Technology Policy is run by the White House Science Advisor, releases a joint memo with the Office of Management and Budget that lays out priorities for science, and then it's distributed through the agencies, and they go through this series of passbacks, so I'm sure you're all very familiar, and decide ultimately on how they will structure their budgets for the following years. And each February then a new budget is announced by the president, and then it's arbitrated in Congress for the next year. So there was finally the omnibus passed after the shutdown in February this year, so we're good until the end of September, and hopefully they will pass the budget before before the new fiscal year starts, so we don't have to go through the continuing resolution nonsense, although it likely will be that there will be a kind of patchwork minibuses and omnibuses moving forward. Good, okay, so appropriations process. The important part about this giant map is that, like the DOE, basically competes among other federal agencies inside appropriations subcommittees. So DOE is in the same subcommittee, appropriations subcommittee as Department of Interior and Army Corps of Engineers, and same thing with NIH is competing with the Department of Education, which doesn't necessarily make sense, but they're pulling from the same pool of funds. And so there's 12 appropriations subcommittees in each of the House and the Senate. They all have to mirror each other and they have to pass in total. And usually what they do, instead of passing, one each, they pump them together into separate pockets and then pass them in a patchwork manner. So here's the fiscal 2020 budget proposal. Trump has again still proposed quite a large budget increase, but most of those are increases to one, mandatory spending, and then also defense discretionary spending, including bumps to defense R&D. He's cut non-defense discretionary spending. That should be $63 billion, not $630 billion. That would be, oh, excuse me, that's for non-defense discretionary. Non-defense R&D is about $70 billion, and we'll see what happens. But there's basically cuts kind of across the board. Again, as we've seen for the past 3 years, Trump's budgets have more or less been almost identical. It's like he's learned nothing from this process. He's just going to throw it back into Congress to have them say this isn't good and pass whatever they want. So DOD S&T is minus 7%. NIH got the biggest cuts early on. There's the first year was minus 18%. DOE got significant cuts, including in total acts of RPE. I'm sure all you know. And then NASA, certain programs got 4%. And not listed here is USGS and EPA and NOAA and others that have seen major decreases proposed by the President of the White House. Okay, but then again, so the President proposes and Congress disposes, even though he's across basic applied development, he's proposed dramatic decreases. Congress has done otherwise and continued to extend the caps and spend pass new laws to extend the caps and continue to fund R&D. And the last few years, and kind of a rebuke to Trump, have been pretty big windfalls for all the major science agencies, kind of across the board. NSF is seeing significant increases, and now looking over close to $8 billion budget this year, which has been great for our program. And just this week, the House passed the energy and water bill and several other bills, and again saw a $1.4 billion increase. But this is no surprise from from new Democratic leadership in the U.S. House, and they basically disregarded the president's budget entirely and said this is up from $5.6 billion in total DOE budget, and then specifically for the DOE Office of Science, it's up almost $300 million from last year's and $1.3 billion above the president's request. So that's all really good news. So we'll see how it shakes out in the Senate as they look at their version of the bill. So yeah, I guess the takeaway from the budget stuff is it's up to Congress, and no matter how much the president seems to not care at all about scientific research and development, or it doesn't seem like it's on his radar at all. It is on Congress's radar, and they continue to pass budgets that are very favorable to science. So I guess I wanted to move, why isn't there leadership currently in the White House regarding science? So I want to talk a little bit about OSTP and their role in crafting budgets and kind of changes to the Office of Science and Technology Policy, which really coordinates all of the federal scientific evidence and liaisons with the academic and industrial research communities. So OSTP was founded in 1976 after Nixon more or less fired all of the scientists all at once upon at the start of his second term. And so the office as we know it now is kind of a rehash, kind of a congressionally legislated office that basically said this, OSTP has these certain things. They have to coordinate funding for science and research programs across all the agencies, and so it's run by one Senate-confirmed director who was confirmed this January. He is a meteorologist by training. His name is Dr. Kelvin Drogemeyer. Some of you may know him. And he's a really well-respected scientist who served as vice chair of the National Science Board for many years. And was a vice president for research at the University of Oklahoma and ran kind of a large research triangle in the Midwest. So he's very familiar with the academic research community, specifically in the Midwest region. But he's well known in Washington too for his time on the National Science Board. He was appointed very late, which is why science didn't really show up in part in the budgets. And instead there was a United States Chief Technology Officer, who more or less ran the office in addition to kind of holdovers from the Obama era. His name is Michael Krastios, and he is a former VC employee. He's a chief of staff to a man named Peter Thiel, who is an informal advisor regarding science and technology through the Trump transition, and is an outspoken libertarian in the Silicon Valley community. I don't know Michael's politics at all, but he is regarded very highly within he's done an excellent job promoting U.S. technology and innovation. He's a great public speaker, and also been, agency officials that I've talked to seem to like him. I think he's doing a great job, besides the fact that he's a young guy without a big scientific background. And he's been the assistant of the president for technology, and he's been appointed to be an associate director for the Technology and Innovation Directorate in OSTP. And that matters. The Senate confirmation will allow him to do more stuff. And it will be an interesting thing to see if, having these two titles, one as an assistant to the president, who's more of an advisor, and then also a Senate-confirmed official associate director. There are historically 4 directorates under OSTP. The one that's missing is Energy and Environment, and Dr. Drogemeyer said that he didn't see a need to have that regarding Trump's current priorities for science and engineering. So he's in charge, and there are currently acting assistant directors in both security and international affairs and science. And they typically have a core staff of full-time employees, around 40. That dipped a little bit at the start of the transition, and then afterwards has built back up to the normal amount of full-time employees. What did change in all the reports about saying OSTP has kind of diminished its role, yes, in the sense that it wasn't getting invited to necessarily these big policy meetings, is that all of the detailees left. So Obama's OSTP had something like 130 people at its maximum capacity. Many of these people weren't funded directly through OSTP appropriations, but instead by agencies working in the office. One thing Trump has done right is, or OSTP has done really well, is they've reorganized the National Science and Technology Council, which is a big deal because this is a coordinating council that oversees major interagency programs. And so they've really slimmed it down. Talking to people that have sat on these boards, a lot of times they go, they meet when they don't necessarily have to. So the number of standing boards has decreased, and they really focused on a number of core issues rather than, having something like, I think during the last 2 administrations has grown to something like 40 standing committees and task forces. And so now it's really focused. There's something like 8, and they meet pretty regularly. One thing Trump hasn't done is appointed a President's Council of Advisors for Science and Technology, which is a historically very powerful council of external advisors that advise the President and the President's Science Advisor on science issues. The administration, including Dr. Drogemeyer, said that he will appoint these people, but is appearing to be slow in that process, largely probably because I'm not sure, one, it's late in the term already, and 2, I'm not sure who we could get to sit on these things given the administration's relationship with the scientific community. I hope that there is a PCAST. He did renew the executive order which mandates its existence and operations, so that is a good sign. What else has happened? So typically there are 4 Senate confirmed ADs. There's only been 1 appointed, Michael, the CTO. And then they haven't shown any other interest in getting these people Senate confirmed, so that hasn't been happening. There's no Energy Environment Directorate. A lot of things they've been doing haven't necessarily been science research focused. They've been things like technology focused, like computing and AI, other emerging technologies, machine learning, quantum systems, that kind of thing. Things that are more in response to US competitiveness than necessarily fundamental and basic research that we do at universities and national labs. And then changes of staffing I talked about. There really was a brief dip in terms of total number of staff members, but a lot of them are DTLs and not full-time employees. So I guess I wanted to end, I don't know, I want to leave time for questions, just in terms of moving forward the outlook for R&D and the federal budget in general. The question really remains if Congress will continue to ignore the caps that they passed, almost a decade ago at this point, and continue to extend the caps. The point of this graph is basically showing the non-defense, defense, and mandatory and discretionary budgets next to mandatory, and you can see how mandatory spending has kind of grown significantly over the same 30, 40 years that I've been talking about. So really, will we be able to fix healthcare, for instance, and reel in mandatory spending? Debt is also an issue. CBO projects basically where the outlays, the top line, are going to continue. I'm sure it won't be this straight. And CBO it makes it look kind of still pretty severe in terms of the gap then between our expenditures and then the government revenues, and that gap would continue to expand, increasing our debt and leaving very little room for discretionary funds. And so then I guess I want to talk about changing roles of new precedents for both federal funding research and then industry-funded research, and then nonprofits and university research. Again, here is kind of the start of the Reagan era, where Reagan's policy towards science was, we'll do basic science, we won't do any development, let industry take care of whatever we can do. And as we all know that that doesn't really work out very well if you just let industry pick up where science at the research stage lets off. So there is a kind of a decline, mostly in development. If you look at development as a percentage of GDP, there's a dramatic decline after the early 80s, which is signaling a new stance on industrial policy regarding an investment from the government. This was the start of the NIH doubling, so mostly this dip back up is from increasing investments into bio research, and then here is the Recovery Act of 2009, and since then it's been pretty much on decline as a percentage of GDP, which is a really good thing. So I want to end with this graph because I think it's an interesting take on what happened with basic research, things that are curiosity driven, not necessarily going to end up in the marketplace. Is really there was a continued growth of basic research funding, and after the early 2000s, it's more or less capped off. And so really this is, in many people's view, should be the crux of how government funds science is in basic research, things that industry isn't going to pick up and do, and there being continued growth in basic. This isn't even a percentage, an intensity thing. This is like in millions of dollars. So it's kind of capped off, and really will government continue to fund basic research is an open question. But one thing to note is that in the same amount of time period, university specific programs from campuses have increased substantially over the past 2 decades. And same thing with nonprofits. So nonprofits taking more active role, not just in biomedical research, but also in the physical sciences as well, which is an interesting change. And I can talk more about that. Then I also want to point out one of Dr. Drogemeyer's, the science advisor's, comments about alpha institutes, and he's trying to focus on government university industry partnerships, who are notoriously very difficult in the US, and most university campuses, Rice for one, my home institution, does a pretty terrible job at moving things from lab to market, mostly because there are all kinds of rules about being tax exempt and other issues regarding infrastructure and shared facilities and all these other IP issues and things like that. But if he's really going to change regulations to, these are his words, and there's no hard evidence of concrete language of how things would change, but really shifting the way that government, university, industry partnership works, or specifically university industry partnerships work would be a welcome change to a lot of institutions that really struggle to develop products on campus. Not that campuses should necessarily be the place where that happens, but there should be an easier time if there are new IP, new idea on campuses, getting those things to market. And then one thing Dr. Dorjamai did do was talk about long-term planning for science, which has been in a lot of policy, science policy people's agenda for a long time, just skipping all of the process of year-to-year funding up and downs, and rather trying to make longer-term investments so we can actually plan and do our research on a timetable. And he points to the high energy and physics community, because you guys have a really robust process for setting goals and achieving them. So I think that's it. I will take questions. I personally study PCAST. Is my kind of the work that I've been doing. It's a history project as much as a policy project, but I'm happy to talk about budgets and about scientific leadership in the White House. So thank you for hosting me. I enjoyed it.
Minutes. Any questions? I think first.
Okay, so show the initial plot with the percentage of discretionary.
Yeah.
Stable about 10%. But then you also show mandatory spending.
Yeah.
So the percentage of the total is getting smaller.
Right.
Right. So,
Yeah.
so should we feel happy that it stays at 10% of discretionary, or should we be worried that it's dropping as a fraction?
Yeah, good question. I mean, frankly, I'm worried. I don't think anyone in the science community is not worried about the future of science budgets. That's a real issue. But I guess that it's really creative to basically say this is what we should expect for R&D, not as saying this is necessarily news, I suppose. And so if mandatory spending and interest are going to continue to rise, we have to continue to lobby for increased basic sciences to kind of match scope investments, also that to fill the need of doing research. His work.
Let's try.
Better to compare. I think all these curves really should be related to GDP.
Sorry, I didn't make that clear. Most of them are. I should have stopped and illustrated that. This one is not. So basic research, if you looked at it as a fraction of GDP, had more or less grown up until the mid-'80s and then kind of levels out. And then applied research, and so let me go back one slide. So here. Is there a laser pointer? Oh, here we go. So federal R&D, federal research, just research being basic plus applied, and federal basic research as a function of GDP has been more or less constant all of these years. So as GDP grows, also basic research, applied research. What has changed is the federal government's investment in development. So if you look at that plot, I should have plotted it. There's a huge thing, and then the dip basically sits here. If you subtract, these three curves, you can see basically, or these two curves from this curve. So this being entirely federal R&D, these two curves being R and applied and basic R. And so you'll basically see a huge dip in development funding from the government. So, but basic research and total research being applied and basic have been more or less constant as a function of GDP. So I think your comment is right. I think seeing it, they call that, I guess, research intensity, whatever that means. I mean, that is what that means, but it's jargon saying as a percentage.
Other questions? I have several. Could you talk more about the non-profit contribution to R&D? Separate.
Yeah. Sorry, I think maybe it's a. Oh, that's smart. Okay. Yeah, there's the philanthropy, science philanthropy is really interesting because it's a really there have been a number of recent changes. One, there's this I think it's called Science Philanthropy Alliance or something like that, which is basically pools together lots of different, so people like Packard Foundation, Moore Foundation, Rita Allen, people that will fund basic research and not just biomedical. So historically, foundation research has been largely from, say, Gates Foundation, which has comparatively a much large, an endowment of something like, I think it's just over 3 or 4 billion. So they give out about $800,000 to $1 billion a year in research money for biomedical sciences. So that, with respect to physical sciences and the philanthropy community saying, funding quantum science or something is pretty minimal. But what people like Moore and Packard will do, those foundations will fund individual researchers, and then they're starting to get more into infrastructure and other things on campus. So the Science Philanthropy Alliance is really active in kind of pulling together to be able to do more with their money rather than giving out smaller grants. So that's an interesting thing that's been happening. There's also been, now what are these prizes called? Zuckerberg and crew in Silicon Valley gives out their version of a Nobel Prize every year, and the prize money for these awards is significant. It's something like 3 or 4 times that for a Nobel Prize, and they give out a ton, which is interesting. But then that raises also questions of the private sector, funding basic science, individuals that are the heads of these foundations making decisions about where the money goes rather than going through our well-established peer review process. So I don't think it should replace, obviously it shouldn't replace federal funding in basic science, but it could augment things moving forward if the pool of money continues to decrease. And then university-based funding, that brings up mostly questions of equity. About how resources are shared, so places with large endowments. Rice, for instance, has a pretty significant one, and so in terms of doing large new research programs or infrastructure projects, that'll probably happen in larger universities where you have a significant endowment to fall back on if the economy begins to dip. But the total share, it is interesting that these things have happened in the last couple years. And so this is exactly what Dr. Drogemeyer was talking about, is these alpha institutes as we're establishing on university campuses. Something more, he uses the Bell Labs model, of course, but Bell Labs for a long time had pretty close to monopoly, so it's on the telecommunications market, so it's hard to think that Bell Labs will ever be duplicated, but there are things that they could do to establish more permanent long-term research programs for other fields that aren't necessarily high energy physics or heliophysics or stuff where you can really take a long-term look at things. So yeah, I hope that answers some of your question.
Time?
Yeah, sure. Yeah.
No, you had.
Okay.
Yes, the red curve shows the total federal research and development, and you made a statement development which goes down. Do you think that's a result or a cause of the governmental component from the fact that the private and other contributions to development have gone up?
Yeah. Likely both. I think it's a change of certainly the Reagan era was really what started that, is their specific policy saying we're staying out of industries, we're not going to fund anything in which the government, which the industry can do. And then of course there's advanced manufacturing in the 80s was a big part of U.S. federal science policy. And so, and then you had, a lot of this too in terms of industry research and development. What's counted? A large portion of it is pharmaceuticals. So the amount of money that goes in from, from Pfizer to Pfizer to create a new drug is, well, they claim it to be pretty significant. And then also you have Silicon Valley that's invested in certain aspects that universities, or that the government considers to be a research and development. But it's all self-reported, and so typically industry has a history of over-reporting the work that they do in R&D. But it is really significant. I shouldn't take shots at them, but sorry, my mic went out again. Sorry. Anyway, it's to answer your question, it's both. It's both the result of federal policy and also increased investment from industry. Yeah. There was one there if you want. I don't know how much time I have left, but if you wanted to ask this question, sorry. Oh, okay, no worries.
We have 1 minute. So if you're fast.
Well, I was going to ask, it may not be in your line of research, but do you have any thoughts on the reduction in the number of faculty committees?
Oh, yeah. Yeah, I have lots of thoughts about that. It's straight up bad. Yeah, and it's based on, the language is almost identical to Bill Clinton's '93 executive order. It's funny how he took it almost directly from that. It's about the FACA committees, the 1/3 reduction of FACA committees. So that really is targeting, I would say, environmental and energy resources. It kind of follows in line with administration priorities towards trying to stomp down on renewable energy and environmental research. And so it kind of follows. There was that EPA, all the business surrounding FACA's language about being fair and balanced, and then using that against the Science Advisory Board at the EPA to kind of get more industry representatives in there, that kind of like really weedy stuff. But yeah, that shouldn't go unnoticed. I mean, there are about 1,000 FACA committees, something like 300 deal directly with science and technology, innovation to some extent. A lot of them, so for instance, at NSB is in a FACA committee, which is interesting, under the Sunshine Act, which is interesting. But NSF has quite a number of other FACA committees that are active in various research areas. I doubt much will happen. He hadn't laid out a plan that said, this is what's going to happen at the agency if you guys don't get rid of 1/3 of your FACA committees. He's just asking for a plan to get rid of them. I don't know how much traction it will gain. Certainly, the scientific community isn't happy with it. I'm not happy with it. I thought the delay and the no PCAS thing is a pretty strong indicator. But we'll see. I'm doubtful that anything will happen in the next 2 years, that he's elected. But I think it's a really bad, order. I mean, personally, I think it also speaks to the fact that people don't know what FACA committees really do. It's hard to quantify the work that they do, and it's extremely important advisory work, and no one's telling those stories usually. Because there's no one that's going around and collecting, evidence of saying, this is why. Our committee on soil and rain runoff is the most important committee. They really do tremendous work, and it takes a lot of time for the researchers that are doing these FACA committees. So it's a real slap in the face to the people that serve on these things, because they pour a tremendous amount of time. And really, it's almost like one of these things like getting rid of OTA, right? Like it makes an example of it, because OTA's budget is negative. And same thing with FACA committees. They run on bare bones. The PCAS annual budget was something like $200,000 a year most years, and that was just for getting coffee for everybody and flying them in to have plenary sessions. And most of the work that these FACA committees aren't even in the required travel. A lot of the work and reports that they do. So really, it's a kind of just a statement thing rather than anything that's a really meaningful policy. Was my view on it. This is forgetting I'm at a DOE facility, so maybe people here have more insider knowledge about what's happening on the ground at DOE and all of their FACA committees. But yeah, I thought it was a bad piece of policy that won't do very much. Yeah.
Thank you.
Talk about physics, Diane Gwen, and she's going to talk about short-range correlations. Please. Thank you. Hi, everyone. First of all, I would like to say thank you very much for organization for their invitation to give a talk today. So today I will give a presentation about short-range correlation in neutron-rich nuclei. So there were a few talks about SRC in last 2 days. So let me just quickly have an introduction about what is a short-range correlation. So in nuclei, when nucleons come really close together at a distance about 1 Fermi meter, where their wave function overlap, they experience very strong correlation and forming the short-range correlation pair. And nucleons in the short-range correlation pair have a very high relative momentum, and they have a low center of mass momentum. So the next question is that why do we care about the short-range correlation? So the answer for this question is that short-range correlation is really important for the nuclear physics, and it is also very significant to other fields as the particle physics, quantum mechanics, astrophysics, neutrino, or atomic. So short-range correlation is not a new topic. It has been studied for years, and it spans a huge amount of effort from both theory and experiment. So where do we stand, and what do we know about short-range correlation? So there are two main results we know about short-range correlation. The first one is that short-range correlation is the universal behavior from different nuclei. So short-range correlation is responsible for high momentum tail from different nuclei, and it accounts for 20 to 25% of nucleons. 20 to 25 nucleons in the medium to the heavy nuclei. So second important result we know about short-range correlation are the NP pair dominant. So in the triple coincidence experiment in the whole A JLab, we find using the carbon-12 the target, we find out that 90% contribution of the short-range correlation pair come from the NP pair. So only the 5% come from the NP and the NN and the PP pair. So it means that contribution of NP pair around 18 times bigger than contribution from the PP or NN pair. So we have another measurement with the wide range cover of the different nuclei from the carbon-12 to the lab. So we observe the consistent behavior of the NP dominant. So fraction of NP pair is over 100% here, and when we have a very small fraction of PP pair in the short-range correlation. So it is consistent in the wide range of A. And this NP dominant also can be explained by tensor 4 dominant in NN interaction. So with these two, the main result, we have a next question is that what else do we want to learn about short-range correlation? So there are many things we want to study about short-range correlation, but today I just focus about two questions. The first one is that the nuclear asymmetry dependent of the SRC. And second is the separated the contribution of proton, neutron to the short-range collation. And to be able to study about this question, the neutron-rich nuclei is a perfect tool to study about that. And we have a several experiment results come out recently. It can help to explain some aspects of this question. So I will show you some results about this experiment later. But before we go to seeing the result from the different experiment to study about to study in the neutron-rich nuclei, let's take a look about what happened to SRC in neutron-rich nuclei. So let's start with symmetry nuclei. So in symmetry nuclei, we have the same number of proton and neutron. And as I mentioned earlier, with the NP dominant, what we expected is that in the high momentum tail, where we have a number of the NP pair is dominant, we expect to see the same number of proton and neutron with the high momentum. So now, when we're adding more neutron, what will happen? So the first assumption is that when we're adding more neutron, the red line here, and if these neutron, they are uncorrelated, what happens is that they will add more neutron in the low momentum side, but we'll have no change in the high momentum tail. So we just only increase number of neutron in this region. So second assumption is that now this adding neutron, they correlated, but with each other. So what does that mean is that we will have a more number, we will increasing the number of NN short-range correlation pair. So in that case, we will increase the number of the neutron with the high momentum. Yeah, and then the third assumption is that now this adding neutron, they correlated with the proton. So in this case, what happened is that in this case, the number of the NP pair will increasing. So it means that we will increasing the number of the both number of proton and neutron with a high momentum. So to study about what the assumption is correct in the neutron-rich nuclei for SRC, we using the different channel of experiment. So the way we study about it is that we're using the electron come and interact with nuclei and breaking the short-range correlation pair, and we will detect the different outgoing particle to different channel. The first channel is inclusive, the scattering EE bright. So in this channel, we only detected the scattering, the electron. And second channel, we are using is the EE bright P. So in this channel, we will detect the leading proton as well. So the third channel will be EE bright NN. So in this channel, we will detect everything like scattering electron, leading proton, and the recoil, either recoil neutron or the proton. So there are several experiment results come out for the last few years about the neutron-rich nuclei to study about short-range correlation. So let me start with the result from EE bright P. So let me start with EE bright experiment. So this experiment will happen in the whole A, and this is my dissertation thesis. So we do the scattering on the isotope calcium-48 and 40. So the special about these two nuclei is that they have the same number of the proton, 20 proton. But the difference is that calcium-48, they have A more neutron. So what we want to learn is that now we're adding the A more neutron. What will happen to short-range correlation? So the result I'm showing here is a cross-section. We take the cross-section ratio from the calcium-48 to calcium-40. And in this region, it's the high X BJ, where we believe is that short-range correlation is dominant. So the cross-section ratio looks like a constant here. And this value of this constant is about 1.2. So what is this result telling us is that when we're adding more neutron to the adding A more neutron, we're also increasing number of the short-range correlation pair. So that is what we can see. But this one is the EE bright experiment, so we are not sensitive to contribution of the proton and neutron. So we cannot separate the contribution of the proton or neutron to the short-range correlation pair. So we are moving to the next data set. So for this data set is the class collaboration for 6 GeV in the whole B. So this analysis will publish on the Nature next year, and this analysis showed two very important results. I will go to the first one. So in the first one, what we did is that we take the ratio of number of the neutron to number of the proton in the high momentum and the low momentum of the mean field. So results showing that the ratio of the N over P in the high momentum is a constant, and this constant very close to 1. And what does that mean? So this means that in the high momentum, the number of we have the same number of the proton and the neutron. So this result is consistent with the expectation from NP dominant. And second result tells us another interesting story. So in this second result, we are taking the fraction of the high momentum of the neutron and the proton. So results showing us is that the fraction of neutron with the high momentum with the symmetry of nuclei almost as a constant, but the fraction of the proton with the high momentum increasing with the asymmetry of nuclei. So this result is very interesting because it's showing us that it looks like the neutron is saturated with the symmetry. But for protons, they are more correlated when the asymmetry increasing. It means that when we have a more neutron, we also have a more proton in the short-range correlation. In the other hand, is that this one showing us that protons have a higher kinetic energy in the neutron-rich nuclei. It's very interesting. So with the experiment result, we be able to answer the few questions of the short-range correlation in the neutron-rich nuclei, but it also have a limitation. So first limitation of this data set is that we have a very low statistic. And second is that I want to point out that we are using one symmetry nuclei in the carbon-12 here as baseline. And then we will take the ratio from different nuclei on the carbon-12. So this one is not ideal to be able to test the separation contribution of proton and neutron to the SRC. That is why we propose another experiment, EE'P, in the whole C of the JLab. That experiment named CAFE. So what is special about this experiment? So in this experiment, we select a very special set of the nuclei. So we have a calcium-40, 48, and the iron. So what's special about it? So to move from the calcium-40 to 48, we have the same number of protons, but now we're adding only neutron to this system to go to calcium-48. And from calcium-48, we will move to iron by adding more proton. So by using this special set of the nuclei, we will be able to separate the pairing probability of the proton and neutron in the SRC. And because of they are having the proton and neutron on different orbits, so we can be able to study about pairing from the different orbits as well. And this is kind of like pretty big asymmetry. It can show us the asymmetry dependent as well of the SRC. So all of these experiment results will be able to tell us a lot more about the short-range correlation. But we also want to confirm this integration with the theory calculation. But as you know that all of this nuclei is very heavy. It's very challenging to do calculation for those heavy nuclei. That's why if we want to have a confirmation with the theory calculation, we moving to the field body, the system. That's why we have an EE'P experiment, tritium experiment in the whole JLab. So the special thing about the tritium experiment is that we are using mirrors, the nuclei, helium-3 and tritium. So this one is just like field body system. Because they are like field body system, we will be able to have a theory calculation for it. And second thing is that the tritium is one of the most asymmetric nuclei. And another thing, I think the other tritium talk also mentioned is that because they are mirror nuclei, so when we take the ratio of the momentum distribution on the helium-3 to tritium, we will be able to access the information of the ratio of the momentum distribution of proton to the neutron on the helium-3. But this one will help us to avoid a lot of trouble to detect neutron because detect the proton in helium-3 is much easier compared to detect the neutron on helium-3. Yeah, so in this experiment, in this tritium experiment, what we want to do is that we will take the ratio of the cross-section between two nuclei to be able to study more about short-range correlation. But before we go to the experimental result, let's take a look at the simple expectation from the theory side. Because now here we are taking a look at the ratio of the momentum distribution between helium-3 to tritium. based on the simple counting of the number of protons between helium-3 to tritium. So this ratio of the momentum distribution will be around 2. So that is very simple, the estimation. But you remember that we have an NP dominant. So if with the NP dominant, what is the ratio need to go down around 1 in the high momentum tail? Because of both helium-3 and tritium, they will create a 2 NP pair. So they have the same NP pair in these 2 nuclei. That's why if NP dominant, this ratio will equal to 1. And to balance between the degree here, the ratio, this ratio, it needs to go above 2 in the lower momentum. And then we will have a transition between the low to the high momentum. So it will be really good if we be able to map out the region when we're able to see the transition from the low momentum to the high momentum. So we also have a lot of the theory calculation to predict this ratio as well. So we have the set of the calculation using the spectral function, using the 2 different spectral functions here. And we also have the VMC calculation to predict what is the ratio for, what is its ratio. So now come to the experimental data. So when we compare experimental data to all those theory calculations, we observe something very interesting. So first of all, you can see that in the momentum is below Fermi momentum. It means that the low momentum side. You can see that data and theory calculation agree with each other really well. But when we move to high momentum tail, you can see the very big difference. It from the 20 to 50% depend on the different calculation. So this is really big. Difference, and we still don't understand. We not be able to understand what it happened here. So this difference, it can be because of the symmetry, asymmetry. It also can come from the final state interaction. Actually, we take into account some theory calculation for the final state interaction from the MESAC, and that one is that can take into the account of the 5%. So that definitely cannot be able to explain this big difference in the high momentum. So we also can think about other thing is maybe we have some problem with the NN interaction. So it can come from anything. So that is why we still spend a lot of time to be able to study about the high p-mid region to be able to nail down the difference between theory and experimental calculation. That is why we are moving forward to extract the cross-section to be able to nail down this problem. But we also need a theory calculation input to be able to understand this problem. So let me finish up my talk with the conclusion. So neutron-rich nuclei have to understand a lot of questions. One of the biggest questions is that the proton is more correlated in the neutron-rich nuclei. And second is that we have an experiment is coming in the JLab. We can help us to study more about short-range correlation. And we are moving to absolute cross-section for helium-3 and tritium to understand the difference at the high momentum. And we need the input from theory to be able to explain what we are observing from the experimental as well. And finally, thank you very much for your time. Yeah. So any questions? Yeah.
We have a few minutes for questions. Any questions?
Can you talk a little bit about the timelines of CAFE? That's number one. And then if you go back to your last experimental slide, how do you expect this picture to change with the new CAFE data? Yeah, sure. Yeah, so let me start with the CAFE first. So actually the CAFE, we think that original plan, it will run in the next year. And I will assign this project for my postdoc time. So I'm really hoping that I have a chance to be able to run CAFE before I end my postdoc. But at this time, I think that it may be postponed to maybe next year or even 2022. So we don't know about it yet. But I'm really hoping that it can moving forward and we be able to run the CAFE as soon as possible. And I think that the question about CAFE, it can change this picture or not. So furthermore, I think that for the CAFE, it's using the very heavy nuclei. So I don't think like we will be able to separate the pairing probability of the proton and neutron in the short-range correlation using CAFE. But we will not be able to have a theory calculation for CAFE. Yeah, but for this one, it is a few body. This one is a few body system. So we will be able to, if we have a theory calculation and we also extracted the cross section, it may be able to nail down this problem. And the difference may be not the bad thing. So maybe this one is that indicate that we didn't understand the theory very well. Maybe we didn't nail down the constraint of the NN interaction at the short distance. That is the one possibility. So maybe that one can, if we can understand this difference, we may be able to put a new constraint on the NN interaction at the short distance. So that is my answer for your question. Yeah. So in the meantime, any other questions? So then as a follow-up, as far as I know, there are ab initio calculations from the theory community on nuclei as heavy as lithium. Have you considered not those nuclei, although you may end up with the same problem? That's number one. And number two, is there any other observable you can think of using this same nuclei that could be helpful in studying further this problem? For these two nuclei, I think that at this point we only can think of taking the absolute cross section for it. Yeah, because this one is cross section ratio. We think that in the ratio a lot of information may be lost. But if the absolute cross section, I think it can tell us more about this difference. So that is our approaching at this moment. And you also mentioned about theory calculation for the other nuclei as well. I think that in the CAFE, what I'm showing is just the focusing of the CAFE, but we also include few more other nuclei when we're taking the data on that one to be able to compare with theory calculation from few more nuclei. It's not just only this, but this is our focus. Yeah. Thank you.
Thank you very much again.
Now we're moving towards price procedures.
Good afternoon. This session is giving us an opportunity to recognize some of the recipients of JSA prizes and awards. These prizes and awards are part of the JSA Initiatives Fund program. This program was put in place over 12 years ago, and its purpose is to further the scientific outreach and enhance the lab science and technological programs, and also some activities and initiatives and projects that benefit the user community, that's you. This just shows some of the categories in which JSA funds have supported over the past 12 years. The over $6 million, a large part of it has gone to graduate support, undergrad support, and even the STEM education K through 12 groups. And then we also support scientific meetings. That includes this meeting here, and other user support projects and outreach. The prizes that we are awarding today, I'll talk about later, but also this year in the FY19 program, we've already awarded several prizes, several projects. The JSA Graduate Fellowship Awards program was something that was started in 1989 by SURA. SURA is one of the partners of Jefferson Science Associates, and we were actually the original M&O contractor for JLab. We started this, and since then we've awarded 225 fellowships to 22 different SURA universities. This year we're happy to announce that we were able to award 9 fellowships to Devaki Bhattapatek from Louisiana Tech, Colin Eggerer, Tanjeev Khan, and Amy Schertz from William & Mary, John Matter from UVA, Joseph Newton and Sajini Wachianga from ODU, Richard Trotta from Catholic, and Yunji
Yang from MIT. Youngshi is in his second year. He also just finished up his current fellowship at Jefferson Lab. Another part of the Initiative Fund program is our sabbatical leave support program. This again was started by Sura back in the late 1990s. We've made 31 awards to faculty members who choose to spend part of their sabbatical time here at Jefferson Lab, and we provide some nominal living support for them while they're here. The current awardees for this year were Keitha Bimini-Watha from Louisiana Tech and Juliette Mamet from the University of Manitoba. And it's noteworthy that both of these recipients also were prior recipients when I believe Rakitha was a prior thesis award holder, and Juliette, when she was a student at Virginia Tech, won one of the JSA fellowships. Then some other awards supported by the Initiative Fund program. The Hugs International Fellowship for grad students in developing country. This year chose two students, Hassi El Jarrari from Morocco and Johan Hernandez Ibarra from Mexico. And I believe they're just finishing up their program here at the lab. The Accelerator Physics Education Outreach with Mexican universities. This project, very interestingly, started at JLab, funded as part of the FEL program that was here at JLab, and it was continued and picked up by the Initiatives Fund program several years ago. Victor Manuel Lazaraga Rubio is the recipient this year, and the interesting thing about Victor is he was nominated by and awarded this support by the recipient of the first winner of this Accelerator Education Outreach program with Mexican universities. So the first recipient was here on that, and now he's nominated a student, and his student is here. A couple of other awards have been made. The Cooperative Education Program, Neil Bashmi from Rochester Institute of Technology has been here for several months now. He is working with some of our engineering folks who are mentoring him. And we just this week awarded the Minority Female Undergraduate Research Assistantship to Maya Watts from Michigan State University. So now I'll move on to some of the recognition that we want to make. These projects that I'm going to talk about are under the purview of your users group board, and they may have made these awards. So first, I'd like to recognize the recipient of the JSA Postdoctoral Research Prize. This was established by your board back in 2008, and since then we've made 12 awards. This year, the 2019 prize is awarded to Argonne postdoc Andrea Signori for his project Unraveling Hadronization. And Andrea was a JLab postdoc researcher before he moved on to Argonne. Andrea, I hope you're here. There you go. Juliet, Will. Where? Here. Where? Yeah. Congratulations. Congratulations. The next recognition is for the JSA Thesis Prize. This, again, the Users Board started in 1999. We've awarded over 20 thesis awards. This year's award is to Los Alamos postdoc Curtis Bartlett for his dissertation for his William & Mary degree. And Curtis was a recipient of one of the fellowship awards a couple of years ago. Curtis. Put this in your pocket.
Thank you very much.
On your head.
Oh, I see.
Oh, are you okay?
I'm small.
There we go. Appreciate it. Thank you.
And then finally, earlier this week, you held the poster competition, and you made some selections for that. So I'd like to honor these prize winners. First place is Patrick Berry from NC State. I understand Patrick had to leave. Okay. Second place goes to Berku Duran from Temple. Berku, are you here? Oh, come forward, please. And third place goes to Jahini Wachunga from ODU, who also, as you heard, is a recipient of our JSA Fellowship this year. So Jahini. Let's see, Berku. I hope I pronounced your name right. I didn't, did I? Burju, okay. So I should have asked you before. Congratulations. That concludes it.
Thank you, Elizabeth, and thank you for the JSA support.
Certainly.
I'm chair of the JLUO user board. It's going to manage it.
Hi, welcome everyone. So I'm going to talk about JLUO organization. You probably know us because we organize these meetings that you're here, but that's not the only thing we're doing, and I'm going to try to run you through what we're doing. All right, so we have a wiki where you can find more information about us, but basically what we're doing can be put into 3 categories. We do community building, like we get this great meeting going on. We represent the users within JLab, and we do some outreach. Our group is a group of 12, and 12 people who were on the board up to yesterday evening are here. So the people who are highlighted in red here are outgoing members. If you see them in the hallway, go ahead and tell them thank you for working for the organization. One thing more that you can notice on this here is that everyone has a focus. And so if you have a specific issues that will fit into these categories, go ahead and talk to those people. I think the posters are up in the lab, and it's up on the hallway, so you can figure out what is everyone doing. I'm very pleased to introduce the new members who started yesterday. Ed Brash is going to be our chair, or your chair, in a few years. There's a chair line here. Wouter is a new member. Suzanne Schemann is a new member. Emily Passmar and Amy Schurtz is a new member. I want to thank everyone who accepted to be on the ballot for the election. Thank you very much. And I also want to thank all of you who voted. It's important. Go ahead and vote next year. We have a nomination committee whose members are here. They also deserve thanks for putting the ballot together. If you want to run, or if you know someone who will be good in this kind of job, go ahead and contact them. They are always looking for suggestions. Okay, so I'm going to give just a few examples of things we do as an organization. So we do community building. As I said, we organize this meeting here. You might have taken part to the satellite meetings that we have at the APS in April and for the DNP fall meeting. We organize the poster competition and the launch networking that some of you might have gone to. Today, there is also a software carpentry workshop that is going on. As Elizabeth said, the awards that were given today or presented today, we run a committee for evaluation. Ken Paschke was the person who ran the evaluation this year, as well as other committee members. You can also tell them thank you for this work when you see them. And we submit several continuing initiative funds to GSA. GSA is supporting most of our activities, and we're very grateful for that. Thank you. Oh, yeah, another thing that we do is representing the users within JLab. So we have 3 persons here who are representing you in a JLab standing committee, the Safety Council, the Radiation Review Committee, and the Director Inclusion and Diversity Committee. And these are the people who are representing you. The JLEIC chair is an observer in the PAC deliberation, and it observes mostly the interaction between the PAC member and the presenter or the proposers. And then we meet twice a year with the JLab management and also with GSA twice a year each. The last meeting was in March with GSA, and with JLab we're meeting yesterday and today. So now we're going to the outreach event that we're doing. So the thing that the largest event for us is participating to the organization of the Nuclear Physics Day on the Hill. So that's when users go on the Hill to talk to Congress people and senators or their representatives and advocate for nuclear physics at large. It's an action that is combined between JLab, JLEIC, FWIB, and fundamental symmetries. And as you can see, this is 7 years that we're participating, and each year we have more participants. So I'd like to stop here and ask, maybe by a show of hand, who has gone? If you've gone to one of these, can you show us you've gone? Okay, so if you've not gone, you can look at your buddy or your colleague and ask them how it is and what is happening there. This is something that Stuart, Bob, and I think also our funding agency said it's important for us to go and make the case. So if you've not done it yet, not very good. But good thing, I'm going to show you how you can do it. So if you go to our wiki, here there are instructions to put in your non-JLab and non-governmental email address. We cannot use a JLab or your governmental email address to contact you to go and do some lobbying. So we have a separate mailing list. So go ahead and you can register there. And it's basically very much like when you're registering for mailing list at JLab, you send an email to this address here saying you want to be registered and will be asked to confirm. If we don't have your university email address or your personal email address, we just cannot tell you that you need to show up on that day, right? So we need your email address there. If you're still confused, these slides are going to be put on the web. If you're still confused, ask me or ask any other people who are on the board. We'll tell you how to do that. Okay, another thing that we do for outreach is to bolster the JLab representation with its scientific organization, and for example, within the DNP Executive Committee. But we think about, well, maybe proposing names to NSAC, fellowships, and things like that. Each time you get a message saying, hey, who wants to be on a committee? We have a committee to suggest your name, right? So the one that is coming up is the DNP Executive Committee. This is going up in 2 steps. First, there is a solicitation going out from the DNP Nomination Committee asking to suggest names. And then based on the names that have been suggested to them, they put on their own ideas, of course, they put together an election ballot. So the end of this solicitation nomination is coming on July 1st. And we have decided, the JLEIC Nomination Committee has decided that they will nominate Curtis Meyer for the chairline. More people nominating or suggesting the name to the DNP committee will make a stronger point. So we encourage you to go ahead and suggest the name on the online form that is accessible from the DNP webpage under news and announcement. Because those slides go on the web, I give you the link here. It's probably easier to go from the DNP website. So if you want to help us, and if you want to try to bolster the representation of JLab on the DNP Executive Committee, we suggest that you suggest Curtis as a new member, or to be put on the ballot. All right. So we've been meeting yesterday, and we're going to meet again, the board of directors of the organization, with the JLab management. The meeting is going on, so I can't exactly tell you what we've been talking about or the highlight of the meeting, but our agenda is here. And if you're interested, this is on our wiki. You can look more at it. And that's all I had to say. Well, yeah, I can say one thing that we talked a lot about yesterday was the balance between running the JLab 12 GV and preparing the EIC is something that we've been talking a lot. Please go ahead and add your non-governmental email address on this mailing list that we're having, and we're welcome to hear about your concerns and your ideas for the organization. Thank you.
Thank you, Juliette. Any questions, comments, remarks, impressions, concerns? Well, if not, I would like us all to thank Julie again for her dedicated work. I had the pleasure to work with her in the past year, and we owe her a lot for moving forward with some of the issues that have been stagnant from the past. So thank you, Julie, and I hope we continue collaborating. Now we are for a treat in the next two talks. I welcome Andrea Signori, as you know, the winner of the postdoctoral prize of JSA, who is going to talk to us about his winning research on hadronization.
Thank you. So I'm very happy to be able to share these research lines with you today. And I'm also very grateful to the board of directors and JSA for this award, of course. So I'm going to tell you something related to hadronization and why I believe it's important for the Jefferson Lab Physics program and important in general. So we're going to go through like a few concepts related to hadronization, and then the way we study hadronization, which is fragmentation functions, why some kinds of these fragmentation functions, which are called the transverse momentum dependent TMD fragmentation functions, are useful for the CDS program at JLab, and also like what we can understand about these functions from other experiments, including E plus E minus annihilation and also more. And then I will also touch briefly like a new look that we can give at the chiral load sector of hadron structure and hadronization. So with hadronization, we mean like a dynamical, non-perturbative transition from a quark or a gluon, which is a colored object, to a colorless hadron. So it's a mechanism which is dynamical. It's really related to the QCD interactions. It's directly connected so to the dynamical generation of some of the hadronic properties like the mass, the spin, and the size of the hadrons. It's also related, of course, to the confinement of quarks in the bound states and to the chiral symmetry of QCD. So it's one of the most interesting phenomena that we can study in QCD. So hadronization is also interesting from the practical point of view, because whenever you do scattering experiments that involves quarks and gluons in the hard interaction, then you're going to have hadrons in the final stage, or you're going to have the hadronization part following like the hard scattering event, if you forget for a moment about the top quark. So studying hadronization is extremely important, both at the fundamental level, but also at the practical level, if you want to understand like your scattering experiments. And also, this brings me to like the JLab case. So at JLab, we are after hadron tomography in momentum space, but by means of a process which is intrinsically a convolution of hadron structure and hadronization. So in semi-closed DIS, your cross-section will be sensitive to like the yellow part here, which is the hard interaction, but we don't, I'm not going to worry too much about this part because we know how to calculate it. So it's difficult, but we know how to deal with it. And then we have the hadron structure part here and the hadronization here. So the goal would be to break this correlation or understand how to reduce the dependence of hadron structure from hadronization in looking at the experimental data before actually going to analyze JLab 12 GeV data or even the electron-ion collider data. So one of the tools that we have to study hadronization are fragmentation functions that can give us like a probabilistic interpretation of hadronization. So you can define in field theory your fragmentation functions by means of an operator like this, a two-point function. And diagrammatically, it's like this kind of object where you have a quark in the initial state, which like fragments or something happens generated by the dynamics of QCD, and you get to have a hadron which goes to the final state with momentum pH and spin SH. And then the yellow blob here is like whatever happens which is generated by hadronization and you don't observe. Okay, so if you take specific integrations of this two-point function here, you can define your transverse momentum dependent fragmentation functions. They are transverse momentum dependent because they depend both on the collinear momentum fraction Z of the quark, but also on the transverse momentum of the hadron, the transverse momentum generated by the hadronization. So in a specific approximation that we call the leading twist, you have 8 TMD fragmentation functions. Okay, so depending on the hadron polarization or the quark polarization. And in principle, you can give a similar scheme also for quark to dihedron fragmentation functions. So if you have a quark which fragments into 2 and you observe 2 hadrons instead of 1, these objects are a bit more complicated, and we're not going to worry about that now. And also for gluon to single or dihedron fragmentation functions. So you can come up with fragmentation functions also if you have a gluon in the initial state rather than a quark. So Why these functions are important in our case? So at JLab, as we said, if we study semi-inclusive DIS to study hadron structure in momentum space, we basically observe a convolution of structure, hadron structure, and hadronization. And in mathematical terms, this means that the cross-section is a convolution of a transverse momentum-dependent parton distribution function and the transverse momentum-dependent fragmentation functions. And so you have your photon, which selects a quark out of the target. This quark has a specific transverse momentum, K-perp. Then you have your hard interaction, and before the quark, before arriving into the final state, becomes a hadron. And the hadron acquires a transverse momentum, P-perp, during the hadronization process. So what you observe, thanks to this delta function here in the cross-section, is PHT, which is the transverse momentum of the observed hadron, which is always, say, the sum of the quark transverse momentum in the target and the hadron transverse momentum, which is generated during hadronization. So you're always measuring, let's say, the transverse momentum of the hadron, a specific number, and you can interpret it as a sum of two different things. And of course, you can increase one and decrease the other, or vice versa, and you always get the same result. So there is a strong anti-correlation between the transverse momenta that you can measure in a CDS event. So we have extractions of the TMD fragmentation functions in TMD factorization from CDs especially. But they are correlated with the form, the functional form that you choose for your transverse momentum dependent PDF. So we need to do something about it. A visual example of what I was talking about is the following. So in this plot, you can see different extractions of the width, the average transverse momenta, the width for the K-perp, which is the transverse momentum of the quark in your target, and P-perp square, which is the average transverse momentum generated during the hadronization. So I want you to focus for the moment on the yellow blob here, which is an extraction of these quantities only from data for semi-inclusive DIS. So what you can see immediately is that these two quantities here are extremely anti-correlated. It's what I said before. If you can increase one, you can decrease the other because you measure the sum of them. Now, if you look at the red blob here, you can see that the anti-correlation decreases a little bit because what happened here is that in the fit we included also data which are related to Drellian events. So data which are purely sensitive to parton distribution functions. So by including that, you can decrease a bit the anti-correlation. But what we would like to do is to have data from processes which are purely sensitive to fragmentation functions, to hadronization, in order to completely separate the two effects. So we need to study TMD fragmentation function from this kind of processes participated only by hadronization. And one example of that is E plus E minus into two hadrons. So in this figure here, you can see like this kind of reactions in a frame where one of the two hadrons, P2, is collinear, has no transverse momentum, and you measure the transverse momentum of the first hadron with respect to this plane. So you can also go to another frame where P1 and P2 are both collinear, and the transverse momentum dependence is in the photon, in the intermediate particle. In that frame that we call the hadron frame, the cross-section differential with respect to QT, where QT is the transverse momentum of the photon, is a convolution of two TMD fragmentation functions. So we have only hadronization in the final state here. So this is something definitely interesting for our purpose. From the theory point of view, we like this process because it's TMD factorizable, we know the proof, and this means that we can control very well the approximations that we are making. We know that in specific kinematic regimes, if we write the cross-section in this way, we are not making a huge mistake. So we know how to control our approximations. Also, the perturbative part of your TMD fragmentation functions are quite known, they are known quite well to, let's say, order alpha strong square in perturbation theory. And also something that we started working on is to complete the formalism for studying this kind of cross-section. Now we know how to calculate this cross-section at low transverse momentum, so by means of TMD fragmentation functions, but we want to extend the same formalisms to the large transverse momentum region, where you have to use collinear factorization and collinear fragmentation function. So for the experts in the audience, we are trying to build the W plus Y prescription to match the two transverse momentum regions for this process here. So from the experimental point of view, we don't have data yet, or we don't have published data yet, but we know that analyses are on the way, for example, in the Bell collaboration and also at BES-free. But for the moment, so if we want to test if we are doing something right, or if our calculations are off by an order of magnitude or so, we can use a Monte Carlo event generator like Pythia as a proxy for the real data, and because it has been trained on lab data, so we know that more or less qualitatively it can give us the right picture. So combining theory and experiment, we will be able to extract these TMD fragmentation functions. That's one of the goals of this research project, and which I believe is an important contribution to the CDS program at JLab. So let me now remind you what we mean by extracting TMD distributions from data. So TMD distributions are interesting. They're kind of weird because they contain both perturbative and non-perturbative contributions. So here in this slide, I am writing down the solution of the so-called evolution equations for the TMD fragmentation functions. And in these slides, you see the ingredients of the TMD that you can calculate in QCD, in perturbative QCD. So we have an evolution. So these evolution equations, first of all, they tell you in mathematical terms how much the picture changes if you change the resolution of the probe that you are using in your Hart scattering event. So if you're shooting a picture of your target with a CDS event, and if you change the Q square of the photon, these equations tell you how it's going to, let's say the non-perturbative hadron structure and the non-perturbative hadronization, how they are going to change with the resolution of the picture you're taking. So you have two different variables in which the TMD fragmentation function or a TMD PDF evolve, because you have two different kinds of divergences that you can renormalize. So the first one is the evolution in the mu variable, which is coming from the renormalization of the ultraviolet divergences, whereas in the zeta evolutions tells you is coming basically from the renormalization of the so-called rapidity divergences. Another thing you can do is to take the distribution at the initial scales, mu I and zeta I, and expand it on the basis of the collinear parton distribution or fragmentation functions. So you can match the TMD to the collinear distributions, and this is important. So the gamma F, the K, and the C quantities are the ones that drive the evolution, and they are calculable in perturbation theory. Whereas when we want to extract TMDs from data, what we are after are the non-perturbative contributions in these formulae. Basically, the G sub K function, which corrects like the evolution kernel K at large separation or small transverse momentum in a sense, if you want, and also the factor here that corrects the expansion of the low BT, the expansion of the input distributions, and basically represents the intrinsic transverse motion of the quark or the gluon. So the quantities GK, the function describing the intrinsic transverse momentum distributions, and also let's say the collinear parton distribution function or fragmentation function represents the non-perturbative structure that you're after. And the fact that you have also the collinear distribution here reminds us that in the future we will need to think about extracting collinear and TMD fragmentation functions or PDFs together from like a global data set. They are intrinsically related for this reason. Okay, so I believe that not only E plus E minus into two hadrons is an important process to study hadronization, but also jet physics can offer interesting possibilities. For example, if you, at an electron-ion collider, we will probably be able to do jet CDs. Namely, instead of tagging one hadron only in the final state, you could observe like a collimated spray of hadrons. And I think it's nicely described in this paper here, and you can have a look if you want. The jet itself is also a rich hadronization lab in the sense that you could, if you have the power to do so, for example, I think they are able to do so at LHCb. You can tag the quark in the initial state, and you can also tag the quark in the hadron in the jet. And then you can do interesting studies related to, for example, the flavor decomposition of the hadronization mechanism, or in-jet hadronization studies, which are going to be interesting, for example, if you want to test the universality properties of fragmentation function and the revolution properties. So this is another part that probably we will touch in this research proposal. So talking about jets naturally leads me to the last topic of the talk, which is a new look at the chiral load sector. And we would like to get to it by using a jet, which is, say, a fully inclusive version of the jet that I was talking about here. So in this case, you see that you have an axis, a jet axis, and probably an algorithm that defines the radius and the cone, which basically tells you what's inside and what's outside of the jet, how many hadrons are going to be inside the cone and how many hadrons are going to be outside. You can also think about having a jet which is very large and encompasses all the hadrons that can be produced from the quark. And that object is very similar to the cut quark propagator. Namely, if you focus on this diagram here, which is basically the cross-section for deep and elastic scattering, you see that the quark which flows in the final state has a blob here that you could think about. You could think about this blob as the dressing, the QCD dressing of the quark, but also has the, let's say, the fully inclusive hadronization of the quark. So all the hadrons that can come from the quark itself and cross the cut. So they go actually into the final state. So this object here emerges in DIS at large X, because the scale that you find characterizing this object in the factorization theorem is Q squared times 1 minus X. So the blob becomes non-perturbative at increasingly low Q and large X. So it could be something interesting, definitely, for the JLab kinematics for semi-inclusive DIS. So one of the interesting things of this fully inclusive jet is the fact that you can relate it to the correlator that we introduced at the beginning of the talk for describing the fragmentation of the quark into one hadron. Basically, if you take this correlator for single hadron production, and if you integrate over the hadron momentum and you sum over all the hadrons that you can produce, you get the quark propagator, which is very interesting because it can give you momentum sum rules for fragmentation functions. One of the momentum sum rules that we like most is the sum rule that involves the scalar projections of these correlators here, and leads to the so-called mass sum rule, where you have the integral of the E fragmentation function, which is a twist-free chiral load fragmentation function, being related to an object that we call like the jet mass, or like something like a color-screened quark mass, which is nothing else but the average of the produced hadron masses, MH, weighted by this chiral load fragmentation function. So this jet mass is not, you shouldn't think about it like that's like the invariant mass of the jet, but it's something related to the chiral load structure of the jet itself. So it's something really different. It can also be negative in principle. It shouldn't be, we don't know yet if it's a positive or a negative quantity. So the nice thing, though, is that you can separate this quantity into different components, into a current and a dynamical component. So being a twist-free object in QCD, you can use like the Dirac equation, and the QCD equation of motions gives you a relation between the E and like the twist-2 and the twist-free dynamical fragmentation functions. If you do a specific approximation, which is called the Van Zura-Wilczek approximation, and you neglect the purely dynamical components of the twist-free part, you immediately understand that the jet mass is equal to the current quark mass. So it's a tiny object in principle. But this suggests you that if you don't neglect this truly dynamical component, then your jet mass can be equal to the current mass plus something else. And this something else is the integral of the twist-free dynamical fragmentation function. So why did we do this? Why is this important? So it's important because it quantifies, really with a quantitative relation, what we usually say, namely that hadronization is related to chiral symmetry breaking and to the dynamical generation of mass. This quantity here, this MQ that we call the correlation mass, because it's generated by the gluon quark correlation, probably is not going to vanish in the chiral limit. So it can be an order parameter also for chiral symmetry breaking, which is something very interesting. So you can study some rules like for fun if you want to think about the chiral symmetry and the structure of hadronization, but you can also apply this machinery to scattering experiments and cross sections in the following way. So if you have a process like semi-inclusive DIS, these momentum sum rules allow you to understand what's going to happen if you integrate over the hadrons that you are detecting, over the momentum of the hadron that you are detecting. So it's interesting, but it's very challenging because you have to work at least at twist 3 in the chiral odd sector. So it's something that we really we really don't understand very well from the theory point of view. And I believe there is a lot of work to be done, but the reward is probably very nice. So in collinear factorization, you can have your semi-inclusive DIS process, and at twist 3, you have a contribution to the cross-section which is proportional to the transversity PDF, coupled to the E tilde, the dynamical twist-free fragmentation function, unpolarized. If you apply the sum rule that we discussed in the previous slide, what you obtain is that in inclusive DIS, you have a contribution which goes like the transversity PDF convoluted with this dynamical mass. So this is a new effect that was not supposed to be there. We didn't know that you can have this kind of mass corrections in inclusive DIS, dynamical mass corrections. And it can have a contribution to the G2 structure function, as it was discussed some time ago by Alberto Accardi and Alessandro Bacchetta. And also it was mentioned like in the first day of the meeting by Whitney Armstrong, that he was presenting the results for the D2 matrix element. So in principle, you can do a similar thing for E plus E minus into two hadrons, where you have a transversity fragmentation function and the chiral odd E tilde fragmentation function. And again, you get, for the one particle more inclusive process, you get a contribution which goes like the transversity convoluted with the dynamical mass. But also you can do it for dihedron fragmentation functions, and eventually you end up with the interference fragmentation function and the dynamical mass. You can also do it in proton-proton collisions if you want, but I think we don't know the cross-section of a twist-free for this process yet. So this is just speculation. But as you can see, there are many things that we can explore, and it's a matter of like manpower and work time. So also, in order to make quantitative predictions, we need to go through the factorization theorems for these processes, which is like a non-trivial task. So with the funds awarded by JSA, what I'm planning to do is to support one or two students who want to contribute to this research line. And I think we can support up to 4 months in total, so it could be like good for a couple of summer projects, say. And there are both theory-oriented and phenomenology-oriented projects in this research proposal. So, of course, if you're interested, feel free to ask. And we will also support visits of external collaborators to JLab, which is nice because you can bring in like more ideas and a broader perspective. So, concluding, I think I tried to convince you that hadronization is a fundamental aspect of QCD. it's also crucial from the practical point of view, and I think it's very important for the CDS program at JLab and also for the future CDS program that we understand hadronization very well before going to study hadron structure. So you can do really many nice things at the twist 2 level, but in the chiral even sector, but also in the chiral odd one by means of these some rules related to the dynamical mass and fragmentation functions. So I hope that we will be able to do a good job. Thank you.
Any of this phenomenology, like the dynamical mass, being applied to already existing data by somebody?
No. I mean, the studies of the twist-free fragmentation function and the dynamical mass, they date back like a couple of years ago. So it's rather new. And I don't think we have tried, I don't think there are like precise phenomenological analysis yet. I think there is, in the paper by Accardi and Bacchetto, they assume the dynamical mass is order, let's say, half of a GeV, and they try to understand what's the impact on the G2 structure function, but no more than that.
So you said that it's few years old, or rather new. What has triggered the introduction of that quantity? Did it come from some discrepancies with data, or?
So, actually, this object here, which is the master function from which you can derive also the dynamical mass, goes back to 1987. So it was studied by Professor Sturman in the context of DIS at large X, and then it was also studied in the context of effective theories by Chen and collaborators. But Accardi and Jianwei Chu here, they brought back this object in the context of hadron mass corrections. So that was one of the triggers, let's say.
So your first focus in this research would be to analyze E plus, E minus,
yes,
to get the fragmentation functions? Okay.
Hopefully.
Right. Please.
Do you have any concerns about factorization working well enough in these studies at our energies?
So one of the reasons I chose to start with E plus, E minus into 2 hadrons is because we know the factorization theorem there, the TMD factorization theorem. So I'm not concerned about factorization for that process. But if you go to, say, jet physics or like this kind of twist-free observable, then I don't know. For the moment, I am agnostic, but I don't know if factorization has been established at the same, with the same, let's say, precision, at the same level of accuracy. For sure, it's something we should look at before going quantitative.
Thank Andrea again. Congratulations again.
Thank you.
I'd like to, we are going now into the break. If we have any speakers from the next session in the audience, please come down and hold your talks before the session begins. Other than that, I think we have
First, I'd like to start off by saying thank you very much to the JSA users group and the users here at the lab in general for not only for allowing me or awarding me the prize. This is the result of my dissertation research at College of William & Mary, which I graduated back in August. And my dissertation was actually on 3 topics, but I'm only talking about 2 here, so to try and keep the time down so I don't bore everybody. But the 2 most interesting results from my dissertation are actually 2 first measured observables from the Q-week experiment. And these are the first measurements in parity violating and beam normal single spin asymmetries in elastic electron aluminum scattering. So moving forward, let me just give a brief introduction. It's been talked about before already at this meeting, but what is parity violating electron scattering? So we use the very powerful electron beam of JLab to basically take polarized electrons from the injector, accelerate them, and scatter them off of a target that happens to be a solid target in our case, aluminum. And what we're interested in is measuring essentially the amount of electrons that get scattered off in a given helicity state. And what that means is essentially the control that we have is flipping the spin in the injector of the electron, which is a sort of pseudo parity transformation. What does that actually do? If you compare the amount of electrons that you detect in some detector system in one given spin state versus the next given spin state post transformation, you can build this observable, which is called a parity violating asymmetry. What does this give you access to? Is the real part of the interference term between the electromagnetic and the neutral Z exchange scattering amplitudes. And these asymmetries, depending on the actual physical system that you're talking about, can range anywhere from a few ppb to a few ppm, parts per million to parts per billion. What's nice about this type of observable is there's many measurement systematics associated with measuring a cross-section go away because you're essentially measuring two cross-sections and common terms drop out when you form this observable. Moving forward, just to give also a motivation of what QWEIC was for the people who might not be as familiar with it. QWEIC was a precision test of the standard model. We were trying to measure, or in fact did measure, the weak charge of the proton. And that's done with longitudinally polarized electrons scattering off of a liquid hydrogen target. And the idea is that by doing these asymmetry measurements gives you access to this weak charge parameter after performing several theoretical corrections. And if you see any deviation this from the standard model predicted weak charge, that might be an indication of new physics. And there's many models that were suggested in literature what might cause that. So in fact, we did measure this on multiple occasions. This is to give people an understanding, it's on the order of about 200 parts per billion. And from that, we extract this weak charge parameter and actually an additional parameter, the fundamental parameter of the standard model, sine squared theta w, the weak mixing angle. From that, initially we had published in PRL about 4% of our data from the very, very early commissioning run that we took back in 2010 into 2011, if I recall properly. Finally published in 2013. And now, more recently, last year, we essentially published the final result from the entire experiment in Nature with the actual final uncertainties associated with our determination of the weak charge of the proton. Now, fast forward to why I'm talking about this. Essentially, in the QWEIC experiment, we used a liquid hydrogen target, and liquid hydrogen is notoriously pesky because it likes to go everywhere, so you need to keep it in some sort of cell. We keep it in actually an aluminum alloy cell. And so in order to understand the physics backgrounds that come from electron scattering off of this cell, we performed several what we would call ancillary measurements with aluminum alloy targets from the same material as the aluminum cell to be able to understand our backgrounds. From this data set, you're able to actually extract out other newly measured quantities, which I'm going to talk about now. So motivating this, the reason why this is sort of important is back in 2014, Chuck Horowitz at Indiana University performed a very nice theoretical calculation of a parity-violating asymmetry from electrons scattering off of aluminum-27. So one of the interesting things is that this is the first time this observable has been calculated, although other parity-violating nucleus measurements have been of interest to the lab before. For example, PREX2, which is running right now, is talking about parity violation measurement on lead, and then also CREX, which will be on calcium. Aluminum's kind of different because it's an odd-even nucleus, odd number of nucleons, and so it has sort of an asymmetric nucleon distribution, and so it gives rise to these interesting structure in the parity-violating asymmetry. What you see here, the blue line, is what you get for the Born approximation when you assume basically symmetric nucleus. But when you start to include the nuclear structure effects of an aluminum, you start to get a little bit of differences in this higher lab scattering angle. So our goal was, from this publication, was to be able to go through the effort and take our ancillary physics data, perform the analysis to extract out the elastic aluminum parity-violating asymmetry. And so, what does it really mean to talk about a parity-violating asymmetry on a nucleus? Well, how do you get there? Well, I already explained sort of how we measure at least a parity-violating asymmetry. In terms of parity-violation electron nucleus scattering bigger than the proton, you are essentially measuring this observable, which gives you access to the ratio of what we would call a weak form factor, which is the weak analog to the electromagnetic form factor that has been measured for many decades. In particular, since we know the electromagnetic form factor of aluminum, it gives us access to the weak form factor of, weak form factor at a given Q squared. In reality, if you follow through sort of some of the basic math, it's really just in momentum space, it's a Fourier transform of the weak charge density, which can be expressed as basically the combination of the weak charge of the neutron times the basically neutron density inside of a given nucleus, and thus again also the proton's weak charge times the proton's density in the nucleus. Now, these are not really well known. You'd have to sort of experimentally determine them, even though we determine them sort of more in momentum space. But in theoretically, this would take on some sort of form. So you could assume one of the first order simplest forms for a nucleon distribution would be like something like the Wood-Saxon's form, where you basically have some distribution that falls off, and the width of this distribution is sort of given by this parameter r, which we would call a radius. This is very important because this is one of the final observables that we extract from our parity-violating asymmetry measurement here. Moving forward, the motivation, like I said, why are we interested in these types of quantities is, first of all, they're tests of relativistic mean field models. Importantly, since PREX is running, many of the theoretical calculations that go into that analysis, not the experimental, but interpretation of the PREX result earlier and hopefully here in the future once the experiment finishes up, requires theorists to perform calculations with relativistic mean field models. And so having an additional parity-violating asymmetry, which can then be compared to predictions from these relativistic mean field models of a lighter nuclei, gives confirmation that we understand if these models are actually predicting the correct results. So in Horowitz's paper, he made a few predictions. The parity-violating asymmetry should be on the order of about 2 parts per million, so much, much larger than the hydrogen result. With a proton distribution radius on the order of about 2.9 Fermi, and about a neutron distribution radius about 2.9, but a little bit bigger, 2.913, which when you take the difference between the neutron and the proton, there's a parameter in sort of low energy nuclear physics, which is called the skin thickness. And so if you're interested in sort of parameterizing the difference between these two radii, you often quote the difference in that, which shows how much the neutrons are moving beyond the proton distribution. For heavy nuclei, this can be quite large, like PREX. For aluminum, obviously, we naively expect it to be small. An additional thing, too, which was nice, is that by making about a 4% measurement on our asymmetry, that translates to about a 2% relative at the neutron distribution radius at our kinematics. So it's part of the motivation why we wanted to go through the effort of extracting out the neutron radius. Now, where was QEIC performed? Performed in Hall C, for those who may not know. We took background data with the aluminum target in 2 particular run periods, in 2011, 2012, with a 1.16 GeV. So this is the 6 GeV era, with a beam current of around 65 microamps and a polarization of about 88%. Now, what differs from previous parity-violating electron nucleus scattering measurements, such as PREX and PREX2 and CREX, is that we were using the QEIC spectrometer, which has a much, much larger byte sort of acceptance than, let's say, the HRSs in Hall A. So as a result, we cover quite a large theta range with a mean theta of around 7.6 degrees, but we have a large azimuthal angle coverage of about basically 49% of 2 pi. This gives us, when you actually calculate it out, our average Q squared is very, very low, about 0.02 GeV squared. And when you actually look at the actual energy byte that it takes in space, it's about 150 MeV, which is different than, like I said, PREX, which is able to actually focus down and have a very tight energy acceptance. So what did it look like? This was sort of a schematic drawing of what the QEIC apparatus looked like inside of Hall C. The electron beam would come in from the left and traverse across through here, come out the back end. Your target cans here. There's a bunch of primary collimators that collimate the scattered electrons before they get picked up by the Q-TOR toroidal magnet and then focused in a magnetic field onto an array of Cherenkov bars that are positioned here with these pieces of lead in front, which we call lead pre-radiators. Of course, shielding all the way around it to be able to try and reduce backgrounds. So what did the target actually look like, since this kind of differs from the QEIC liquid hydrogen target? In fact, we had a solid target ladder, which probably many of you are familiar if you've ever sat on shift and worked on other experiments, which was periodically injected during those times into the beam One of the more interesting things is that the aluminum target that we used is not isotopically pure. It had other alloy elements in it. The reason for that is because it's the same sample that we used for the aluminum alloy that was in the liquid hydrogen target cell. So we have other backgrounds that we know we have to correct for. Primarily, there's occasionally scattering from zinc, magnesium, and copper. I'll talk a little bit about those in the future. So what did all of our data look like? So after all of those 2 running periods, and you go through extracting those out and actually building your asymmetries, this is what your raw asymmetry looks like after you sign correct. What we mean by that is there's a few helicity controls that we have in the experiment, i.e. ways that we can change the helicity. There's a fast reversal, which get averaged together. There's also slow reversals as well, which occur either in the injector area by doing multiple methods, i.e. Changing the precession or the spin of the electron with a magnetic field, or before the electrons get produced with an insertable half-wave plate into the injector laser. I'm happy to answer questions for people who are interested. All total, looking at the raw data set, you see about the average is about just under 1.5 part per million. So it's on the order of what Horowitz had predicted in his initial 2014 paper. And the statistical power that we had with our asymmetry is about 4.7% relative. So how do we actually extract out the information, the actual pure parity violating elastic aluminum asymmetry? Well, first we have a bunch of measurement-based corrections which tend to be small. These are on the orders of parts per billion because the JLEIC collaboration went through great effort to minimize these for the liquid hydrogen experiment, and most of those types of systematic corrections carried over to the aluminum analysis. I won't really cover many of these today because I think the more interesting thing are actually how we go from a measure to correcting for backgrounds from other types of scattering because we have such a large energy acceptance. And so I'll focus on some of this. So once you have an A measured, corrected for many part per billion level sort of asymmetries, you can then correct for false, basically background asymmetries that come around from quasi-elastic, inelastic scattering, and so on and so forth. And in the end, after you apply all these corrections, including a small acceptance correction in front, you essentially get your elastic parity violating asymmetry, which is the quantity of interest. So the way that I performed this in my dissertation is the fact that there was many inputs into this calculation because we have quite a few backgrounds. So one of the ways to be able to propagate on the uncertainties was to actually apply a Monte Carlo method by randomly sampling from Gaussian distributions of inputs. And so it's one of the more interesting things. You can see sort of here how the final output value gets calculated. It is a sort of basically a Gaussian distribution. One of the nice things is, like I said, it reduces the effort of me trying to go through and do all the partial derivatives, which was nice. But in the end, after you apply all the corrections, you get an elastic parity violating asymmetry around 1.9 parts per million with a total uncertainty of about 0.173. All total combined statistics and systematics, it's about a 9% measurement, which is quite good for being the first time it's ever been measured. And how does this look like compared to Horowitz's theory that he published in 2014? It's basically published at our mean average scattering angle here. If you look at the inset of the plot up top here, you can see that we're within our error bar within the theoretical model, so we're in very good agreement, which was refreshing to see. So from that next step, talk quickly about some of the dominant systematics in the analysis. One of the biggest ones was the inelastic asymmetry. This primarily comes from inelastic scattering effects and non-quasi-elastic that were treated separately. They have the largest, they're the dominant uncertainty in all this analysis, even larger than statistics. And if we were able to reduce this down below that of statistics, we could almost be statistics-dominated measurement, which is quite nice. Some of the other leading ones were the quasi-elastic contributions, the asymmetries coming from scattering in the zinc, alloy elements, and the magnesium. And like I said, combined comes out to the 0.173 that I showed previously. So how do you actually go through and calculate some of these quantities? A background fraction, in a sense, is a ratio of an individual scattering process that you want to correct for, such as inelastic scattering, You have to come through with a model, which we put into our Geant4 Monte Carlo code, which essentially has a one-to-one representation of what our magnetic optics are, our magnetic field, our spectrometer, and how it operates. We try to calculate sort of the signal that we get in our detector, and then we create ratios out of the total sum of all of the different types of scattering processes we believe are occurring. So to give an example here for quasi-elastic, inelastic, which are some of the largest, the quasi-elastic is approximately about 12% of our signal comes from quasi-elastic scattering because we have such a large energy bite. Inelastic scattering is a little bit lower, but as you'll find, the asymmetry really causes a large systematic uncertainty. So where do the asymmetries come from? In particular, quasi-elastic scattering in this sort of regime, at least a asymmetry has yet to be measured on aluminum. So we were forced to actually go to Chuck Horowitz and his graduate student, Zaidu Lin, to be able to perform a relativistic Fermi gas model to come up with an asymmetry estimate, which we applied a conservative uncertainty to. This agrees well with a free nucleon estimate. If you were to just take basically the asymmetry you get from scattering off of a neutron scaled by the number of neutrons in a nucleus and the number of protons without any sort of final state interactions or medium effects, which is good. In inelastic scattering, we actually had some data that we took separately, but it's statistics dominated. So we ended up using the asymmetry extracted from those measurements, and this is where that large uncertainty comes and becomes the dominant uncertainty in our analysis. Once you fold it in with the actual background fraction that reduces this contribution down when applying the correction. We're still working on updating one or two missing things in this number, which will cause us to change and slightly inflate this uncertainty. It's a work in progress. I mentioned, how do we make corrections for the aluminum alloy elements? Well, first, thus again, most of parity violating asymmetries on some of these other nuclei are also not measured. So we were forced to go back and try and get theoretical predictions. So we spoke with Chuck Horowitz again and collaborators, and he was able to come up with not only cross-section predictions for us, but also parity violating asymmetry predictions. We were able to fold these into our Monte Carlo simulation and come up with predictions for what each of the backgrounds from scattering, at least elastically scattering from each of these backgrounds, contributes to our analysis. Again, we provide, apply very, very conservative uncertainties on the asymmetries and the cross-sections. They're probably good to better than 10%, but a conservative approach was taken just simply because we weren't considering any other, sort of quasi-elastic or inelastic scattering from off of these elements. So now that we had that parity violating asymmetry, one of the things that we wanted to do was actually extract out this neutron distribution radius. So working again closely with Chuck Horowitz and Zaidu Lin in Indiana University and Farouk Fatev, they came up with a collection of 11 relativistic mean field models calculated at our kinematics. These models were selected because they produce a bunch of, they match binding energies seen in many nuclei known that have been measured before, charge radii that have been measured before from electron scattering and from other methods, isoscalar, isovector giant resonance sizes, which have been measured before. And more importantly, this is spawned off of work that they're doing, tying these observables to neutron star masses. When you do that, and here are the name of the models here, you can essentially plot them and then come up with a correlation between the RNs that they have, that the models predict, and a parity violating observable. And so what's nice is we can take our measurement, insert it here, and calculate out what our RN is. When you do that, you come up with an RN around 3.024 with the uncertainty coming from the total systematic and statistical from the actual asymmetry measurement, and then a little bit additional from the fit. In the end, this is a determination of R relative RN of the relative uncertainty of RN, 3.4%. So how does this procedure actually look graphically? So thus again, here are the collection of the models. Here is where we took our 1.92 value. You basically run it up, and we run it up, and then you read off what RN is. The shaded regions here, the inside shaded region is the statistical error, and the outside shaded region is the total error from your asymmetry, and you see how that basically folds into your determination of RN. So we're just within 1 sigma and some change of the models that Chuck and collaborators provided us. You take it one step further, if you have a prediction for your neutron, for your proton distribution radius, which came from a collection of models, you can actually calculate that skin thickness parameter, which is important for low energy nuclear physics. And so what's nice about this is that even with our uncertainty, essentially this value is small enough, it's close to 0, it's consistent with 0, it's what you expect for aluminum-27, which doesn't have a large neutron excess, such as like lead. The RMF models themselves are able to predict the skin thickness parameter, and they predict a range of values that are close to 0. So it's quite interesting. Shifting gears in the time that I have left, I want to cover over beam normal single spin asymmetries, the other observable that we also had data for. These are known as transverse asymmetries. And instead of having longitudinally polarized electrons, we now use transversely polarized electrons to be able to gain access to the basically the imaginary double photon exchange amplitudes. So how does one actually measure these? Thus again, I say you have particles coming in with a spin in a transverse plane. You can also rotate that either horizontally or in the vertical transverse plane. And what that gives you access to is some asymmetry that you see in your detectors that has a sinusoidal variation. You'll see some data here in a second. What's nice about this is we're able to systematically study at least the spin of the electrons by setting it either vertical or horizontal, which allows you to sort of explore phase space a little bit more. One of the interesting things, the reason why we're trying to perform the analysis of these measurements is the fact that PREX, when it ran back in 2012 and earlier, 2010 I should say, and then published the results in 2012, they noticed for lead that the beam normal single spin asymmetry predicted for lead was way off the theoretical predictions, whereas their measurement of carbon happened to be pretty much right on theoretical prediction. There's a big jump in Z number between obviously carbon and lead, so there was a question about if any beam normal single spin asymmetries on nuclei and Z's in between carbon and lead might show any indication that there is some sort of need for an update or some physical phenomenon going on here that's not necessarily explained in current theory. So one of the things that if you look through the literature, we tried to be able to reinterpret this. There's some assumptions that go into this plot. What you're looking at on the vertical axis is the beam normal single spin asymmetry in parts per million, and basically how it evolves with atomic mass at A. So you have your HAPX points from earlier parity violating experiments that measured beam normal single spin asymmetries, but then PREX points out here, and you see lead's way off. Now there's some assumptions made in this plot. The kinematics for all these measurements are not the same. So these have all been scaled, Q-scaled to Q weeks, basically Q value. And you'll see why for a reason. But really what you're trying to look at here is that even when you reinterpret it in terms of A, the disagreement with a sort of naive theory, which is this sort of theoretical interpretation, a leading order of how those beam normal single spin asymmetries should go with Q, there's some relation between A and Z with some scaling parameter. And so if you were to plot basically the A to Z ratio and scale it by that scaling parameter for all, basically all major nuclei all the way up to lead, you see that, they would predict by this first order equation that the beam normal single spin asymmetry should be largely negative and not close to 0 or slightly positive like the PREX result. So our actual measured data looks something like this. I was talking about we actually were able to select out whether our scattering angle is horizontal or vertical. This happens to be from a horizontal data set. So you end up seeing 2 types of asymmetries here that are plotted. And you can actually take the you can subtract the 2 and see how well they cancel with the green line in between. Statistically, we have about a 4% measurement, but obviously there's large systematics. This is what happens when you sign correct it. You now get a nice sinusoidal, which you can then pull off the amplitude, which is your beam normal single spin asymmetry. And you'd have to go through a similar thing. You have to apply corrections, and then you also have to do background corrections. It's just like the parity violating case, but now obviously with transverse asymmetries. How do we actually apply these? We were using basically Q weeks beam normal single spin asymmetry measurement of hydrogen, which was also produced, a measurement was also performed by the collaboration. And then we also did an inelastic measurement where we changed our magnetic field down. Instead of having the elastic stripe on our detectors, we had the inelastic stripe. And so it allowed us to measure different types of asymmetries that I used in this analysis to try and essentially correct away any sort of inelastic contamination might be in the aluminum measurement. Unfortunately, aluminum alloy elements, there hasn't been that many beam normal single spin asymmetries on other elements. So we kind of had to use that A to Z scaling to make up approximate order of magnitude estimates of what the beam normal single spin asymmetries would be. And also, additionally, there are some other backgrounds from single particle excited states and the giant dipole resonance that we just don't know how to theoretically, correct for. So they've kind of left the final asymmetries left as an effective asymmetry, and we would welcome any theorist who would like to do calculations for that. In the end, after combining all of our data both in vertical and horizontal polarizations, you can come down to a beam normal single spin asymmetry in the order of -16 parts per million. This comes out to be at 11% relative measurement. Thus again, very similarly, the inelastic asymmetry is the dominant one here, followed by its fraction, background fraction, and the quasi-elastic pieces, and then the radiative corrections for these types of things. How do the actually points look? So here's that same plot again, and here's the aluminum point placed on it. So it's now much, much lower than what the naive first order scaling, A to Z scaling for these beam normal single spin asymmetries would predict. And then we did also additionally measurement on carbon, which agrees very well with the theory. So there's some questions about, if there are higher order effects that you have to take into account. And we've recently talked with a few theorists, in particular Misha Gorstein, who's updated a newer calculation for us, and I'll talk about that in a second. So to just quickly summarize, parity violating asymmetry, QEIC is basically, by making an aluminum asymmetry measurement, you can actually access the neutron distribution radius of the aluminum nucleus. And what's interesting about that is if you go one step further and actually calculate out the neutron skin, we find that's consistent with zero within our error bar, which is the naive expectation. But it's a good check for theoretical models that are important in lower energy nuclear physics, and then also for nuclear physics models that are important for neutron stars. In the beam normal single spin asymmetry case, we're hoping that maybe some of these results will spark interest in theorists to come back and perform more updated theory calculations, as some more observables are coming soon. And we would like to try and reduce down that inelastic uncertainty at some point. So, and we have two publications working on, two publications about both of these results that we're currently working on. Hopefully we'll have published in the next year. So thank you very much.
Very nice, thanks.
Thank you.
Questions?
I may have a question, but you don't need to give me the mic. So if you go back to slide 25, you are showing the signals for the in and out.
Yes.
You are showing that 24. You are showing that the difference between the two is consistent with zero.
That is correct.
Do you apply any kind of corrections based on this, or you are just including the green bars within the systematics?
Oh, I see what you're saying. So are you saying because we're not necessarily zero, is there a correction that shifts it back exactly? In this analysis, I don't think I exactly did that because it's basically almost consistent with zero, nor do you really have to, because we're more interested in just the variation of the sinusoidal. I mean, you still worry about an offset at some point, but the systematics that we have already in the measurement from the background corrections far dominate any effect that you would see there, I guess. This probably hopefully answers your question. So, yeah. It's a good question, though. Thank you.
Any other questions? Okay, let's thank the speaker again.
Hello? Can you hear me? So, just.
Next, Olga will tell us about omega meson, sigma beam asymmetries in photoproduction on nuclei, I guess.
Yeah. Thank you. So, the work that I'm going to present today was the result of what I did for my thesis. I graduated 1 year ago from Idaho State, and I was under the supervision of Dr. Philip Coy. So the review in general, how I like to introduce this is in the N-star, like all sort of hadron spectroscopy. So I would like to introduce why is this relevant to study the observables, the polarized observables for this. But I also would like to explain why we chose the omega meson for this work. But also, why are we doing this in the bound proton if we have already the free proton for the N-star context? And I explain how the experimental layout that we use in the G13 run group, the methodology to extract the sigma symmetry, and the results in the quasi-free region, and the discussion. So the motivation is, first, why will we want to study the baryon spectrum? So, in particular, the baryon spectrum and how the structure of that spectrum is going to give us is going to give us information of the underlying degrees of freedom in the perturbative regime. So we hoped that we had something beautiful and easy in our hands, but it was not easy. Here I'm showing what is the total cross-section for pi proton. And as you can see, this is not a bump hunt. So where I have bumps, in some of them I have several resonances, and when I don't have any bump, there are resonances. So it's not easy and it's not clear, like it was not clear at least, how are we going to go through this? So for that, we had to create this monster, which is this thing up here. With lots of collaborations and working together in order to get this spectrum. So how do we do that? So from different facilities all around the world, we are going to look at the observables, and we are going to extract polarization observables for different channels. And all, here with the cross-section, unpolarized cross-section, and the polarization observables, we are going to have to input these in different collaborations too of multiple channel analysis machinery. So here I'm just, I just put the baryon spectroscopy ones, but yeah, the one said that is the one from my university now at George Washington. So with those, I can extract the excited state parameters, and I'm going to compare those with both QCD-inspired models and lattice QCD. And hopefully, I left here my beautiful colored QCD apart from this because we still have to understand the whole thing. So why meson? Why omega meson? So here I'm showing the total cross-section of gamma p as a function of the energy of the photon. And as you can see here in this square, we have in green the cross-section for the omega. And for energies above 1.7 GeV, this starts to become relevant. And why is this relevant? Because we would like to understand this sector. So this at the beginning of, this is the 2016 particle data group. And the N-star region at the beginning is very well understood, but we will hope to understand the older one. Why omega again also? Because it's an isospin filter and only M stars are going to contribute as not delta stars. And that's going to simplify the analysis a lot. And it has a narrow, beautiful peak that is going to be easy for us to just extract something. And why I'm showing 2016, because I want you to notice what is the difference in between what we saw in 2016 and in 2018. So not only we got several more channels contributing, but also in omega has become really important and relevant in some of this area here that was where most of the changes from 2016 to 2018 happened. So why polarization observables if we have our unpolarized cross-section? So we have these many structures that we would like to understand, and non-polarized unpolarized cross-sections are going to give us information of or are related to the sum of the squares of our amplitudes. But the polarization observables are related to the phase, and in this case they are going to help us disentangle some of the structures that we would like to see. And as you see, we are going to be able to identify clearly or more clearly what is it that we are looking at. And for the polarization observables of the vector meson, the omega is a vector meson, we can calculate the single polarized, double polarized spin density matrix elements. But for the experiment that I did, we had linear polarized photons with unpolarized targets. So we are going to center in this one, the sigma spin beam asymmetry. And now, why do we do this study of the photoproduction of the bound proton? So, first of all, the method that we use, at least for understanding our Monte Carlo, or that we use in our Monte Carlo, was to consider the neutron to be on shell and the proton to be off shell. And this means that the higher the missing momentum, the missing momentum of the neutron in this case, the higher the probability that we are going to have final state interactions events. And we would like to answer the question of, or shed light on what is the effect of the off-shellness on the of the nucleon in the observables, in the polarized observables that we are looking. And since this is the easiest medium that we have, this is like the zero step to understand what is the medium starts and in which kinematic region we will start seeing effects for these observables. So the experimental layout is happening in Hall B of JLab. This is the old classics spectrometer. For our, we had this coherent Bremsstrahlung facility where we had electrons coming and real photons, tagged real photons coming into our 40 centimeter deuteron target, and then we will detect the final particles in class. One other thing that is important to say is that we got energies in between 1.1 and 2.3, and the coherent peak we said to be moving from 1.3 to 2.3 every 200 mega electron volts, the coherent peak. So I'm not going to go into the details. I just want to point out one of the differences for my analysis, and is that since I will not be able to detect the neutron, I will have to detect the two photons in the final state. So we have 5 final state particles. And what is this going to happen is that my statistics is going to drop as the number of particles that I will go. So for charged particles, we just did a simple PID cut and the delta beta momentum dependent cut. For the 2 neutral particles have very simple difference, and we detect the photon. So this is, as I said, like standard, and we corrected also. But so this is what we don't see, right? So the pi 0 we have to reconstruct with the 2 photons, and now, and this is one of the main cuts that it's important to understand, is that we did a cut in 0.2 and assume that the most of my events in these regions are going to be quasi-free. And that in this region over 0.2 is going to be final state interaction dominating. After that, I see 3 regions, or the omega events, the eta events, and the non-resonant background. So we slice this, and we did a fit over around this omega peak, and we took this as this region as the omega region. Of course, we have backgrounds under that, and we background correct this distribution. So now, how do I calculate the beam asymmetry? So we have 2 kinds of polarizations, perpendicular and parallel to the floor of the hole, and we calculate the difference of those distributions, like normalized. And we get this monstrosity, but this monstrosity is good because we can fix by other means these parameters, and in reality we just have 1 parameter to float, and this is like a really nice way to help your fix. I just want to point out that one of these parameters is the average of the polarization, and it's multiplying my sigma. So this is going to be one of the biggest sources of uncertainty. So preliminary results, in red I have my results for the quasi-free. In blue I have the results that, the only results that I'm aware of for quasi-free protons that was published in 2015 from grad collaboration. And this is the free proton from class from Collins in 2017. So let me first start by comparing my work with the other quasi-free work. So as you see, it's only just for kinematic beams in energy. And as you can see, the agreement is fairly good at the beginning, and it starts like going for low energies. As for when we move to the higher energies, the disagreement starts to be higher. And I think I have a reason, like I think I know why that happens. And on the other side, we have the free proton. This is a high statistics that was performed in G8, also class. And all our observables are small in amplitude for those. So I also have the Bongachina 2016 that will like show it includes the Collins data. So as for systematic uncertainties, I'm going to point out what are the sources of larger systematic uncertainties. So the mean polarization is the largest with a 5% contribution to that. But we also wanted to understand, and this is something that is very important to us, is to compare the cut at 0.2 and the cut at 0.15, and this is still big. I will say that if I do the cut in 0.15 GeV/C, I will obtain a higher purity, but my statistics get reduced a lot. So I had to to negotiate with my data. And finally, to conclude, so the omega channel is relevant, as I showed you, in the study of missing resonances, in particularly the N-star resonances. We extracted the beam spin asymmetry photoproducer of omega resonance from bound proton for energies from 1.1 to 2.3 GeV. The comparison with GRAL is well is good for lower energy beams, and as we move further, it's not as good. And I believe this is because I do not see any cut in the missing momentum of the GRAL results. So there is no differentiation in between which ones are quasi-free and which ones come from final state interaction, and those might be diluting their sample. Our results compared to free events reported by class collaboration are in general smaller in amplitude for cosine theta equal to 0 and around, especially. We estimate that just uncertainty for the cut, as I said, to divide my events, quasi-free events from the final state interaction events are 0.021. So I believe that I know that I have some final state interaction diluting also my sample, but as I said, I needed enough statistics in order to be able. And there are very interesting proposals at the moment trying to study photoproduction of mesons in medium in class 12 and LUEX. So I hope that interesting physics are going to come up. Thank you. Thank you.
Okay, thank you. Very nice. Questions? How long did it take to do the amplitude analysis that you did?
Like, well, so, like, what? I did not.
Yeah, you didn't perform the amplitude analysis?
No,
oh, okay.
I did not. Mm-hmm. Yeah, no. So the idea is to send it. So the idea is to send it to one of the Bongachina to be able. There is like some of the energy beams are not before, like have not been taken into account before. So that's the ones that we want to take into account. But we still have to understand how are we going to report the quasi-free and
okay.
as compared with the final state interaction. Yes.
Other questions? Are you going to be involved in the 12 GeV equivalent experiments?
I am involved now in LUEX. So it's barium spectroscopy, but not quite, yeah.
Okay.
So yes, now that's the future for me.
Okay, good. Okay, let's thank the speaker again, please.
Yes, yes. But yeah. Oh,
So next we will hear about interpreting short-range correlations by Rainier.
Hello, everyone. We used to describe nucleons and nuclei as particles that would act independently. And you could describe them to good accuracy as being affected by the average potential created by all the other nucleons in the nucleus. And some of these theories are, for example, the well-known shell model. And in this picture, in this single nucleon picture, you could interpret in momentum space, this would be the one-body momentum distribution, so the occupancy of momenta states, as a Fermi gas that would occupy all the states up to some Fermi momentum. Now, by doing spectroscopy, we found out that only about 80% of the nucleons can be described this way. And one of the current pictures that we have is that 20% of the time, nucleons like to get close together, and as a result of the structure of the nucleon-nucleon interaction, they fly apart with high relative momentum and low center of mass momentum. And that populates a high momentum tail above the Fermi momentum. So in this picture, we have a one-body momentum distribution with two fairly well-separated regimes, the mean field part below the Fermi momentum and this high momentum tail. And you may think, well, this is a 20% of the nucleons. Some things in nuclear physics we only know to about a 20%, so does it even make sense to study them? And so the quick answer to that is, even though these are 20% of the nucleons, they carry about over 75% of all the kinetic energy inside the nucleus. And so when they manifest, they have a fairly strong signature. So how would we go about studying short-range correlations and nuclear structure in general? There are several ways of doing this. One of the ways that you can pursue is you can solve the many-body Schrodinger equation. And to do that, you need to plug in a potential, and the nucleon-nucleon potential is a complicated QCD interaction. So it's not straightforward. So a way to do this, well, to get around solving this many-body problem, we can use some numerical technique, and I'm going to be talking about quantum Monte Carlo. And then something that you can do is you can replace this complex QCD interaction with some effective NN interaction that captures the physics that you want to study. So you plug in this potential, you solve the Schrodinger equation, you do quantum Monte Carlo, and you end up with different distributions. For example, this is the one-body momentum distribution. This is the same cartoon that I showed you before, but these are realistic calculations using 4 different potentials. I'm going to be coming back to these specific 4 potentials. And what you can see here, the vertical line is the Fermi momentum. So you have the mean field behavior below the Fermi momentum, and then you have the high momentum tail. And something that you can notice is that below the Fermi momentum, all these distributions predict about the same behavior. But when you go to high momentum, you have very distinct behavior across NN interactions. So that's also a good thing about studying short-range correlations, is that it can tell you about the specific short-distance structure of the nucleon-nucleon potential. And there are 2 main avenues that we can pursue for studying short-range correlations. We can do experiments, we can do theory, and so this is precisely the title of my talk. I was given this task to describe to you how to interpret short-range correlations using electron scattering data and this theory called the generalized contact formalism. My name is Ray Cruz-Torres. I'm a grad student at MIT, and I wanted to take a second to thank the organizers for this opportunity to speak here. So to jump right into my talk, I have divided it in 3 big sections. First, I'm going to describe to you what this generalized contact formalism is. Then we're going to apply the contact formalism to different nucleon-nucleon models. We're going to try and learn some physics from it. And as a third point, we are going to touch base between theory and experiment, and I'm going to be using this contact formalism to predict some observables and compare to actual data. So the contact formalism is an effective theory to describe short-range correlations in nuclei. And it relies on the concept of factorization. This short-distance pairing is expected to be so intense that the interaction between the 2 nucleons in the pair is very, very different from the interaction of the whole pair with the residual system, which allows for you to write the many-body nuclear wave function as a product of 2 terms. There's this blue function that describes the interaction of the 2 nucleons, and then there's this red function that describes the interaction of the 2 nucleons with the rest of the system.
And if you accept these for a second, it allows for you to calculate some quantities such as the two-body coordinate density. So this is the probability to find two nucleons with some separation. And this function, this is a nuclear function. This is for the whole nucleus, whether you're talking about helium-4 or calcium-40, you name it. The idea is that in the contact formalism, in the region where short-range correlations dominate, the claim is that you can express the many-body function as two terms. One, which describes the interaction between two nucleons, and then a constant, which tells you the abundance of these pairs. And you can do these for several pairs of nucleons, several spin projections, and whatnot. And you can, as I said, this is the nuclear two-body coordinate density. These constants are called the contacts. This is where the contact formalism name comes from. And this function is the solution to the Schrödinger equation for two nucleons. So this is something that you need to get with quantum Monte Carlo. I have no idea how to do that. That's for smart people to do. But this is a two-body function. So you solve the Schrödinger equation for two nucleons. You do it once. This is a universal function, universal across nuclei. And then you determine the abundance of short-range correlated pairs. And the product of these two functions, the claim is that it can describe this many-body function. You can do this in coordinate space. You can also do it in momentum space. Same mathematical structure, just now relative momentum. And so to try and demonstrate this to you, what I'm showing here are two-body coordinate densities calculated using quantum Monte Carlo for a variety of nuclei from tritium all the way to calcium-40. And so you can see two distinct regions in these distributions. And by the way, they all have different normalizations. We chose to normalize them all to have the same height at 1 Fermi so that you can see them all in the same plot. And so you can see two distinct regions. There's this region above 1 Fermi in which all nuclei have very different behaviors. And then you have this short distance part in which all the nuclei collapse to the same behavior. So again, the claim for the contact formalism is that this two nucleon function times the abundance of pairs can describe this region here. And so if I add to this plot the solution to the Schrödinger equation times this constant that we call the contact, this shows you basically that while we cannot describe the long distance part, the short distance part where short range correlations dominate can be fully described with this formalism. This is one potential, AB18. I showed you before 3 other potentials, so we can repeat the same exercise for different potentials. And so if you try to compare AB18 with N2LO 1.0 Fermi cutoff or with this one, you can see that the short distance behavior is very different across interactions. But for one interaction, all nuclei behave the same at short distance. And I'm actually here, it's not as clear as in the previous slide, but the black line here is the nucleon-nucleon wave function. So we would have to calculate these, and by that I mean solve the Schrödinger equation for each specific potentials. So what we would do is we would fit the right-hand side of this equation to the left-hand side in the pink area in all these plots, and that would give us the abundance of pairs or the contacts. This is at short distances. We can independently repeat the exercise at high momentum. So these are the corresponding functions at high momentum. And here I'm actually showing the ratio of the two nucleon wave function and the whole many-body function. And the reason why I'm showing the ratio is because these functions in momentum space decay exponentially. So it's just so that you can see it in the plot. And so you can see that at high momentum, we have these scaling region. So again, we fit the contacts independently in coordinate space, in momentum space, and we can extract these abundances of pairs. So we did that exercise for all these nuclei, and again, individually in R space, in K space, and this is what we end up with. So we have PN pairs with spin 1 on the top plot, PP pairs with spin 0 on the bottom, NN with spin 0, or PN with spin 0, which would be all the pairs that we can form, are equivalent to these. So as long as you have spin 0, you have this behavior. And we're plotting these for different nuclei. The squares are contacts in R space, the circles are in momentum space, and then the colors are for different interactions. And there are a few things that we can learn from this plot, but I don't have the time to do it. I just want you to remember that, for example, all these red points are systematically below the rest, and that will come in handy in a couple of slides. But something that we can do is we can take these quantities and we can plot them differently and do different things with them and try to learn some physics. So let's do that. For example, we always wave our hands and say that these pairs come from a short distance behavior that translates into a high momentum behavior, but that's a very qualitative description. This is to put it in some quantitative ground. So here we're plotting the ratio of Pn spin 1 in R space and K space. So we extract the contacts at short distance, we extract them independently at high momentum, we take the ratio, and you can see that within 20%, this ratio for all nuclei that you see here is consistent with 1. And if you look at the case of spin 0, for many of these points, they are also consistent with 1. You can see that there are some outliers. That's something that we are going to study in the future. It's not clear at this point whether it is an issue with the quantum Monte Carlo calculation or whether there's some physics there. But these are, as you heard in Deanne's talk before, we have predominantly more Pn spin 1 pairs than any other type of pair. And so you can see the short distance, high momentum correspondence. Something else that we can do with these constants is you can take the ratio. For example, in this plot, I'm showing the ratio of any nucleus over deuterium for Pn spin 1, the ratio of Pn spin 1 of any nucleus to helium-4, and then Pp spin 0, any nucleus to helium-4. And what you can see here is, as I said in a couple of slides, the red points were systematically below, and that's because different potentials have very different behaviors at short distance and high momenta. However, when you take the ratio for a given interaction of one nucleus to deuterium or helium-4, you can see that these ratios are completely insensitive within error bars, insensitive to whichever interaction you chose. So what can we learn from these? There's this category of experiments that was described yesterday by Efrain and Florian and also was mentioned by Deanne today, in which you do inclusive scattering and you extract the cross-section for a given nucleus over deuterium and you plot that as a function of x. And then when you look at x greater than 1, you see a plateau, and that plateau corresponds to short-range correlation dominance. And you assign the height of this plateau to the abundance of pairs. So if you compare these plots, this is A over D, this is A over D, abundance of pairs, abundance of pairs. And the fact that for dramatically different nuclear-nuclear interactions, you obtain the same abundance of pairs tells you that inclusive experiments cannot teach you about the specific details of the short distance structure of the nuclear-nuclear interaction. And it also tells you that the abundance of pairs is a property of the mean field and not of these tails. So if you want to learn about the specific structure of the NN interaction at short distances, you can do what's called exclusive experiments. For example, you can count how many times you get proton-proton pairs and how many times you get proton-neutron pairs as a function of the initial momentum that the nucleon had. And this is an extraction that was done in Hall A in 2014. And you can see that this exclusive data gives you some discriminating power. And it tells you, for example, that the AV4 prime nuclear-nuclear interaction is not nature's nuclear-nuclear interaction. So we can learn about this structure with exclusive experiments. So this is the contact formalism we have found in our group and outside a few applications to it. I don't have time to go into them, but I'm leaving these as reference if you guys are interested. I wanted to take a moment, though, to talk about this specific application of using the contact formalism to calculate cross-sections. And for a second, I'm going to take a lateral step. This is not related to all the things that I've been talking about. This is more general. And the idea is that you can write, in the plane wave impulse approximation, you can write the electron E prime P cross-section as a product of the elementary electron-nucleon cross-section times a spectral function. There are several well-known, well-documented prescriptions for the electron-nucleon cross-section, like the Forest cross-section. Spectral functions are a little bit trickier. And the spectral function is the probability to find a nucleon inside the nucleus with some momentum P and some energy E. Also in the plane wave, if you assume that the transferred photon couples to only one nucleon in the nucleus and that nucleus as it comes out of the nucleus doesn't re-interact, then you can parameterize the initial nucleon momentum as missing momentum.
So if you determine missing momentum from your measurement, then you can have a say on the behavior that the nucleon had before the interaction took place. So how does this picture comes back and ties together with the contact formalism? Well, there's a prescription in the contact formalism for this spectral function in the regions where short-range correlations dominate. And so you can make use of the same contacts that I showed you. You can make use of the same nucleon-nucleon wave functions that I showed you, and you can calculate the spectral function. The only additional ingredient in this equation is this function which describes the motion of the center of mass of these pairs. And I don't have the time to go into detail, but I just wanted to leave this reference here and tell you that it has been measured, it has been calculated, we know it. So we have all the ingredients that we need to calculate a spectral function with the contact formalism, which means that we have everything that we need to calculate the cross-section. So now we need some data to compare this cross-section to. And so we have EG2 data from class. This is an experiment that ran a few years ago. It's a 5 GeV electron beam on carbon, aluminum, iron, and lead. I'm going to be showing some results for carbon. And we have the class detector, which can, so this was the class 6 detector, which could potentially see anything that you threw at it. So we have the data. And so what we now need to do is we need to take the contact formalism, calculate the cross-section, generate many, many events that follow this cross-section. And then we apply some corrections, such as radiative correction to the generated events. We apply some additional corrections, such as transparency and single charge exchange. We take into account the fact that the detector acceptance is not perfect. And last but not least, we apply to the generated data the exact same event selection criteria as we apply to the data itself. And so if you take all this into account, you can plot the number of counts for E prime P or E prime PP as a function of missing momentum. So again, this is the proxy for the initial momentum that the nucleon had before the interaction. Of course, it has to be above the Fermi momentum because we are using a formalism that only works for short-range correlations. And this is what we get. Now, there's a floating, there's an imposed normalization here to make sure that all the curves have the same number of counts. So we're only comparing shapes. But you can see that the data prefers the AV18 potential over all the other potentials. And something else that I want you to notice, so first of all, this is not work that I can take credit for. This specific work was done by Axel Schmidt and others. And so it might be in my naive mind, but I find remarkable that this data goes all the way up to 1 GeV. These are nucleons inside the nucleus moving at 1 GeV. So if you want to go away from that forced normalization that we impose to compare the shapes, you can take the ratio of these two plots, and this is what we get. So again, the measured data is in red. The AV18 and N2LO 1.0 calculations with the contact formalism are the black and the blue band. And then AV4 prime is red. And again, as we just saw before with the experiment in Hall A, the data tells us again that there's no way AV4 prime could be the nature's NN potential. And just very briefly to explain to you this shape that you see here, this is the part of the nucleon-nucleon potential which we expect to be spin dependent. So the tensor force cannot couple to PP pairs with spin 0, and that's why PP is suppressed here. And then as you go and you probe nucleons that interact closer and closer, you're probing the scalar core of the nucleon-nucleon potential, and that's why there's a rise here. So that's the amount of information that I have time today to share with you. Just to quickly recap, we talked about the contact formalism that describes the nuclear wave function where short-range correlations dominate. We saw that NN models differ significantly at short distance and high momentum. And even though that's the case, inclusive experiments cannot teach us about the specific nature of the nucleon-nucleon interaction at short distances. Last but not least, if it does tell us about the abundance of pairs, but if you want to know about the specific structure of the nucleon-nucleon potential at short distances, then you can go to exclusive measurements and they can tell us about that. With that, I'd like to finish, and I only have left to say that, of course, this is not not work that I'm doing by myself. We have a very, very large collaboration, and this is hopefully all, and if not, most of the people that helped with all these analyses that I presented today. Thanks.
Very nice. Questions? Do you know specifically what's wrong with the AV4?
Yeah, the AV4 prime potential is only theoretically motivated because one of the things that happens with it is that it intentionally does not have a tensor force. It doesn't have a tensor component. So we know or we think that these short-range correlations come from, or the main region where we probe them experimentally come from the area where the scalar force is minimal and the tensor force takes over. And that's basically what happens here. So the reason why this is 0 is because of the tensor force. And then as you go away from it, the scalar part takes over, and that's why they all agree in here. But so it doesn't have a tensor component. And it's just, we know there's a tensor force, it's just motivated to see what happens if you exclude the tensor force in a potential.
Okay. Other questions? Okay, if not, let's thank the speaker. So, the last talk of the event, the icing on the cake by Pete.
What happened? Wrong way?
Is it?
I guess.
Is it switching automatically? Or?
I have no idea. Oh, no, that's not it. Let's see if you can bring back to the beginning. All right. So the title of the talk is Novel Searches for New Particles at Jefferson Lab. I would argue actually that a correlated neutron-proton pair forms a novel particle at Jefferson Lab. But I actually want to talk about 5 different subjects. First is symmetry tests. The second was physics of stars, particularly neutron stars. I'd love to relate it to the black hole seminar we saw earlier. I'm just not smart enough to. Dark matter searches going on here at the lab. Searches for new particles such as the pentaquark, and searches for forces beyond the standard model. That's not working well at all. That jumped me 10 slides forward or something.
It's probably going to do it again.
Do these get shuffled?
We can try restarting it.
Yeah, let's try that. The topic I want to talk about is, I'm going to put that down.
It's like an automatic scroll through.
Yeah. So the lambda 3 neutron puzzle was the first topic I actually meant to talk about. So the lambda 3 neutron has long been thought to be an unbound system. You can go back to 1958, and there's a paper by Dalitz and Brown which suggests that we should not find it based on isospin arguments. But recently, in 2013, German collaboration HiPi published evidence of a state. And they suggested the state was bound, but it could have also been unbound, which raised the idea that we should try to measure the state at Jefferson Lab. And in particular, we tried to determine the neutron lambda potential. The neutron proton lambda potential, there's over a dozen points in the scattering. That's not a lot, but there's a little bit of data. There's no data whatsoever on the neutron lambda scattering potential. And so the idea was that that might actually help us to understand an unknown feature. So far, all the models of hypernuclei have suggested that they're just going to use the same potential between the lambda and the neutron as between the lambda and the proton. So we did this experiment last November in Hall A. We used the standard Hall A high-resolution spectrometers. The addition of some aerogel detectors helped us with particle identification, but otherwise it was very standard. We used the maximum current that the target could take. This was the tritium target that some of the other speakers have been talking about also, which was about 20 micrograms. Vishnu Pandey's going to, he spoke about this in a flash talk yesterday, and he's going to be speaking about it in a 20-minute talk on Friday also to give us details. Currently that data, which was, again, only taken in November, is under analysis, and he's going to talk on Friday about the state of the analysis, which is mostly looking at the optics right now. So there's another experiment which has been just submitted to the PAC-47, which is to look at charge symmetry breaking in hydrogen 3 lambda and hydrogen 4 lambda. And Toshi Gogami he's actually coming into town tonight. He'll be here tomorrow, I guess. And like most strange physicists, he loves to talk about our experiments. He'll be happy to talk about this one too, also with you. I'm not going to spend any time on it today, just out of time constraints. So what I do want to talk about for a few minutes is the possibility of finding hyperon stars, which would be neutron stars with a non-zero hyperon content. Right? So the idea is that most models for the equation of state of neutron stars suggest the maximum mass should be something about 1.4 solar masses. But recently there's been a couple of measurements above 2 solar masses. I'm showing one on here at a 2 solar mass. There's another one about 2.4 solar masses which has been reported. Those are sensitive measurements which astronomers have made, and they have to interpret the data to give us this out, but they believe the results are robust. So how do these things exist? One suggestion would be that just like a pencil likes to go to a lower state of energy, if you bounce it on its point, any little breeze will push it over. In the same way, neutrons at the edge of the core would like to tumble down into a lower potential state and form hyperons. Right? So to form them, though, we would need to stiffen the equation of state of hyperon stars. To do that, we would need to have better understanding of the potential as well. And so that's what the measurement, which has been approved at PAC-46, is about. And that's to look at 2 isotopes of calcium, calcium-40 and calcium-48, which go then to the reaction at JLab takes place on a proton. So you end up with a different element at the end. But which would give us these 2 points in blue. Let's see if the pointer will work. Here and here. And you can see we're getting a spread then of about a little less than 0.2 in the neutron-proton asymmetry. All right? So the connection to neutron stars, is that we have to extrapolate that all the way up to here, where the difference is almost 1, or about 0.8 something. So it is still a theoretical extrapolation required for that data, but you can see that that's actually not a totally unreasonable arm length to try to extrapolate over. What's plotted horizontally is a to the negative 2/3. And the red points are hypernuclei, so this was one of the better hypernuclei we could look at. The other states for lead, for example, or some of the heavier elements, we don't get too much further if we go to heavier elements. This was a reasonable choice. Okay, the setup we're going to use is to use one of the normal spectrometers in Hall A, one of the HRSs to detect the electron in. But it's got a 23, 24 meter flight path, which means that we'd like to go to something shorter for the kaon. We can use the HKS high resolution kaon spectrometer, which the Japanese have funded and built here at Jefferson Lab. We've used that before in Hall C. It's not in either hall right now, so we can easily bring it to, well, Not easily, but we can bring it to Hall A, and we can install it there. We're going to use a 4.5 GeV beam. That's one of the now standard JLab energies in the 12 GeV era. That's 2 pass. The kaon comes out at a fairly low momentum, 1.2 GeV over C. That's kind of important for us because the HKS has a maximum momentum of right around there, so that for the central momentum. The impact of that compared to previous pion beams is shown on the right. So this is the previous measurements on calcium here with the pion beam. Nue, who helped me prepare the talk, wanted me to emphasize the reaction spectroscopy advantages of Jefferson Lab. In particular, the particle ID has given us really clean spectra. So these are simulations, these are not actual data, but they are based on the type of clean data that we saw with 12 GeV. One of the impacts, I'm sorry, we saw with 6 GeV. One of the impacts with the 6 GeV data was that we could actually see, for the first time ever, we could see excitations of the core proton or neutrons versus the, say, the S or the P shell lambdas. And so this type of spectra is what we expect after we've done all the background subtractions for the new experiments. What that means in terms of an impact is I'm trying to show here. So what's plotted again on the upper graph horizontally is a to the negative 2/3. In the gray box is where our measurements would take place. And you see a handful of points in there. They're for different values of the potential, and CT is this parameter that we're varying in the AFD-MC models. And what that tells us then, you can see on the bottom here, based on different values of CT, we should actually see very different values of the binding energy for the lambda in these two nuclei. And so this is why we think that we'll have a reasonable chance of disentangling this piece of physics that can tell us about the neutron stars. All right. Before leaving the topic of kaons and strangeness, I do want to mention one other recent measurement. This is perhaps not quite as exotic, but the LT separation on kaons at 12 GeV just finished taking data in Hall C recently. Richard Trotta spoke about that yesterday in a flash talk. He's going to talk about it at a little more length on Friday at 3:30. What that measurement did was that it gave us the first cross-section data for high Q squared to test scaling of the cross-section for kaons. So we've already established that we believe we see it for pions. Can we also see it now for kaons as well? That first separated kaon cross-section, it's also interesting because we're above the resonance region for the first time. So previous measurements in any of the halls have always been, by necessity, confined to lower values of W, right around the resonance region or deeply in the resonance region. Right? In addition, we're looking at the t-dependence of the separated cross-sections. For example, in particular, we're interested in the t-dependence of the longitudinal cross-section. We're hoping that the data will allow us to try to get out the kaon form factor for that. And plotted here on the right is the missing mass spectra. This is the one at high energy where we happen to get a bigger bite of the invariant mass spectrum, and we can see more of the excited states due to that. All right. So I'm going to switch gears now and talk about dark matter searches. Technically, that we're not looking at dark matter. We're actually looking for the dark photon, which would be exchanged between dark matter particles. This is the APEX experiment. I was interested to see one of the telescopes this morning, and the black hole talk was actually labeled APEX. It's an interesting coincidence. But this would be sort of physics beyond the standard model, since the standard model doesn't address dark matter. The dark matter observations so far have all come from astronomy. We don't know that there is a dark photon, but this would be the force mediator between dark matter, if there was an additional force between them then. So the technique is to look for positron pairs coming from the interference between the virtual photon production and between a prime or a heavy dark gauge boson production. So this is a bump hunt, which we heard a couple talks ago was not what they were doing for the Omega search. This is a bump hunt, very much so. And so we're actually looking for a little peak hanging out on top of the regular E plus E minus spectrum that we would see. You can see the diagrams for it here. There's a cartoon here for it. And you can also see a cartoon of what it looks like with the septa. One feature of most of the measurements that we're talking about today is that a lot of them involve the use of septa to try to get to smaller scattering angles, because at this point in JLab's life, we're trying to look for really small cross-sections. So we can enhance that cross-section by going to a larger virtual photon flux if we go to smaller angles. All right. So this is data from the 2010 running. Apex just finished about 3 months ago, I guess. And so we don't have data like this yet from the recent Apex running. But this is the test running with about 770,000 events. We were looking for a small, narrow bump on top of the large, smooth background. The shape of this background is given by the spectrometer coincidence acceptances. So to do this, we obviously need excellent mass resolution so that we can see this narrow bump sitting on top of a very large background. And this is the results from the 2010 test run. We could exclude the blue region here based on that test run. You see this little jagged, that's where the different slices that we took didn't quite match up. And based on the recent running, we should have a tighter exclusion band. You can see the phase space is sort of narrowed since 2010. This is the data here outlined in red that we have covered that phase space now in the just collected data sample. So the data sample that we just collected is excellent quality. We are currently analyzing it and looking to have results in about a year. But you can see that there's a fair amount of phase space which we would still like to explore and cover this phase space right sort of here. And Bogdan's going to talk about this more again on Thursday. He's got to talk tomorrow afternoon about that. All right, so switching again, this is moving back to Hall C to a just completed experiment on JSI production. This is the search for the LHCb charmed pentaquarks. This is sort of a new particle search. So LHCb believed that they saw a new particle. It could be a bound state, or it could again be a resonant state. That resonant state could have been enhanced. A few years ago, we actually looked up an old CERN search where they had shown that you can take a flat distribution and you can produce artificially a peak by just putting random cuts, well, they're not quite random, but putting select cuts, let's say, on about 10 different variables, 10 independent variables. You can produce a peak out of a otherwise flat background. And so it is possible that they accidentally produce this peak. Jefferson Lab forms a perfect place to try to see if this thing really exists. And so this is the online spectra that they obtained. What's plotted is the energy of the photon horizontally here, and the absolute value of Mandel's CMT on the vertical axis. This is the absolute value, so it's a positive quantity. So the two lower bins here correspond to the lower T values, and this one would correspond to slightly lower photon energy, slightly higher photon energy. And then we've got sort of a middle T and a high T cut that they were able to take. And you can see here the number of events which we measured per coulomb in that measurement. And this forms the largest JSI data set ever produced with a photon beam, right? And the aim is to produce a verdict or result on whether the pentaquark exists within a year or so. And there was a nice talk on Monday about this from Sylvester Houston. There is another talk, well, there was already a flash talk yesterday also by Burka, and there's another one tomorrow afternoon also, another talk, which will be about 20 minutes. This must be a feature of going to PDFs. That should be the correct JSI. But they have the potential to double the statistics on what they measured, because you have about a 5.94% branching fraction for the JSI to go to E plus E minus, and about a 5.93% branching fraction to go to mu plus mu minus. So this is a preliminary mu plus mu minus spectra, which will basically double their statistics by adding this channel to it, which will, again, make it even larger, the largest real photon sample ever measured. Okay, and then we come to the molar experiment. So the molar experiment, this is a fairly dense slide, so let me slow down a little bit for this one. The molar experiment we heard earlier in the thesis talk about Q-week. This is similar to what they did with Q-week, but this plot here is a really fun plot to look at. You can see where the Q-week asymmetry was. You can even see some asymmetries which were as large as almost 10 to the minus 4. This is an evolution that we've marched down at the lab, and you can see now molar is aiming for something which is a few times 10 to the minus 8. That's really pretty impressive, that we reached that status where we can control the beam asymmetries, we can control everything to a few times 10 to the minus 8. So if we look at these measurements, you can just about spot all the ones. They've all been nicely labeled here for us, all right? So what they're trying to do is to measure sine squared theta W, 1 minus sine squared 1 minus 4 sine squared theta w, it's almost 0. It should be about 0.08 or so. And so by measuring that very, very accurately, we can look for a deviation from the standard model. So this is also a search for physics beyond the standard model. In particular, it's a search for a new force beyond those known to the standard model. And this is the schematic of what the detector is envisioned to look like. One of the really fun things, we've been talking about using the use of septa to try to get to smaller scattering angles. Here they're using a septa to, well, they're not using a septa, they're using a special magnet to get to angles as small as a 1/4 degree. So that's really a challenge. And the backgrounds are going to be immense, obviously, which means that they have to take special attention to the collimators. So there's a double bounce collimator system plan where you would need to bounce twice to get it into the detectors. This does fit within the Hall-A physical framework. Another one of the fun challenges for this is a 1 1/4 long, a 1 1/4 long target that they're going to use, which will handle up to 4 kilowatts. So at least to me, it wasn't so long ago when we wondered if we'd be able to do a 1 kilowatt target. So this is actually a very impressive target which is being designed for this. And 130 gigahertz rate, that's obviously not going to be a counting experiment. That's going to be an integrating experiment for this. So this is a picture. One of the features of this magnet is that we've had a lot of experience with superconducting magnets here at the lab, and as a result, the collaboration decided to go with a normal conducting magnet. And this is a prototype of one of those coils for the magnet. One of the features of it is that it'll actually be defocusing in the phi angle, but focusing otherwise. And so you can sort of see the strength of the magnetic field here. And so that should give them the resolution they need to do the scattering. So the outlook on this is actually very optimistic at this point. There's a $35 million MIE funding which has been requested. There's 2 recent reviews. The most recent was just this year. And they're hoping to start the project next year. It's a 4-year construction. And then it would take 3 years to run the experiment, which means that the experiment could actually be running 2024 optimistically, and could be completed 8 years from now, optimistically. All right. The collaboration is 30 institutions with 120 physicists in 5 different countries. This really is an evolution building on the knowledge gained by the lab in the past set of experiments. And my guess is that the number of PhD students is going to increase over 13. That's what we currently have listed. Mark Pitt gave a really nice talk of this yesterday afternoon. The slides are up now, I think, on the web page, and you can go back and you can look at his for a lot more details on this experiment. All right, so in conclusion, I'm just a minute or 2 late, I think. The Jefferson Lab program is a lot more diverse than doing just neutrons and protons. Yeah, but that diversity also comes with a huge set of equipment requirements. So we've now standardized SEPTA. We probably have 6 or 8 different designs for SEPTA, which have a lot of similarities, but they aren't all superconducting. Some are normal conducting. The majority, I think, now at this point are normal conducting. They've allowed us to reach really small scattering angles. We've also had to create new targets, and in particular, new target geometries for these experiments. Some of the experiments have required specialized particle identification, and most of them have required strong rejection of backgrounds because of the small scattering angles. We required specialized magnetic spectrometers, not just the molar, but also the HKS and other experiments like that. Typically, these specialized requirements come with specialized accelerator needs also. So new requirements, different requirements. Parity beam is not the same thing as hypernuclear quality beam. We need different requirements on, for example, energy spread or centroid. We don't typically, in the hypernuclear experiments, care too much about the polarization. That's not one of the things we're sensitive to. We would be sensitive to changes in position on target, but perhaps not at the same level that the parity beam is trying to control it. And the stabilities are a big thing, too, that we're trying to measure. So beam energy stability is a very big thing for hypernuclear, for example, also for the molar. And so some of those techniques, actually, that we had working at 6 GeV are not currently working at 12 GeV. That includes the synchrotron radiation, for example, or the OTR, which we don't currently have working in the accelerator yet, but which are planned in the next year or 2. Thank you very much for your time.
Thank you, Pete. That's an impressive array of all different kinds of work. Are there questions? Surely there are questions.
What's under the blanket? We're all dying to know what's up here.
That's her job. She's going to tell you.
All right, I'll turn it over
in
to you
due
guys
time.
then. You don't need that? Okay.
Okay, well, let's thank the speaker again and have a little bit of fun.